Okay. So we start that.
Assalamu alaikum. Good morning, ladies and gentlemen. I am honored today to welcome you all to the second International Conference on Chemical and Materials for Emerging Technologies, Sustainable Development Goals Edition. This is Noor Badr from Center of Advanced Material at Qatar University, and I will be your MC for today. The VP of Research and Graduate Studies, Professor Mariam Al-Maadid, dear professors and researchers who are joining us today, and my colleagues. I would like to welcome you all in this collaboration event between Qatar University, represented with Center of Advanced Material and Emerging Materials Journal, Journal of Chemistry Africa, and UNESCO. Today's agenda will contain two sessions. Morning session will be considering SDG Goal 13, climate change, and Goal 6, clean water and sanitation. Evening session will be considering Goal 3, good health and well-being, and Goal 6, clean water. Where in both sessions, a group of professors will enlighten our vision with their latest research updates and share with us their informative presentation. Without any further delay, I would like to start our schedule for today by welcoming the Vice President of Research and Graduate Studies, Professor Mariam Al-Maadid, to the stage for the opening speech. Professor Mariam, the stage is yours.
Thank you, Noor. Ladies and gentlemen, good morning and assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. I am delighted to welcome you all at the second International Conference on Chemicals and Materials for Emergent Technologies, SDGs Edition 2022. Happy to see the organizing committee is from academia and other international entities, Center for Advanced Materials in Qatar University, at Qatar University, in collaboration with the UNESCO chair in desalination and water treatment for sustainable water security, Emergent Materials Journal, and Chemistry Africa Journal. I am much delighted to see the number of participants and appreciate your interest in attending this international online conference. I extend a warm welcome to Mr. Salah Khalid, Director of the UNESCO Office for the Gulf States and Yemen, Mr. Naimi Koumain, CEO at Nakad Printers, and Dr. Mohammed Shehemni, Editor-in-Chief of Chemistry Africa. And welcome to all of the distinguished speakers who will present their lectures here. Qatar University is targeting the Sustainable Development Goals through education, research, and innovation, which is also reflected in this conference with sessions focusing on climate change, health, clean water, affordable and clean energy, industry, innovation, and infrastructure. I wish all of you a great learning experience and have a great day. Thank you. Noor?
Thank you, Dr. Mariam. Now I would like to welcome the Director of Center of Advanced Materials, Dr. Mohammed Rashida.
Assalamu alaikum. Ladies and gentlemen, good morning. It gives me great pleasure to welcome you all to this conference entitled Second International Conference on Chemicals and Materials for Emerging Technologies, Sustainability Development Goals Edition 2022. This conference is organized by the Center for Advanced Material, CAM, at Qatar University, in collaboration with UNESCO Chair in Desalination and Water Treatment for Sustainable Water Security at Qatar University, Emergent Materials Journal, and Chemistry Africa Springer Publisher. Thank you all for spending time in your busy schedules to attend this online international conference. It is also an honor for me to welcome Professor Mariam Al-Maadid, Vice President for Research and Graduate Studies at Qatar University, to this event. I am delighted to welcome Dr. Mohammed Shehemni, Executive Editor-in-Chief of Chemistry Africa, Mr. Koumain, CEO at NKAD Printers, Mr. Salah Khalid, Director of UNESCO Office for the Gulf States and Yemen, to this conference. I'm also delighted to welcome all of the eminent speakers who will deliver their valuable talks during this conference. In addition, I'm honored to welcome representatives of our academics, experts in various fields, other dignitaries, and students to this online conference. In Qatar, the Ministry of Environment and Climate Change is exclusively dedicated to addressing matters of environmental concern, ensuring that sustainable and climate-conscious practices are adapted throughout all sectors, while also overseeing the optimal implementation of the national environment and climate change strategy. In addressing the challenge, Qatar is actively working toward managing risks associated with these issues. There are several significant and positive developments. For example, Qatar by 2030 planning to improve water quality by reducing pollution, eliminating dumping, and minimizing the release of hazards, substantially increasing recycling and safe reuse globally. To achieve SDG goal number 3, good health and well-being in Qatar, support the research and development of vaccines and medicines for communicable and non-communicable diseases that primarily affect country development, and provide access to affordable essential medicines and vaccines. Moreover, in Qatar, policies are developing to support domestic technology development, research and innovation by ensuring a conducive policy environment, among other things, industrial diversification and value addition to commodities. Having the opportunity to speak with all of you today has been a great pleasure. Thank you for being so patient. I'm honored to be among such accomplished individuals and to be able to present my perspective to you all. Thank you again and have a wonderful day.
Thank you so much, Dr. Shadat. Now, I would like to welcome Mr. Salah Khaled, Director of UNESCO Office for Gulf State and Yemen. Mr. Salah, you can speak. Mr. Salah, can you hear us?
Hear me now?
Yes, great. We can hear you.
Okay. Thank you so much. Dr. Mariam Al-Maadid, Vice President for Research and Graduate Studies, Dr. Mohammed Al-Shidat, Director of Center for Advanced Materials, distinguished ladies and gentlemen, good morning to you all. Assalamu alaikum. First and foremost, I would like to congratulate Dr. Mariam Al-Maadid for her leadership, Dr. Mohammed Al-Shidat for his guidance, as well as Professor Saeed Zaidi for putting together an excellent research program leading to the successful establishment of the UNESCO Chair on Desalination and Water Treatment, which officially launched in 2021. We are very keen on working together, and we stand ready to strengthen our collaboration and foster scientific cooperation and exchange of expertise towards developing joint research programs to address most pressing challenges in the region. Ladies and gentlemen, in 2015, world leaders have adopted the 2030 Agenda for Sustainable Development, comprised of 17 goals. These goals constitute a roadmap for countries to take action and implement coordination mechanisms and partnerships in response to urgent global challenges. As part of their commitments to the 2030 Agenda, states have aligned their national policies and strategies to a set of specific goals and targets to be achieved by 2030 and beyond. Next year will mark the halfway point of the 2030 Agenda. However, according to the 2022 edition of the Sustainable Development Goals report, and I quote, the SDGs are in grave jeopardy due to multiple cascading and intersecting crises, predominated by COVID-19, climate change, and conflict, end of quote. As it is all too evident by now, the world has almost been brought to a standstill over the past years due to the pandemic. While its overall impact may not yet be fully understood, both in terms of its human, environmental, and its socio-economic effects on nations across the globe, the pandemic was an opportunity to harness the power of sciences and experiment with emerging technologies, not only to meet our needs, but also to build national data ecosystems to monitor COVID-related cases and support decision-making. Many countries staffed their COVID response committees with scientific advisors and mobilized their national research institutes to respond to knowledge gaps and advanced COVID-related research. The pandemic highlighted the important role that peer-reviewed science and scientific research can have in addressing the most pressing challenges of our times. Within this context, UNESCO has been advocating for strengthening scientific collaboration and the openness of science, which led to the formulation of the first international standard-setting instrument on open science in 2021 in the form of a UNESCO recommendation on open science. The recommendation outlines, first, a common definition on open science, also its core values and guiding principles, and finally, recommendations for priority areas of action. Ladies and gentlemen, strengthening the science policy interface is key to determining evidence-based pathways to sustainable development, leading to more innovative, transformative, and policy-oriented actions. As you know, the Arab region will host several major events, including the 5th United Nations Conference of the Least Developed Countries, the LDC5 in Qatar in March 2023. We have also the 27th session of the Conference of the Parties, the COP27, to be held in Egypt, and the COP28 in UAE next year. These events are an opportunity not only to take stock of our progress against targets, but also to continue mobilizing the scientific community and reinforcing the role of educational institutions in contributing to climate action, water security, protection of ecosystems integrity, and building resilient communities. As the UN leading agency for the SDG 4 and the only specialized agency in the field of sciences, we have the convening power, a multidisciplinary and cross-sectoral expertise, and a wide network of in-house institutions and centers, as well as UNESCO-affiliated schools and chairs all around the world. However, collaboration with national and regional stakeholders remains key to local solutions, pooling resources and expertise, as well as enabling a dialogue between scientists, decision makers, businesses, and the civil society. It is my pleasure today to welcome you all to the second edition of the Chemicals and Materials for Emerging Technologies, which will highlight the role of science, technology, and innovation in achieving the SDGs. I wish you all fruitful discussions, and it has been a real honor for me to be with you at the opening. Thank you very much.
Thank you very much, Mr. Salah. Now, I would like to welcome our partner in this conference, Dr. Mohammed Shahimi, the Executive Editor-in-Chief of Chemistry Africa Journal. Dr. Mohammed Shahimi, can you hear me?
Yes, very well. A very good morning, everyone. Thank you very much, Noor, for the introduction. I would like to thank, first of all, my dear colleagues from Qatar University for organizing this second edition of Chemicals and Materials for Emerging Technologies, where the first edition was held in November 2020 during the lockdown. It was a successful meeting, e-conference. And this morning, I would like to thank again Professor Mariam for supervising the whole organization of the second edition. My thanks also to Dr. Mohammed Shidat and Dr. Salah Khalid for their kind words about sustainable development and the organization of this important meeting. I am very grateful also to Dr. Kishore and Mrs. Noor for the time spent over the last 2 months to plan the meeting, schedule the lectures, inviting distinguished speakers. I would like to say a few words about the importance of the second edition. I have noted that it was a very good initiative from Qatar University to change the type of conference. The first edition was really on chemistry and materials for emerging technologies, but sorted by disciplines and very specific topics in physics, chemistry, material science, and it is really a very different spirit we have today. It means that we have shifted this conference, a scientific conference, to a conference that targets the sustainable development goals of United Nations. So now we do not target only the disciplines, but also we have a holistic approach for the sustainable development goals, and this is what makes a very big difference with the first edition. And I think we in the coming years we will see more and more publications and books that have a holistic approach for the sustainable development, and not only doing some innovative chemistry or physics or material science separately. Now we have a more general approach, and which means the need for collaborative work between specialists in different topics. So thank you again for the whole organization, and I thank the speakers who have accepted to join us and to give excellent presentation of their works, and I thank them very much in anticipation to share their knowledge, and thank you again for the whole organization. So have a good conference, and enjoy the KMET 2022. Have a good day. Thank you.
Thank you so much, Dr. Shahini. It's always a pleasure to work with you. Now I would like to welcome Nahimi Kumain, the CEO of NKAD 3D Printing. Mr. Kumain, can you hear me?
Yes. Hello, everybody. Can you hear me?
Yes.
Okay.
Yes.
First of all, thank you for this invitation. So, as I said, my name is Nahimi Kumain, and I founded the company NKAD Printers, and we are specialized in additive manufacturing. My profile, I started as a material and process engineer, and also industrial engineer, and I studied at the University of Paris-Saclay, more precisely at Central Paris, and also at the University of Limoges. So when I started to work, I didn't go directly into the entrepreneurship. I started to gain experience working in different companies. I already had the idea of starting my own startup. So when I decided to start it, I had let's say this background and those skills that you acquired at the university. For example, during the last year of studies, what we do is like some workshop, how to manage a company, how to start your company, study the market. We also had some courses on accounting and, let's say, all the soft skills required to start a company. And I have to admit, it was not easy because, as you know, a company, it's so large a set of skills that you need. It's really learning by doing. And I liked this metaphor when they say that entrepreneurship, it's like jumping out from a plane. And when you jump, when you are in the sky, you start to build your parachute. For me, it's a really good image to explain what is this adventure. And during this adventure, it was really great for me, and it's still great because, as you know, it's a technology for the future, and it's really a sustainable technology, because when you look, for example, in the building sector, additive manufacturing, 3D printing give you the opportunity to use local materials, and also to use less weights, because when you compare those process compared to traditional manufacturing technology like milling, for example, you produce less waste. And you have also other application. For example, many companies today say, okay, we want to use materials that are available and not used. For example, single-use plastic. Today, many companies use single-use plastic with additive manufacturing to produce furniture. Also, I don't know if you know some companies using it to produce molds or boats. So it's really a technology that gives you the opportunity for sustainable development. Yeah.
Thank you so much, Mr. Kumail.
Thank
Now,
you.
I would like to welcome you all for our first session. And the moderator will be Professor Saeed Zaidi from Qatar University and Professor Muhammad Hassan from Center of Advanced Material. So, Professor Zaidi, the floor is yours.
I'm audible? Okay, can you hear me? Okay, so now we have the first this keynote speaker today is from University of Technology Malaysia, Professor Muhammad Hafiz Usman. He's a Dean of Research and Chair, Frontier Materials Alliance, University of Technology Malaysia. Professor Hafiz is a professor in schools of chemical energy engineering, University of Technology Malaysia. He earned his PhD in chemical engineering from Imperial College London in 2011. He was the director of Advanced Membrane Technology Center from 2018 to 2021. And currently he holds the position as the chair of Frontier Materials Alliance. His research lies on the development of innovative membrane technology in removing pollutants from water and wastewater, as well as for efficient energy generation. He has published a number of papers, more than 400 research papers, 30 book chapters. He has very high H index and he has more than 7,000 to 8,000 citations. He's a very accomplished researcher. He's a member of many societies, member of many forums, and he has conducted more than 50 projects and supervised a number of students. So so we welcome Professor Hafiz Usman. The title of his talk is Ceramic Hollow Fiber Membrane Derived from Naturally Occurring Materials for Water and Wastewater Treatment Application. Thank you, Professor Hafiz Usman, and now floor is yours. You can start your presentation. Thank you very much.
Thank you so much, Prof. Javis Saidi. Can you hear me well? Can you hear me?
Yes, yes.
Okay. So first of all, I would like to express my gratitude to the Organizing Committee, Center for Advanced Materials, especially Prof. Said Zaidi for inviting me to give some sharing in this conference. I'm very delighted able to share some of the research that I'm doing in our center. Okay, so my name is Muhammad Hafizahman Osman. I'm from Advanced Technology Center, University of Technology Malaysia. So our center is the only research center in membrane in Malaysia, and we've been recognized as a national center of excellence for reclamation. Okay, so for the topic that I'm going to give today is the ceramic hollow fiber membrane derived from natural occurring materials for water and wastewater treatment application. So there's no doubt that membrane technology is one of the most promising technology for suppression, especially for water and water treatment. Okay? But membrane is always associated with the high cost. So one of the reasons that make the membrane is quite expensive is because of the manufacturing process of the membrane. Normally, in order to produce a membrane, it's require a very sophisticated process in order to produce uniform pore size on the membrane structure. Because the pore size is very important for membrane in order to make sure that membrane have a very good selectivity and can act as a selective barrier and allow the certain person to pass through. Compared to the other normal coating layer, normally they don't have a specific process solution. They are very random, but membrane it must have a very narrow process distribution. So normally membrane are classified according to the type, according to material. Okay? So we can find the membrane either as an organic membrane made from natural polymer or synthetic polymer, and this very well known and commercially available in the market. Example of the organic membrane is polyvinyl chloride, PFP, and polypropylene. And another types of membrane, we classify them as a inorganic membrane. So you can divide them into ceramic membrane, carbon membrane, and also metal membrane. Okay? And it's also commercially widely used is alumina type of ceramic membrane. Okay? So a combination between an inorganic membrane, they also have another piece of membrane, what we call as the mixed membrane. And mixed actually is the base is a polymeric membrane, but normally they add some inorganic material as additive, and this is in order to increase or improve the performance of the polymer having inorganic material in it. So this is actually is to further enhance the property of the membrane. However, due to the incorporations of this another material into the polymeric matrix, normally the agglomeration, so leaching is always an issue. So this type of membrane normally we cannot not find always in the market because most of the mismatched membrane is still under development. Okay. So if we compare the two types of membrane that is always in the market, commercially and what we use in the market industry. So polymer and ceramic membrane. So both of them have a pro and cons. Like the ceramic membrane, they are very superior in terms of chemical strength and also in terms of chemical and thermal resistance because of the nature of the ceramic material is very tough. But it also they can use it for longer lifetime. Okay? So for ceramic membrane, we can use it for more than 20 years sometimes. Compared to the polymeric membrane, you need to replace them. You need to replace them every 4 years, every 3 years. You have to replace them. But ceramic membrane, you can use them for many years, 20 years, 15 years. So therefore, the ceramic membrane is, better in terms of mechanical strength, chemical, and also thermal resistant. However, the main issue with the ceramic membrane is the cost. The ceramic membrane is very, very expensive compared to the polymeric membrane. And ceramic membranes also have issue with the brittleness. Is also brittle because of the nature of the ceramic is quite brittle. So therefore, ceramic membrane is not widely used as compared to the polymeric membrane. Although it has many advantages, but normally we don't use a ceramic membrane in water treatment or in a common application. Normally we can use them or we commonly being used in a harsh condition operation, not in common operating condition operation. So the common structure of a ceramic membrane normally is asymmetric, meaning that the top and bottom layer have a different structure. So if you can see here, so the ceramic membrane normally composed by a porous support layer, and the pore size is more than 1 micron. And then we have to deposit one layer to close up the gap to make it more denser. And if we like to achieve a denser structure, so we have to add more layers, deposit more layers. Okay? So you can look at this presentation. So if you want to achieve like microfiltration, that actually is the biggest pore for water treatment. Okay, so normally the pore size is between 10 nanometers to 3 micron. Okay? So if you want to achieve microfiltration, probably you just need to have like 2 layer. But if you want to have like filtration, you have to add more layer. And in fact, if you would like to use it for filtration and just you have to add more and more layers. So this is how the ceramic membrane works. And the preparations of the ceramic membrane conventionally is a very multiple step process. So it is a very tedious process. So you need to prepare the ceramic slurry base by mixing the powder. Okay? Normally alumina or zirconia. Normally you have to mix with some of the solvent and to prepare the ceramic slurry of this. Okay? And then you can use either acetic casting, or pressing to produce membrane, or we can use another technique called extrusion to produce a tubular membrane. The tubular is like a tube, like a straw. Okay, so until then we can get the membrane precursor, the support precursor. So we have to undergo the sinking process. So we will burn off some of the solvent or some of the glue that we use during the slurry preparation. So after that, we have to deposit the coating layer by using either vapor deposition or deep coating. Okay, so this followed by another sinking process, and we have to repeat this process all over again until we get the desired structure that we would like to achieve. Okay, meaning that if we want to achieve a smaller pore size, so we need to deposit more layer and do more sinking. So this is some of the reason what makes the ceramic membrane expensive. Firstly, is because of the expensive raw material for the ceramic membrane. Alumina is zirconia. It is probably 5 times much expensive than the polymeric material. For example, you can get a polymeric material like 100 USD per kilogram, but for the ceramic material, probably you have to purchase like 500 per kilogram. Okay, so it is like 5 times more expensive than polymeric material. So if we talk about the fabrication method and the ceramic membrane, normally, like I mentioned, you have to use or undergo multiple step process to produce the smooth structure. You have to do extrusion, sintering, position, and sintering, and you have to repeat this process many times. Okay, and also we need to undergo high sintering temperature. The alumina and zirconia require the sintering temperature above than 1,400, which this consume a lot of energy for production. And also the configurations of ceramic membrane normally available in the market is either as a flat shape, like this one, or as a tubular. Okay, so this one actually is relatively lower surface area. So you need to have more and more ceramic membrane in order to cater a large volume of fit. Okay. Therefore, the strategy to reduce the cost of ceramic membrane has been proposed in the literature before. So we can use either we change the raw material to alternative material that are abundantly available. This one is like a clay type and many other types of material we can use to replace alumina and zirconia. And also the fabrication method, phase inversion. Phase inversion method probably people in polymeric membrane have heard. This one is a very common method for polymeric membrane production, but not very common for ceramic membrane. And we also can, introduce this type of method for production of ceramic membrane uh, in order to get a smooth structure in a single step. And by having this method, we can also produce the hollow design. Hollow fiber is similar like a tubular, but it is a smaller in diameter. So normally diameter of hollow fiber is like 2 millimeter, and thus we can increase the surface area of the membrane. And this is the amount, potential material for ceramic membrane, what we can consider as alternative material. So this alternative material is very, very cheap. You can sometimes for free. Sometimes it's just less than $1 per kilogram compared to alumina and zirconia. So the criteria before we choose this material, either it is suitable or not to be used as a ceramic material, it is must be non-toxic, abundantly point, abundantly available, and also low cost. So we can categorize them into three main categories: natural occurring material. Normally, it is a clay type, which has a hydroxyl group OH, and this can induce a super hydrophobic property, which is very favorable to be used for water treatment. So some of the examples of this natural occurring material is kaolin, bauxite, and silver. And another type is agricultural or industrial waste. This type of material contains of silica and also low melting point, and this type of material normally have a good absorption capacity. Example for this agriculture or industrial waste is rice husk ash, palm oil ash, and also fly ash. And another type is animal bones, like cow bones and also chicken bones. This one can produce hydroxyapatite through a simple calcination. And also this type of material have a unique rod that promotes specific pore range in membrane. So this table shows chemical composition of alternative ceramic that has potential to be used as a raw material for ceramic. Kaolin, bauxite, zeolite, fly ash, rice husk, palm oil ash, sugarcane ash. So if you can see from this table, we can see that major component for alternative material is alumina and silica. Okay. So since silica have a little bit lower sintering temperature than alumina, so the higher the content of silica inside the alumina, inside the material, so the lower the sintering temperature of the ceramic membrane. Okay. So in this alternative material, there is also some impurities. Okay. These impurities can be disadvantageous because it can create a lot of problems. But some of the impurities, it can act as the sintering act as well, meaning that it can further reduce the sintering temperature of the ceramic membrane. So the normal sintering temperature to produce a membrane is 1,400 Kelvin. But by having silica and other, you can reduce as low as 1,000 degrees Celsius. So 400 degrees Celsius difference is very big, for energy consumption. And how these impurities can act as a sintering aid is based on the mechanism of liquid phase sintering. Okay? So certain temperature, for example, at 1,000 degrees Celsius and above, so some of these impurities, for example, oxide, carbon dioxide, gallium oxide, they can melt. Okay, they can melt because the concentration is quite low, so they can melt and they can glue the main component like silica and alumina together. So it can further reduce the sintering temperature of production for the ceramic membrane. Okay, so this is the technique that been introduced in the early of 2000 by a group of researchers from Imperial College. So they use this technique, a dry jet wet phase inversion combined with sintering process in order to produce a hollow fiber ceramic membrane. Okay, so the step is like this. So we have to prepare the dip suspension preparation by mixing of the ceramic material together with solvent and some polymer and we extrude dip suspension through syringe pump. Some agate, okay. So we use a spinneret to mold become a very nice shape. Okay. Have a side. So we also have to inject the internal coagulant, produce the lumen, to produce the ball inside. Okay. Because of this process, phase inversion. So this phase inversion is a solidification process. So the mechanism of this solvent and solvent exchange will lead to the viscous fingering phenomenon. So this viscous fingering phenomenon will induce the structure of the finger line. Okay, finger light, meaning that you will get the microvoid void that's similar like your finger, okay, in terms of the shape. Okay. So the combinations of finger light and sponge light in the membrane, this one is what we call as asymmetric structure. Okay, this asymmetric structure is very, very important for ceramic membrane because it can have a good separation, very efficient in terms of the separation, and obviously it can give you very high flux permeation with very less resistance. Okay. So once you get the precursor, okay, you need to undergo another centrifugal process in order to burn off your polymer binder and some of the leftover solvent in order to make it into a very strong ceramic membrane. So this process we consider as a single step process to produce a symmetric structure compared to the conventional technique. You need to involve a very much step process. You need to undergo a several sintering procedure. But for this one, you only need to produce or undergo one sintering process. So in terms of the publications of ceramic hollow fiber membrane, okay, the first publication is 1969. So it's keep increasing, and a tremendous increase we can see started from 2000, early of 2000. This is because of the introductions of the phase inversion process to produce the ceramic hollow fiber membrane. Okay, so by using this technique, so many researchers have involved in this research, including our center in University of Indonesia. So now, up to 2021, we are considered as the first contributor of this area for ceramic hollow fiber membrane. So the research in our center is we use many types of materials. For example, the mature acrylic material. So we have fabricated kaolin membrane, mullite membrane, boxley membrane, silica sand membrane, natural zeolite membrane, and also bauxite. For the agricultural and industrial waste, we have used rice husk ash as the raw material to produce membrane, palm oil peel ash membrane, aluminum dross membrane, fly ash membrane. The aluminum dross and also fly ash the waste from industry that we can find it a lot in Malaysia. Okay, so we use it as a raw material for membrane production. And we also can use the animal bones, for example, cow bones and cockroach. This material we can into hydroxyapatite and we can use them as a membrane. So if we many types of ceramic membrane, okay, low cost and also pure metal oxide. So we can see that sintering temperature, the low cost membrane is lower than the pure metal. We take the alumina, we have to sinter them. Same goes to zirconia and lithium stabilizer. So, but it's different case for the low cost ceramic membrane. So normally you can achieve a good membrane at as low as 1000 degrees Celsius. Okay? So meaning that the temperature for productions of ceramic membrane is much lower compared to the pure metal oxide. In terms of the mechanical strength, so we can see that yes, some of the material like rice husk, kaolin, the cane bagasse, they have a lower in terms of mechanical strength compared to the pure materials. But some of the material, for example, bauxite, sand, and mullite, they have a comparable mechanical to the metals. So this is indication that the low cost ceramic membrane also has a potential to replace the pure metals. And in terms of the pore size and porosity, it's not much different. So this low cost ceramic membrane can be considered as a microfiltration range, okay, microfiltration range, meaning that the pore size is bigger than 0.1 micron. So the applications of this ceramic hollow fiber membrane, we can use it for many applications, like water and surface treatment, microtubules, fuel cell, and also gas separation. So for this presentation, I'm going to emphasize more on the natural acrylic material. I selected 3 to be addressed in this presentation: silica sand, bauxite membrane, as well as ball clay membrane, okay, for different types of application in water treatment. Okay, so we go for the first material. It is a silica sand. Silica sand, we can get it a lot in seashore, in river shore. You know, we can get it a lot. So the one that we use is have a high concentration or high compositions of silica in 99.5%, and the rest is alumina, barium oxide, and gallium oxide. And we investigate thoroughly the parameter for production in terms of the loading of the ceramic and also the sintering temperature of the ceramic membrane production from 1200 to 1400. Okay. You see here the structure that obtained from the face is symmetric, contains of like 30% of finger-like void from the total thickness of the membrane and the sponge structure. Okay. So we can also see that by increasing the sintering temperature, the structure becomes denser and denser. And at some point, it just becomes too dense and probably is not too suitable for separated, like 1250. Probably it is too dense and not suitable to be used for. Okay. So when we see in terms of the process distribution, so we can confirm that the pore size of the membrane is microfiltration range. The pore size is 0.18 micron. Okay, it is microfiltration. And we also check the contact angle because of it contains hydrophilic groups. So it shows super hydrophilic property. Okay? So due to the super hydrophilic property, so we would like to use this type of membrane for oily wastewater treatment. The oily wastewater treatment, either it is coming from oil refinery process or from a palm oil mill, and we can use this type of membrane. Okay? So the concept is very straightforward because of the membrane have a very super hydrophilic property. So it will repel most of the oil contaminants or oil pollutants that has a hydrophobic property, and it will allow water H2O to pass through to the membrane. So we can get as high as flux as possible. So this is the setup that we use in our lab. And when we increase the sintering temperature, we can see that in terms of the rejection is indicator the suppression efficiency of the membrane. So meaning that the suppression efficiency is increasing, but at the same time, the flux, the permeability is reduced too much. So from 1,350, we can achieve like 23 LMH. It reduced to 17 LMH, 1,200, and further reduced at 1,400. So meaning that this type of membrane, if you sinter at too high temperature, so it will increase in terms of rejection, but at the same time, it will reduce the flux. So the optimum condition in terms of the sintering temperature for this type of membrane is at 1,150. So you can see from this video, this is actually a moving video. So you can see we have the feed is the oily wastewater contents of the oil contaminants, and we pass through this simple process, and we have the silica sand membrane inside it, so we can produce a quite crystal clear membrane as a polymer. So I would like to introduce is a photocatalytic membrane. Photocatalytic membrane is a combination of the photocatalyst with the filtration membrane. Okay, so you can have like a synergical effect by having this photocatalytic membrane, and many people have used this photocatalytic membrane in research for self-cleaning process. Okay, meaning that you probably very good anti-fouling property have the photocatalyst on your membrane surface. Okay, so we use a bauxite material. Okay, this bauxite material is the ore for alumina, is the main source for alumina production. Okay, so we have a lot of resources for bauxites in Malaysia. So we get the sample for free, okay? And then we we check for the SRF in terms of the ceramic composition. So you can see that the composition is become higher when you do some customization process. And interestingly, inside this oxide, this also contains of a very precious material for catalyst, which is titanium dioxide and also ferric oxide. This two material actually can help in terms of the absorption and also photodegradation of the photocatalysis process. So therefore, we would like to use this type of membrane as the photocatalytic membrane. Okay, so we use the bauxite as a raw material to produce the ceramic membrane. So it is orange in color because bauxite is orange in color. So when we produce the ceramic membrane, we also get the orange membrane. Okay? So it has a sponge-like and finger-like structure as well. So, and we subject these types of membrane for bisphenol A degradation. Bisphenol A is one type of the recalcitrant organic pollutant, one type of indifference of the compound, and it is very difficult to be removed by biological process. So the having advanced oxidation process like photocatalysis here is very helpful to totally remove the presence of BPA inside the cell. So the concept is very quite straightforward. So we expose the membrane with some light source, either it is visible light or UV light, and because of the presence of photocatalyst on the membrane, so it will absorb the pollutant onto the membrane surface. And at the same time, when there is light coming, it will release some of the oxygen radical and carbon radical that will attack to the organic pollutant that already on the surface and degrade the pollutant become carbon dioxide and also H2O. So the final product of this photodegradation is CO2 and H2O. Okay, and at the same time, the membrane will act as the filtration and can filter the water as clean as possible. So in terms of the degradation for a pure bauxite membrane, we get the degradations of bisphenol A as high as 70%. So 70% of photocatalytic degradation. But we know that we can further increase the performance of the photocatalytic degradation. So we try to do some surface modification on the bauxite membrane by conduct a hydrothermal process. We would like to invite another photocatalyst material, titanium dioxide, also copper oxide. Titanium dioxide is a good membrane for UV light driven, and copper oxide is good for visible light driven. Okay. So we would like to test under both light sources. Okay. So we have the coating and CO coating, and we subject them for another degradation test. And as a result, we can see that when we coat with KO2 and expose to the UV light, we can further increase the degradations of the bisphenol A from 70, and we can increase up to 90%. Okay? And in fact, when we use a CO under visible light, we can further increase the degradation almost 100%. So this shows that by doing some surface modification on the bauxite membrane, we can further increase the performance of the membrane. So as I mentioned before, most of the ceramic membrane, it is hydrophilic in nature because of the presence of the hydroxyl group. But this ceramic membrane also can be used for hydrophobic membrane application, for example, membrane insulation and also membrane compactor. Okay, as long as we do some surface modification via the hydrophobization. So there are lots of hydrophobization methods, for example, fluoroacylsilane emission method and salt gel method and also CVD method. Okay, in our lab, we use fluoroacylsilane method because of its simpleness and also fast active. Okay? So we use fast emission method. Okay? And for these types of membrane, in order to turn into hydrophobic membrane, we use a ball clay material. The ball clay material is one of the clay material that are available in Malaysia as well. So it's a compositions of silica and alumina as the major constituent. Okay? So we got this membrane after we prepare phase inversion process. Okay? And we do this fluoroalkyl emission process in order to cross-link the hydroxyl group of the membrane with fluorine group, and then we turn them into a hydrophobic property. Okay, we check the contact angle. So from almost 0°, the water contact angle is become 130° after fast emission method. Okay. So we would like to test this type of membrane for membrane distillation process. The membrane distillation process is one of the emerging techniques nowadays. We use it for seawater desalination. So for this seawater desalination, one of the major issue is if there is organic contaminants, and it will lead to the falling behavior towards the membrane if it's not properly prepared. So therefore, we would like to investigate the presence of the organic contaminants together with saline here. So we use humic acid as the organic contaminants. So let me explain briefly the mechanism of the membrane distillation. Membrane distillation, we have two feed. One is a hot feed, as you can see from the red line. It is a hot feed, so we have to heat up the hot feed up to 80° Celsius, and at this temperature, some of the water will be turned into a vapor. Okay, so the membrane here is not as a filtration, but it's more on as a barrier, okay, as a separator, so that the hot feed and cool feed is not mixed together. Okay, once the vapor is traveled through the membrane, it will reach to the cool side and will be condensed as pure water. Okay, the membrane here, one of the requirements, it has to be hydrophobic because it needs to only allow vapor to pass through, but not water in liquid. Okay? So it's only allow water, vapor, not water. Okay? And it also has to be porous mathematician range so that we can collect as many vapor as possible. So based on our experiment, so we can see that at initial the flux is quite promising, but we can see some degradation, some decline on the membranes, and we predict this is due to the falling of the humic acid on the membrane surface. So we can further prove by see the trends of the conductivity after 500 minutes. We can see that the conductivity is increasing, and this can indicate there is some salt penetration through the membrane as well. So we do some autopsy on the membrane after 500 minutes. So we can see that there is a brown falling island observed on the fluorinated polyfiber. And you can see that some of the pores of the membrane has been clogged as well. So we would like to do some research in order to tackle this falling issue for the hydrophobic membrane. So therefore, we would like to mimic the structure of the lotus leaf structure. Lotus leaf structure, they have noodles, a high peak that can retain the water and have some effluent. And also by having this type of structure, we expect that we can have a very good antifouling property. So inspired by this lotus leaf-like structure, so we would like to turn the super hydrophobic membrane to become the super omniphobic membrane. Okay? So how we can obtain the super omniphobic is we have to do some grafting on the membrane before fluorination. Okay? So previously we used the membrane as it is, and we immerse with fluoroethylene for the surface fluorination to turn into hydrophobic surface. But before we do that, in order to obtain the omniphobic layer, so we have to do some roughening. Okay, so therefore we use the hydrothermal method. Okay, we incorporate the titanium dioxide material by using this hydrothermal method, and by having this method, we can produce a very rough surface on the membrane before we do fluorinations by using this fluoroethylene. Okay. So this is the structure after the hydrothermal process. Okay, we vary the reaction from 2.5 hours up to 10 hours. So we can see there's a two major structure. First is nanorod structure been obtained after 5 hours, and then the flower structure obtained after 10 hours. So we try to make comparison the structure with the pristine membrane. So we can see from the cross section. So the hyperstructure of the membrane is become more significant for the nanoflower compared to the nanorod and pristine membrane. And we also can further confirm by using EDX that there is no penetration of the TiO2 onto the pores of the membrane from this EDX method. So you can see that the TiO2 that deposit onto the membrane is nicely attached on the membrane without penetrate too much deep onto the membrane structure. Okay, this mapping of the yellow dotted is due to the TiO2 present in the initial of the polyethylene material. So we check in terms of the contact angle. We use the water contact angle as well as the low surface tension liquid. So we can see that the structure, the membrane with the nanoflower structure, have a more superior contact angle compared to the membrane with nanorod and also without any hydrothermal layer, and also with the pristine. Pristine is almost zero in terms of the contact angle, either water or any low surface tension liquid. Okay. So it shows that the higher the hyperstructure, the nanorod structure, so the better the resistance of the membrane towards the water and any low surface tension liquid. This low surface tension liquid, you would like to mimic the organic pollen in the during the operation. Okay, so we also check in terms of the robustness of the membrane. We immerse in acidic solution. We immerse in the alkaline solution for long-term operation, for harsh condition with agitation, and for high temperature. We can see that the contact angle is not much difference compared to the beginning. Okay, so this proven that the membrane is chemically, thermally, and mechanically robust. Okay. So we would like to see in terms of the air film formation. Okay. This air film is very important for membrane distillation because we can prevent water to wet on the membrane surface. So we would like to have a more thicker and thicker. So from here, where we immerse in water, so we capture using the optical microscope. Okay, we can see the some of the gap we predict it is the air film. So we can see from here the membrane with a nanoflower structure have a thickest air film compared to the nanorod and also the membrane with fluoroethylene. So how is the mechanism phenomenon is happen is because of this prediction. So by having some nanorod structure, you can entrap air. Okay, when you immerse the membrane into the water. So this entrap air will create the airflow. So the higher of your roughening nanorod, so meaning that the more entrap air can be produced, which is the quicker the air film can be produced. Okay. We further confirm this for the membrane distillation filtration process. So we can see that the falling for the nanoflower is not as severe as the without any modification. Okay, without any modification. So we can further confirm as well by using the conductivity test. So we can see that the trend is stable throughout 500 minutes. Okay. And we also do some autopsy on the membrane. So the membrane is clean, although minutes for the nanoflower structure compared to you can see here island being seen for membrane without any hydrothermal layer. Okay, so we further prove by using SEM. So you can see here is the structure of the membrane still well attached, okay, without any organic pollen attached on the membrane. Yes. So we have experience in the productions of bigger scale for this low-cost ceramic membrane. So we produce 500 membrane, and we install in 100 pieces of membrane in a module. I know that it is quite challenging because the membrane is quite brittle. So the membrane actually is quite brittle, so we have to be very careful. So therefore, before this membrane can be further, you know, pre-commercialized, so we have to resolve all the challenge for the production. So because in our lab we have a quite small furnace, which is the limitation for the large scale production, and also the nature of the silica rich membrane is quite brittle. Therefore, the membrane that produces also quite brittle. And we also have to know that this alternative material, normally the particle size is quite big, probably 5 microns, 10 microns and above. Therefore, is will lead to the formations of less than ceramic packing density and resulting to the bigger pores. So we have to understand how to reduce the pores by adding some smaller particles inside the depth suspension. And also the compositions of the outside is also varies with the location. So for example, if you take it locally from Malaysia, and probably if you take it from somewhere else, so the composition is also vary. Probably you need to further investigate on the impact of this composition. And also the preparation technique for the body for this polyfiber is quite lacking reported in future, so we have to investigate it further. So I think thank you for listening. That's all. Back to you, Dr. Sai. Dr. Sai, can you hear me?
Yeah, okay. Yeah, thank you, Professor Hafez Usman, for your very informative and nice presentation, especially in the membranes for the ceramic membranes have few challenges you have outlined. Now we have time for a few questions. If there is any questions, we can take a few questions. And please raise your hand.
Hello? Hello, can you hear me? Can you hear me?
Yes, yes.
Yeah, thank you very much. It was a brilliant lecture on membranes. Dr. Othman, I have a question about the interface, because these membranes, for example, for water desalinations, they have a chemical stress, the interaction with water at all time. So how do you control the interface between, I've seen when you have shown the video on the electrospinning, how do you control the interface between the ceramic particles and the polymer binder?
Okay. Thank you.
Because you could have demixing of the composite.
Okay. It is a very good question, Prof. So let me explain a bit. So
Yeah.
in here, during the
bottom right, at the bottom right.
So
yeah.
This you're talking about this one, right?
Yeah, exact. Yes. How do you control the interface?
Okay, the interface actually it is related to the particle size. Okay, so the particle size, if the particle size is too big, because during the phase inversion, it is what matter is the intrusions of water to the nascent fiber. Okay, so if we have the particle size is too big, so it's hard for the water to through the membrane. Yeah. So therefore, we have to have a mixing particle size from big to small, so that some of the small particle size will allow the the water to penetrate during this inversion process, and will lead to the viscous phenomenon, and therefore induce this finger-like structure. So what matters here actually is the particle size of the ceramic particles. And regarding to the polymer binder here actually is dissolved in a solvent, meaning that it's homogeneously locate throughout the suspension. So once it get contact with the water, due to solvent and solvent exchange, the polymer binder will start to freeze and solidify. So it will become the glue for the particles, ceramic particles, to become a polyfiber shape.
Okay, thank you very much. Thank you.
Okay, thank you, Prof.
I have a couple of questions.
Yeah,
Dr. Zaid.
Dr. Mohammed Hassan has a question.
Yeah,
Yes, okay.
yeah. Thank you, Professor Muhammad Osman. Very interesting, nice work. So I'm just wondering, it's very interesting method, the dry jet wet phase inversion. And as you mentioned, you save a lot of energy using this method comparing to typical ceramic membranes. I'm just wondering about the impurities. You use the centering to remove the impurities. As we know, like most of these naturally occurring, especially the fly ash, they have a lot of impurities. And you mentioned about this. So I just thought like maybe it might be, I don't know if it will work, a good idea to remove impurities prior to the whole process. You see what I mean? Instead of using the centering to remove the impurities, you just remove it chemically by adding something to make a coordination bonds with other impurities and remove them and try to purify the material as much as you could before you proceed to the dry jet wet and then the centering to make the membrane. So please comment on this if possible.
Okay, thank you, Prof. Very good question. Yeah, I agree with you. We also have tested with different chemical pretreatment in order to further purify the material. Yes, I think by having this chemical treatment, it is very helpful to further purify the material, but at the same time, it will increase the cost of the production. So it is something off between that. I think it is very successful if we have the impurities that does not needed in the ceramic material. So I think there's not any other alternative way except for do the pretreatment by using the chemical method. But some of the impurities, for example, as I show here, the impurities is not that high. The fly ash and also palm oil ash, the most of the impurities coming from the carbon material, which
Yeah.
this carbon material either we can burn off during the sintering process, which can create the pores on the membrane to make the membrane have a nice pore size distribution, or we can remove them if the carbon content is too much. So, like I mentioned to you, it is really depends on the amount of the impurities. So, if the amount of impurities is too high, so definitely we have to do a pre-treatment chemically. But if the impurities is still acceptable, so we can use this carbon material actually as the pore former for the membrane production.
Yeah, the other
I'm
thing
answering
is,
your question?
yeah, sure. Did you see any relation with purifying the material with improving the porosity percentages? So I notice in the porosity percent in your case is always less than the commercial, highly purified silica or yttria or zirconia method. So
Yes.
does this affect the porosity density or the porosity percent in your?
Yes, exactly. So it is affect the porosity. One of the, I think there are two reasons what become the factor for the porosity. One is because of the impurities present in the material. Another reason is because of the particle size for this low cost material, which is quite big and lead to the less denser packing density of the ceramic membrane. So lead to the lower porosity compared to the pure metal oxide. Agree with you. Prof. So, but like I mentioned, some of the material like clay type, natural occurring material, the pre-treatment is not really necessary. Chemical pre-treatment because these impurities can be used as the sinking material. But some of the material like palm oil fluid ash, fly ash, the impurity is coming from the carbon. So this carbon actually is quite a troublesome if the amount is too high. So therefore, do the chemical treatment, we use some carbon, and some of the carbon is as a conformer in the membrane.
Yeah, thank you, Professor. Thank you, Professor Zaidi.
Thank you for the suggestions.
Thank you, Professor Osman. Thank you.
I would like to thank Professor Hafiz Usman for giving a very informative and nice presentation. And also, I appreciate that he just to mention that he is traveling and he's in transit, so he managed to give this presentation. I really thank you very much and appreciate for coming online and giving presentation. Again, thank you very much. See you, inshallah, in the next conference, next presentation. Now we'll move to the next keynote presentation. There is a small change in the program. Professor Nadeem Khalil, somehow he got some urgent things, so he will be giving presentation in the end at the last presentation. So we will move to the next keynote speaker, who is Professor Navanithan Mani. Professor Mani is working at Nanotechnology Research Center, SRM Institute of Science and Technology in India. He completed his PhD from Shizuoka University in Japan, and his research areas are in thermoelectric materials, devices, gas sensors, and dye-synthesized solar cells, and synthesis of nanostructured powders by thermal ball milling and other solid-state methods. He has published more than 270 research articles, and he is a fellow of JSPS and also fellow of JST CREST fellow. He has won many research awards, including Best Research Paper Award and Best Researcher Award, and he has many other accomplishments to his credit. The title of his talk is Effect Engineering in Layered Nanostructures for Thermoelectric Application. I welcome Professor Mani for giving this talk, and now the floor is yours. Thank you very much.
Thank you, Professor Zaidi. Thank you once again. So, first of all, I would like to thank the organizers for giving me this opportunity to talk about our recent research. And I thank Professor Chaimi for organizing this wonderful event. And so let me move into my today's topic. So due to the bandwidth of this, I will just wanted to mute my video if the chat allows me to mute. So I think, hope you can hear me, right?
Yeah, we can hear. You can do that. No problem.
Yeah. So what actually we are doing is that we are working on the materials for particularly to improve the thermoelectric properties. So our group is very actually working in the layered materials. So before moving into my talk, I just wanted to highlight about where I am from. Basically, I'm from SRM of Science and Technology. It is one of the top universities.
Yeah, your voice is, yes.
Dr. Mani, we can't hear you. Dr. Mani? Dr. Mani, we can't hear you. Dr. Mani?
Mrs. Noor, maybe you should send him a written message.
Part of having the sustainable
Dr. Mami,
Can you hear me?
now we can hear you. Can you repeat from the beginning, please? Because we couldn't hear you from the beginning.
Oh, sorry. So can you hear me now?
Yes, yes, great. Thank you.
Yeah. So sorry for the inconvenience. Actually, I am from SRM Institute of Science and Technology. This is the institute which is situated in the southern part of India, that is called Chennai. And we have 4 campuses across India, and we have more than 50,000 students. And we have 4 faculties like Faculty of Engineering Technology, Medical, and then Arts and Sciences, and Law. So let me move into the research what we are doing at our SRM Institute of Science and Technology, particularly in the energy harvesting area. As we know that the energy demand is increasing globally due to the industrializations. However, these energy productions are main causes for the the global warming and the CO2 productions. So mainly these things comes from the burning fossil fuels. So this makes more amount of CO2 as well as other pollutions to the universe. So if you look at the sharing of these 3, like oil and coal and gas, they are comprises of more than 80% of energy productions, and which is the main problem for the earth. So people are already on the track of going for the alternative energy resources like nuclear or hydro or biomass or even solar. So anyway, if you put forth all these things in terms of accountability, their sharing of energy is less compared to this fossil fuels burning. So we need to really look after. We need to really look after the issues are arising from the global warming due to the energy production. So very recently, people are talk about the hydrogen production or thermoelectric productions or any other clean energy productions. So our group is mainly concentrating on the thermoelectric productions from the layered materials. For example, these thermoelectrics are it's almost we can say the thermoelectric research is not new, but however the addressing the issues in the properties as well as the device are relevantly new. So the energy production from the industry, particularly say about the waste heat from the industries are enormous. So if you look at the statistics, about the 70% of heat is wasted as in the form of waste heat, whereas only 30% are used in for their productions. So if you look at the graph, like figure, like we have the plants like thermal plants or steel plants or automobile industries where the enormous amount of heat is used for their production. So in particularly, if you look at the steel industries, their heat range is lies in the range of 700 degrees to 1000 degree. Now, can you hear me? Is there any problem? Please notify me in the case of any problem in the hearing me. So if you look at the temperature gradient, so Kishore, am I audible?
Yes, 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 we can hear you.
Yeah. So if you look at the temperature gradient, this temperature gradient is the main part which can give us the potential amount of gradient to the material. So just I wanted to highlight few things. For example, if you look at the automobile sectors, so the heat is produced in the heat exchanger. It comes around 300 degrees C. So the room temperature, mid temperature, and high temperature. So these all 3 things can be combined together, and we can use these heats for the source of thermoelectrics. So this is the world carbon emissions by the highly developed countries like US and China and other countries. They share more amount of carbon emissions because of the industry in their country. And if you look at the energy demand, this will grow this century in an enormous way. So that means we are going to face a large amount of problems in the CO2 emissions. So it must be reduced, and the consumption from these coal and oil and natural gas must be lowered. So this clean energy resource like the thermoelectric, so which is potentially used like 2 types of materials, that is the P-type semiconductor and N-type semiconductor. They're connected like parallelly, and then the heat is applied at one end, and the other end we can have the cold temperature. So this temperature again will eventually help us to have the thermopower output. So this is the schematic which shows that the heat flow is flow from the hot junction to cold junctions. So there will be the production of the thermopower. So mainly this thermoelectric materials are defined only based on their thermoelectric figure of merit. So this thermoelectric figure of merit is mainly depend upon the parameters like Seebeck coefficient and electric conductivity and thermal conductivity. So these three parameters are interdependent at the absolute temperature. For example, if we wanted to have a material which can be potentially used for commercialization, then their figure of merit must be over than 1. So this achieving this over than 1 is not easy task as on date. So the figure of merit must be having the higher Seebeck coefficient and high electrical conductivity and low thermal conductivity. So if we could play all these three in one particular way, then we can achieve the high figure of merit. So this high figure of merit materials can be have the high thermoelectric figure of efficiency Q max. So if you look at the length versus combatancy, so the nanostructured thermoelectric materials are like worthwhile having the high efficiency. This is a schematic which clearly tells us how thermoelectric research starts in the early 1950s, where we have the ZT close to like 0.1 or 0.2. But over the period, now the people have achieved the thermoelectric figure of merit over 3, in particularly the tin selenide and other materials. So it is started with the bismuth telluride and lead telluride. Bismuth is the material which can be potentially used for room temperature under the lead telluride. But however, these tellurium counterparts are not so good for the even the environment, as well as they are very expensive, and since they are not available in the earth like other materials. And if you look at the silicon-based nanowires, very recently people have achieved the ZT close to 2 and 3, and they are mainly dominating in the field of Internet of Things applications. So from bulk to nanostructures, we can tune their properties so that we can play with their properties for the betterment of the enhancement in the ZT. So let me talk about the layered materials, particularly these layered materials compared to bulk materials. They have the significance in terms of like we can tune their arrangements so that we can have their defects or inclusions between the van der Waals gap, so that these two properties, like as I noted in the thermal conductivity as well as electrical conductivity, these both are simultaneously played by having this kind of nano inclusions or precipitates or across the modulation doping. So this can greatly lower their thermal conductivity and greatly enhances their electrical conductivity. So there are many layered materials. For example, we have the SNSC as well as the bismuth-based seleniums or tellurides. These are all purely layered materials. So what makes these layered materials so advantageous for the thermoelectrics? As I mentioned, these gaps of the layered materials can be very well played by the nano inclusions or nano precipitates, or at the same time using the dopants. So even we have different kind of layered materials. For example, if you take the graphene, it is in the metallic nature, whereas the boronite is an insulator. So in between, the molybdenum disulfide related materials are showing the semiconducting behavior. So in general, the semiconducting behavior of these materials are highly associated with a high amount of ZT. Because if in the case of metals, so the problem with the thermal conductivity, we cannot have the metal as a thermal material owing to high thermal conductivity, whereas for insulator, it's a problem of the electrical conductivity. So one has to be very cautious about the choosing the materials based on their electrical conductivity as well as thermal conductivity. And if you look at the low dimensions and their layered structures, their carrier packets are highly degenerated, and then the opponent transport also highly significantly controlled by having the small amount of the inclusions. So in our research, mainly we focus on the molybdenum disulfide based materials because of their layered materials nature. So that could give us the reduced latest thermal conductivity, easy and independent tuning of electronics and thermal transport. Whereas the nano size give us the sharp 10-step states, which could increase the Seebeck coefficient and scatter the high energy phonon and increase roughness. The anisotropy, another parameter which can gives us the properties which are associated with their grain boundaries. And we should be very careful about the toxicity of the material. So these all parameters put together, we have chosen this molybdenum disulfide, which is already theoretically proven. It can be give the figure of merit over 3.5. And however, in the case of experimental, so far the achieved ZT from other groups are close to 0.2 or 0.3, like that. So realizing the ZT of 3 it's a long way to go. So we have put our efforts to bring this ZT of MOS to close to 1 or above 1. So these are all the strategies which can potentially useful for the thermoelectric performance enhancement. So for example, the energy filtering. This kind of energy filtering between two interfaces or two different junctions, so we can lower their energy transport between these barrier. For example, the high energy electrons can through at particular size of the grains, whereas the low energy electrons are filtered. So the collecting high energy at the same time and lowering the low energy is main factor by having the energy filtering. And the other point is that all scale hierarchical nanostructures. It means that, for example, we wanted to have a particular phonons to lower the thermal conductivity, because mostly the phonons carries the heat. That they are the reason mainly for the increasing the thermal conductivity. So we can have the different kind of structures in one particular composites, so that we can create the grain boundaries, more number of grain boundaries, and the nanoprecipitates as well as the point effects. So this could potentially lower the thermal conductivity to have the high ZT. And then again, I told you the low dimension nanostructures, because of their split in the density of states and short density of states, will give us the more electrical conductivity and a high Seebeck coefficient. And then the interface engineering. So all these effects can be controlled at the interface of the materials. So what we are doing in our lab is that controlling their interface effect by using low temperature effect, particularly the hydrothermal method, as well as the different kind of materials like polyaniline, P.PSS, and molten dioxide and tungsten dioxide to create the interface and to lower the thermal conductivity and enhance the Seebeck coefficient as well as the electrical conductivity. So these are all the materials which we are targeted, like MOS2 polyaniline, MOS2 RGO P.PSS, and MOS2 MOO3, and MOS2 WO3. So this is the sample preparations. Normally what we do is that we prepare the method like hydrothermal method, and this is the optimized condition. After obtaining this material, we go for the pelletizing using cold press as well as hot press. So in this case, we have used the cold press technique, and we fabricate the like pellets in the form of disc as well as the rectangular shape, so that we can measure the thermal conductivity and the coefficient. And in this particular work, so we have achieved the 2H-MOS2, and the material is formed in a CCB discard well matched. And this particular work is the MOS2 PANI. So in this case, we have created the MOS2 and PANI interface at different amount of PANI incorporated into MOS2. So we could see that this amount of PANI is purely incorporated into the MOS2. So, for example, 0.5%, 0.2, like 2.58%, and 58%, 10.8%. So, this peak at the XRD, we can clearly shows that there is a shift and that there is an interface happen between the MOS2 and PANI. So these are all the confirmation of the incorporation of PANI into the MOS2. For example, in the case of TM, we can clearly see that this PANI is highly incorporated into the MOS2 layers. So this lattice spaces confirms the formation of MOS2 and PANI. So this the XPS spectra very clearly tells us that the 5-8% of PANI is clearly has the peak for the nitrogen as well as the sulfur and N1S peaks also.
Sorry for that interruption. Dr. Mani has a problem with the connection, but he's connecting now. Sorry for the delay. Dr. Mani is here again. Dr. Mani, can you hear us? Dr. Mani, we can't hear you. Can you unmute yourself? Dr. Mani? due the problem of connection with Dr. Mani, we will present a poster for 10 minutes, and we will proceed with our normal schedule with Dr. Olga.
Yes. Thank you, Professor Mani, for your nice presentation. Now we have time for a few questions. If somebody have. Okay. Okay, since he's, I don't see him, I think there's some problem. So now we will move to the next presentation, which is by Dr. Olga Gusalinkova. Now, Dr. Olga Gusalinkova obtained her PhD in 2019 from Tomsk Polytechnic University, Russian Federation, and the University of Chemistry and Technology, Prague, Czech Republic. She is currently a JSPS Fellow at the National Institute for Materials Science in Tsukuba, Japan. Her main scientific interests are surface modification using diazonium and iodoxonium salts, the design of source sensing, and new plasmon-assisted reaction for polymer science and organic chemistry. The title of her presentation is Surface Enhanced Raman Spectroscopy Sensing System for Water Safety Monitoring. We welcome Dr. Olga. Now, floor is yours.
Good afternoon.
Dr. Olga, can you hear us?
Yes, I can hear you. Can you hear me?
Yes, yes, we can hear you. Welcome, Dr. Olga.
Okay, great. Yeah, good afternoon to everyone. Today I will present some overall results during the last year, which I obtained in Russia, Czech Republic, and some recent results from Japan. In general, the widespread problem of water pollution is jeopardizing our health. And unsafe water actually kills more people than all other forms of violence. So, if you know now, our drinkable water resource is quite limited. Only about 1% of the fresh water is actually accessible to us. Because water is known as, let's say, universal solvent, it's able to dissolve more and more substances than other liquid on the earth. Therefore, it also can solubilize a lot of contaminants. So the most common contaminants now are considered as agricultural, such as pesticides, different drugs, oils, some radioactive compounds, and also recent hazard become microplastic. And actually all these pollutants affect on both on environment and on the person through the environment, because if there is a huge contamination of water, it can create kind of dead zone for living creatures, and in this place there is a deficiency in the oxygen, which leads to the death of all these creatures. And simultaneously, when some fishes and cows and other animals are consuming these pollutants, after we also eat it with meat and fish. So, okay, so let's move. So therefore, we have to be very serious with water monitoring. Nowadays, the diversity of metal exists, and all of them have some advantages and disadvantages. Like, for example, chromatographical method can be considered as one of the most precise, but usually they are very expensive and not accessible. And nowadays, portable chromatographs are quite uncommon. On the opposite side, for example, electrochemical monitoring systems are quite cheap, but it's very difficult to differentiate between different target analytes. And as an alternative today, I would like to present you some plasmonic devices. Plasmonic devices usually are based on the noble metal nanostructures, which are able to interact with light. And there are two types of optical plasmonic-based sensor. The first one is SPR. SPI technique is actually optical method which is responsible to the changes of refractive index near the structure. And the second method is SERS, or surface enhanced Raman spectroscopy. This is when the signal from the analyte is multiply enhanced by the structure, and theoretically even you can detect one molecule. The main difference here is that in case of SPR you can only monitor the relative changes, but in case of surface enhanced Raman spectroscopy you can have the spectra which is presenting the special shape for each molecule. So let's discuss advantages of surface enhanced Raman spectroscopy for water analysis in detail. The first one, as I told before, is that actually each molecule has their own spectra, which can be considered as a fingerprint of each molecule, and the unique combination of peaks can be used to recognize molecule. The second one, that it's actually applicable for almost all kind of organic and inorganic molecules. You just have to do the appropriate design of your surface. The next big advantage is actually high sensitivity. In 1997, for the first time, it was shown that it's possible to detect even one molecule. The next advantage is short time of analysis. While, for example, some spectroscopic method can take minutes and hours, and quite often you need a very long pretreatment procedure, the analysis time for Raman spectroscopy is about minutes. The next feature is applicability in a portable Raman spectrometer, because quite often you need to monitor the water quality on the place, and you cannot bring your device, huge device with you. And in this case, portable systems are quite useful. And one of the last advantages is the possibility of remote analysis. In case you're using a plasmonic optical fiber, it's possible to do remote detection of some contaminants in water, but actually also in air and some other system. However, as I told you before, that all methods have their own advantages and disadvantages, and SERS is not an exclusion from this. The limitations are quite significant. The first one is selectivity. As I told you before, SERS is really ultra-sensitive method, but this thing also bring to us some disadvantages, like any molecule which is coming to the surface of plasmonic sensor also will be enhanced. It means that if some matrix molecules are also coming to the contact with plasmonic surface, we also will get some spectra from this molecule. The next disadvantage is stability, because for SERS sensing system, mostly we use some noble metals such as gold, silver. Recently, more popular become aluminium, copper. These metals quite often are tended to the oxidation, and if the surface of this sensor is oxidized, you are losing sensitivity of your sensor. The next disadvantage is reproducibility, because enhancement usually occurs in the place between the contact between two or more plasmonic nanoparticles. Therefore, depending on the formation of agglomerate, you can have different spectra. And this is quite considerable for the precise detection to have good reproducibility. And one of the biggest challenges in the water monitoring system based on SERS is the possibility to use this sensor without any pretreatment, using real samples which are normally consist on our target molecule or pollutant which we would like to detect, but also possible that you have some biomolecules like proteins, bacteria, and other living organisms, and you can have some micro contaminants like soil, sand, microplastic. And as I told you before, the selectivity is the issue. So the signal will be enhanced from each component of your sample. Therefore, in order to bring SERS to the next level of applicability, you have to solve all of these challenges. And during maybe last 5 years, I'm trying to solve this. So our kind of concept, which I was using, is you have some plasmonic active substrate, which is being the source of the SERS signal. You have some linker, which is connecting your plasmonic surface with the recognition unit. Recognition unit here is established to capture the target analyte from the water or some other matrix. So as a source of signal, I was using kind of 2D substrates, kind of gratings, I will show you later, or some nanoparticles. As a linker, I'm using commonly diazonium or iodonium chemistry. And this linker not only bring you connection to the recognition unit, but also quite often can help in protection against oxidation. And the last part is recognition unit, which is usually presented by some ligand or receptor. And this part is designed to selectively capture the molecule. And also by capturing, you can do pre-concentration of your analyte near the plasmonic surface, which is increasing the signal. So as I told you before, one of our commonly used substrate is plasmonic grating, which is prepared by laser patterning using photoresponsive polymer SU8 with the following deposition of the metal by sputtering to this pattern. So using these kind of gratings, I think created more than 15 different sensors for different analytes such as heavy metal, other dyes, biomolecules, pesticides, drugs. For example, in case you have some aliphatic functional groups on the surface, you also can capture some cholesterol-like molecules. If you have on the surface porous metal-organic framework, you can capture some hazardous pesticides. If you have some chelator ligand on the surface, you can capture some metal ions. If you have some responsive polymer, you also can capture in controllable way some dyes. And in the next part, I will present just a few examples of our work from this list, but if you would like to know in detail, please just follow some of these references. So one example is utilization of the surface chemistry for the deposition of metal organic framework. In this case, I was using gold gratings, which I explained before how we prepared. And we deposited some diazonium salt containing carboxy moieties. And these carboxy moieties actually served as engine groups in order to grow 3D structure of metal organic framework. Our target molecule were phosphorus containing organopesticides with actually maximum allowable level is about 10 to minus 2 milligram per liter in the food or soil. So we use this kind of 3D porous structure to capture these pesticides from the water and detect them. So as you can see, two different molecules have their own peak, and for each molecule you can choose a characteristic peak and to plot the dependency between the concentration and intensity. In this manner, we found that the limit of detection for both pesticide was about 10 to minus 14 mole per liter, which is much more lower than the maximum allowable concentration. So using our sensor, you can safely detect these pesticides. However, it were only model solution. And as I told before, the real challenge is to analyze some real sample. And here I bring the example of analysis of water which was obtained from soil. So the soil with our target pesticide and some other contaminants was mixed, and after it was extracted in order to obtain the supernatant liquid, which were later analyzed by our plasmonic sensor. And as a result, we show that we could analyze at least 10 to minus 10 molar concentration of the pyroxene, and we can clearly see the peaks of this contaminant. As I told you before, the reproducibility is one of the key challenges in cell sensing. And here we showed that on the one sensor, the signal is highly reproducible. And also, if you prepare different samples independently, the deviation does not exceed 5%, which is a really good result because the acceptable level of deviation is 10% for Raman, but we are still trying to decrease it as much as possible. The next example is detection of some chiral amines. Amines and amino group related compounds are also quite common contaminants which are associated with the risk with some aquatic creatures. But you have to know that sometimes amine can be chiral. It means that there are two enantiomers, and quite often one amine is more toxic than other one, or one is completely non-toxic and the other one is toxic. Therefore, you want to detect not only the structure of amine, but also you can detect the chirality using surface enhanced Raman spectroscopy. So in this case, we also try to simplify the detection system to be applicable for real samples. Therefore, we suggested a two-stage detection procedure. Firstly, you can evaluate the the presence of the amine and chirality by wettability measurement. And after, you can use surface enhanced Raman spectroscopy using portable Raman equipment, the concentration. Oh, probably I did not explain you some chemistry. So in this case, I also was using in the beginning some diazonium to attach amino groups. And after these amino groups was coupled with tartaric acid by EDC NHase coupling. And as a result, you have these chiral carboxy groups, which later can interact with other amine and forming some charged intermediate. So actually, tartaric acid is one of the most common chemical compounds which can differently interact with two enantiomers of amine, forming two different salts. And in one case, you have a crystal of this, and in another case, if the chirality is not matching, there is no crystallization. So our target molecule here was L-DOPA, which is kind of drug, but it also can be can be presented in water. And firstly, you can see that if the chirality of the surface and of the chiral amine coincidence, you can see the changes in the water contact angle. But if the chirality of amine and surface are different, you don't see any interaction. And here the big advantage was utilization of not only like professional goniometer, but also we use some mobile application, which can tell you the water contact angle quite precisely comparable with professional goniometer. And on the second stage, after this drop of the analyte was dried, you can actually analyze the chemical state on your surface. So you can see that there are some typical peaks for this amine. And in the similar way, we found the characteristic peak appeared after interaction with this chiral amine. And we could plot the dependence between the concentration and intensity of peak. In order to show better applicability, we also demonstrated that we can analyze not only separate one enantiomer, but we also can analyze the mixture of two different enantiomers. So the next example is maybe even more useful for the water analysis, because the detection of trace amount of some pharmaceutical actually represent real changes in the environment protection. So the task was here quite complicated, because the low concentration of pharmaceutical can go to the water by the washing out from the human being. So here we present the approach for the inline flow extraction procedure and source measurement, which we did in the microfluidic regime. And as an example of the drug which can be detected in water, we use ibuprofen. And in this case, as a surface-enhanced Raman spectroscopy active tags, we use gold nanostars, which were modified by lipophilic diazonium salts. And as a result, we had some alkyl groups on the surface, which is facilitating the extraction of ibuprofen from the water using organic solvent. So after microfluidic extraction, ibuprofen was captured by these nanoparticles on the surface, and the source measurement was performed in the online way. So we performed microfluidic extraction and source detection of ibuprofen, firstly using some model solution in different concentration up to 10 to minus 8 molar per liter. And we can show that we actually can differentiate between different concentrations. Later, we again started to evaluate the reproducibility of our method as one of the key challenges. And here we showed that for 3 different concentration, the deviation between independent measurement in one chip and between different chips or sensor was quite homogeneous, and deviation did not exceed 4%. And the next advantage is the possibility to recycle the sensor. So here you can see that the sensor was recycled 3 times using dichloromethane to dissolve all ibuprofen, and different concentration one by one can be easily detected. And the last thing is the testing of the real condition. In this case, we used different additives. The first one is sodium chloride, because normally wastewater have some salinity. Also, we try to add BSA, which is a model protein. And the last one, we also try to do pH variation. As you can see, in case of addition of salt, it was quite big decrease in the intensity because of agglomeration of nanoparticles in the presence of salt. So unfortunately, our sensor was not well applicable in water with some salinity. However, in case of presence of some model proteins like BSA, actually the decrease in intensity was negligible, about 2%. And the last one is variation of pH. As you can see, in extremely high pH, the intensity significantly drop. This is because ibuprofen contains some carboxy group, which can be charged and discharged by pH difference. However, in case of acidic pH, we still have quite a high intensity of signal. And yeah, as the last advantage, we just show the applicability of our sensor to some other drugs. So as I told before, by utilization of this strategy, we could solve the selectivity of interaction, the stability by diazonium modification, and reproducibility. But as you can see, quite often in the attempting of analyzing real samples, we fail sometimes. Therefore, we decided that we have to develop some alternative strategy in order to become possible analysis of the real samples. And as a solution, we suggested to use some porous plasmonic materials as a source of the Raman signal. This structure was suggested by Professor Meucci from Japan in 2015, and later we adapted it for some advanced self sensing. So the challenge of the detecting small molecules in the presence of matrix is quite serious, because in addition to selectivity issue, you could have the poisoning of the sensor, which is leading to oxidation, and this is associated with suppressed sensitivity because enhancement is already not so strong and the signal is suppressed. And also you could have overlapping of the signals, and this can give the mistake in the analysis of structure. So how can help these porous materials? The first one, that the porous structure actually can serve as a filter for large molecules, because you can adjust the pore size to a few nanometers, and it means that large biomolecules cannot penetrate inside these pores, and only small molecules can penetrate and be enhanced from the plasmonic porous surface. The next one is facilitates the transport of these gas molecules, and it also means that you can pre-concentrate your target analyte inside the pores. And the next one is increased number of interaction between plasmonic surface, molecule, and Raman laser. And it means that the enhancement is usually the Raman enhancement is usually increased compared to non-porous analogs. So one of the first examples I would like to show is the detection of some tiles in the presence of living system. In this case, as a base, I used mesoporous gold film, which is actually quite solid. But the enhancement of this gold can be intermediate, and it's well known that silver is actually even more self-active than gold. Therefore, I suggested to deposit some silver nanoparticles on the mesoporous gold in order to enhance the sensitivity of sensor. And after this, we tried to detect some tiles in the presence of multi-component sample containing different matrix, and small molecules should penetrate and should be captured by the actually silver, and large molecules should be filtered. And also we suggested the recycling procedure, because silver also can be poisoned by all these components of real samples, but silver is relatively cheap compared to the gold. Therefore, we can just easily just dissolve the silver and have our initial gold surface as it is. And after we can repeat the deposition of silver particles, detection, and so on. So here I showed the detection of benzothiophenol in the presence of some living cells, which also can be met in the water. And in the similar way as I explained before, you can choose some characteristic peaks as a marker peaks of this molecule and to plot the dependence between the concentration and intensity. So here I confirmed that the presence of some living organism in the probe almost did not affect the dependence between the intensity and concentration. It means that our strategy was successful, and the large biomolecules of living cells were filtered and did not penetrate inside. As a result, I showed that the limit of detection 10 to minus 10 molar per liter, and for real sample it was the same. So we found that the major binding site from these tiles was silver, and it means that, as I told before, silver can be dissolved and removed with the tiles, and the gold surface can be recycled. So here we realized the cycling procedure, and we showed that up to 10 cycles of of the detection we can perform without the loss of the sensitivity. And during this cycling, we also measured the reproducibility in sensing, which did not exceed 2%. The next example of the utilizing porous plasmonic materials process is the deposition again of the metal organic framework, which have quite good functionality on the mesoporous film. And as a result, we can detect pseudoephedrine, which is a drug, and this is also a precursor for amphetamine. Therefore, there is a challenge in the detection of these molecules in water and also possible in some other biometrics. So here I used the strategy similar to explained in the beginning with ratings, but as a base I took mesoporous gold. After I modified it with carboxy groups, which become an entering group for the growth of metal organic framework. And in this case, I deposited metal organic framework containing also chiral ligand. So as a result, again, we can detect not only the chemical structure of this drug, but also we can differentiate between two different chirality. So as a result, we have mesoporous of the gold and also nanoporous of the deposited morph. Yes, so in a similar way I explained before, if the chirality of the ligand in the morph is coincident with the chirality of molecule, you have successful detection of your analyte. But if chirality is different, then there is no interaction. So in this way, we showed that the limit of detection for this drug in water was about 10 to minus 14 molar per liter. However, more interesting was analyzing how exactly the architecture of such substrate is affecting the performance of the cell sensor. So therefore, I compared the analytical performance of my substrate with gold without morph, and also with grating, which actually doesn't have this porous structure. So as a result, we can see that if we compare our final sensor with just gold, the sensitivity almost decreased twice. And if you have the same morph but on gold plating, the sensitivity decreased to 40%. It means that both the porous structure of gold and porous structure of morph both are affecting the performance. And finally, we compared actually the analytical performance of our cell sensor with the common method of gas chromatography, which is actually more expensive, however, normally considered as more precise. And in up to minus 10 to minus 20 molar per liter concentration, we showed that our cell sensor performs in the similar way as a reference method of gas chromatography. And of course, as an important point, again, we show the reproducibility of detection. So on the one sample, the deviation did not exceed 5%. And when we prepared 5 different samples independently, the reproducibility sample to sample was even higher with a deviation about 2%. And one of my last project I'm performing in Japan is actually the detection of microplastic in the water solution using this porous plasmonic material. In this case, as a base, I chose commercially available silver microporous 3D substrate. I deposited some mesoporous silver, and after I deposited some lipophilic functional groups using diazonium chemistry. And this substrate was applied for the detection of microplastic, because microplastic become one of the most common pollutant in our world. So you have it already not only in water, but also in some sea creatures and so on, and after we consume it, because recently microplastic was found even in the blood of the humans. So in this design, the mesoporous silver provided additional contact between microplastic and the surface, and also provided additional Raman enhancement. The organic layer actually improved the homogeneity of the substrate and also improved the affinity of the microplastic to the surface. So as a result, you can see this is initial structure of silver form. Here is a mesopores. And after you have these functional groups. So as a result, our substrate was super hydrophobic because of mesopores and also lipophilic functional groups, which is facilitated the contact with hydrophobic microplastic. Here we showed the enhancement of the Raman signal using developed substrate, and we showed that our organic coating is actually protecting the highly active silver surface from oxidation. Here you can see the signal from modified silver, and here the green one, you can see the signal from unmodified silver. So for the deposition of microplastic, I tried to simulate kind of a flow mode. I placed my sample in the cell, and I was penetrating the flow for 10 minutes, and microplastic was deposited inside the pores. So here you can see 5 types of microplastic I have tested, which is polystyrene, polyethylene, Teflon, PMMA, and nylon. This is 5 of the most common microplastic which you can meet in the water samples. So firstly, I determined the relative adsorption capacity on each stage of modification. So as you can see, as received silver form is not so adsorptive, but when you change the morphology to the mesoporous, you can see the improvement. And if you deposit some hydrophobic group, you can see that adsorption capacity is increasing. Here, I also deposited some hydrophilic functional groups for comparison to show that if the surface become hydrophilic, the contact between surface and microplastic is already not so strong. Oh, sorry, it was some way. So here I showed the detection of 5 different types of microplastic with different enhancement factor. But as you can guess, in real samples, there are more than one microplastic possibly present in the water. Therefore, the signals can overlap. And in this case, it's already not so easy to differentiate between different kind of microplastic. As a solution, we are suggesting to use some artificial neural network which can do the multi-level task better than our human eyes. Actually, artificial neural network is kind of special mathematical post-processing system that can find some similarities in the different cell spectra, and after it is trained to understand what do you have on your cell spectra. Here we have the task of multi-level classification. It means that here we have 5 types of plastic, but the real composition can be 3 or 2 different microplastic, and this neural network should say you the probability of the presence of microplastic in water. For this, I measured about 5,000 spectra for the training. After we perform the training of this neural network, and after when you give the unknown spectra, it should tell you which plastic you could have in your sample. So in case of you have only one type of plastic, the analysis is quite easy. So here you can see the map. The closer dots between each other, it means that more similar spectra between each other. So in case of presence of one plastic, you have almost 100% accuracy. However, if you have already mixture of 2 microplastics, the situation becomes more difficult. However, even in this case, the neural network can say you the presence about microplastic with 98% accuracy. So as a result, we tested different mixtures of microplastic, and almost in all cases we got 98% of accuracy for the detection. So to sum up, I would like to briefly overview our result that we prepared about 15 different sensors for common contaminants with improved sensitivity, selectivity, and reproducibility using the gold ratings or nanoparticles, but it was difficult to analyze real multi-component samples with matrix. And now we are trying to move to some porous plasmonic material, because this material can allow us to filter some large biomolecules, and matrix can allow to do pre-concentration inside the pores. But we come to the thing that we anyway have to do some post-processing for the multi-component samples, because the detection of multi-component samples with naked eye become almost impossible. And I just would like to mention some recent trends in the SERS. Like, if to be fast, just the main thing that the SERS systems should be simplified, and we should work more on the analysis of real sample rather than creating new plasmonic surfaces. And I would like to thank you all my collaborators from Japan, Russia, and Czech Republic, and thank you for your attention.
Okay, thank you, Dr. Olga, for your nice presentation about the sensors and application for the nanomaterials. Now we have time for one question, if there are any. We are already running out of time. So.
Hello.
Yes, yes.
Okay, Professor Mohammed.
Can I ask a question?
Yeah, sure.
Hello.
Yes, we can hear you. Yeah.
Hello.
Yes, yes.
We can hear you.
We can hear. Yes, hello. Yeah, Professor Shahimi, we can hear you.
Oh, okay. Thank you very much. Okay. Thank you all, guys. It's a very nice presentation on on SERS application for the detection of pollutants. I have the very last slides are really very good about ANN application to discriminate which kind of plastics, micro plastics. I have a question. Once you have detected the pollutants, the plastic pollutants or microplastics, what is next? Next is, okay, you have adsorbents, porous materials, you collect the plastics, and then you should, what is the intention? Is to collect the plastics or to degrade the plastics?
So the first intention in terms of sensor also to show applicability also for some real samples, because now we are only on stage of model mixtures, but these substrates also can be used for the simultaneous detection and degradation, because plasmon active materials are able not only to be a sensor, but they also can be catalysts for degradation. This is one way, or we can do simultaneously recycling of polymer waste to some organic molecules using the same substrates.
Okay. Okay, so this is a dual functional material. Okay, thank you. Do I have time for another question? Hello?
Right.
Yeah, you have shown that you recover the sensing systems with dichloromethane. Is there any other way to replace dichloromethane? Is it possible to change the solvent?
I use dichloromethane because this molecule, like actually it's possible to use, for example, ethanol or some organic solvent which can dissolve ibuprofen. Just impossible to dissolve with water, but yes, possible.
Okay, yeah, this is an issue. Okay, thank you very much, Olga. Thank you.
Thank you for your time.
Okay, again, thank you very much, Dr. Olga, for your nice presentation. It's very informative. Thanks for your time and coming for this conference. Okay, thank you very much.
Thank you.
Now we have a next presentation is in the program by Professor Nadeem Khalil from Aligarh Muslim University, India. And due to some technical problems, some urgent issues, he will not be able to present himself, but his presentation will be delivered by Halima Salim. Halima, can you, are you there?
Hello.
Yeah,
Can you
okay.
hear me, Professor?
Go ahead,
Yes.
yeah.
Assalamu alaikum and a very good morning to all of you. Myself, Halima Salim. I'm working as a research assistant with the UNESCO Chair, Professor Syed Javed Saidi. And today I'm going to take a presentation on nature-based solutions for wastewater treatment, a sustainable approach. And this presentation I'm taking on behalf of Professor Nadeem Khalil, professor from the Department of Civil Engineering, Aligarh Muslim University, India. As he had some urgency, he is not available to take the presentation, so I'm taking it on his behalf. I'm going through the slides prepared by Professor Nadeem Khalil. Let's check the first slide. Yeah, as you all know, wastewater is actually discarded water after the household, industrial, and agricultural usage. Proper treatment of wastewater is extremely necessary because this wastewater can definitely cause harm to human beings as well as the surroundings. So proper management and treatment of wastewater is extremely important. There are actually two nature-based solutions for wastewater treatment that includes water-based systems and substrate-based systems. Water-based systems include ponds, in-stream restoration, surface flow wetlands, and ponics technologies, whereas the substrate-based systems include soil infiltration systems, building-based systems, zero discharge systems, subsurface flow wetlands, and sludge treatment reed beds. Yeah, so these are the different nature-based solutions, and in some cases we can combine these water-based and the substrate-based systems, and it is known as the hybrid multi-stage systems, which will be more effective as compared to the individual systems. Yeah. Now let's check what is actually a constructed wetlands. This constructed wetland has proven to be the best low-cost and sustainable solution for the wastewater treatment. It is nothing but artificially designed and constructed system which will act as a secondary treatment facilities for household and municipal or biodegradable industrial water. So this has already proven to be the best sustainable technology for the wastewater treatment, and it can also provide as a tertiary treatment system for polishing the water before safe disposal or reuse of the water. The main outflows of the constructed wetlands are groundwater recharge, fertigation, and aquaculture. And also there are three different types of constructed wetlands, and these are horizontal type, vertical type, and free surface type, and these are classified as per the water flow regime. And in some cases, there are also the combined flow regimes known as hybrid constructed wetland. And this is considered to be the best effective out of the different wetland because it can combine the advantages of different systems. So out of the different system, the combined has proven to be the best one. Now let's check more about the constructed wetlands. As you can see from this figure, this is a picture of on-site or semi-centralized treatment system. Here you can see the water from low flush toilet, shower, kitchen sink, etc. is fed to the primary treatment system, and from that the water is treated and it is fed to the constructed wetland where the vegetation is there. It can be the water can be either in horizontal direction flow or vertical direction flow, and then after this the water enters the inspection chamber and finally to the groundwater recharge. You can also see a few pictures of the septic tank where the wastewater is collected, and the horizontal vertical free surface or a combined type of constructed wetland picture is also there. And finally this water obtained from this constructed wetland can be used for irrigation or aquaculture. Yeah, so let's see the hybrid constructed wetland, how it can serve a community. The constructed wetlands can also act as a very effective treatment system for communities, villages, townships, etc. It can protect the coastal waters from pollution. It can also protect the health of local residents, and also it will enable the reuse of treated wastewater for irrigation. You can also see a picture where we can see the wastewater collected in a septic tank and it is transferred through a small bore sewer system and to a hybrid constructed wetland where it includes two constructed wetland types, that is the vertical flow type, that is bed 1, and the horizontal flow type, which is the bed 2. So after proper treatment, the treated effluent can be either reused, it can be either recirculated or disposed. It's optional. So this is how the flow of wastewater happens in a particular constructed wetland type. And here in the next slide, you can see the grey water treatment in urban areas. As you know, this grey water is nothing but water from kitchen use and water from like other household uses like washing machines and all. So these constructed wetlands can be embedded nicely in urban areas that produces water for irrigation or recharge. You can see a figure here. It is actually the latest generation of constructed wetlands for cold climate with integrated aerobic biofilter used in Norway. So you can see from this picture, the water from the septic tank is taken to a constructed wetland. Here it is the horizontal subsurface constructed wetland where it is integrated with the aerobic biofilter with domes. So this is used in Norway as the constructed wetland. Now let's check more details about the horizontal and the vertical flow constructed wetland types. The first one is the horizontal type. As you can see from this picture, the flow of water takes place in the horizontal direction. Yeah, and then large gravel and sand-filled channels are provided for the filtration application and planted with the aquatic vegetation also. The wastewater flows horizontally through the channel. Mainly, it's the anaerobic conditions are required, and the filter material filters out particles and microorganisms degrade the organic matter. So this is the details of horizontal flow. Now let's check more about the vertical flow constructed wetland type. Here you can see from the figure, the water flows in a vertical direction, and gravel and sand filters are there for the filtration purpose, and an intermittent appliance of wastewater over the whole filter surface and higher oxygen injection is needed here. And also wastewater drains vertically through the filter layer towards the drainage system at the bottom. So water is finally collected through the drainage pipes. Now, this is the hybrid type. As I mentioned before, it's a combination of the vertical flow and the horizontal flow constructed wetland, and it can offer more benefits as compared to the individual types because it can combine the benefits of both vertical and the horizontal ones. Horizontal flow provides denitrification, whereas the vertical flow provides the nitrification. Obviously, the advantages of both systems can be combined. As you can see from this figure, it's a prototype of an integrated black water system. Here, upflow anaerobic sludge blanket will be there, and it is followed by a hybrid flow, which is a vertical and then a horizontal flow wetland. Now let's see the pollution removal efficiency of this constructed wetland. For horizontal constructed wetland, high reduction in BOD, suspended solids and pathogens. Also, it provides mainly denitrification. Whereas in vertical constructed wetland, a high reduction in BOD happens. Also, suspended solids and pathogens also will be reduced. It also provides mainly nitrification. Now, the next type is the free surface constructed wetland, where high removals of suspended solids happen and moderate removal of pathogens, nutrients, and other pollutants such as heavy metals happens. The last one is the hybrid constructed wetland, and as I mentioned before, it has increased performance due to the combination of different methods, different technologies. And let's check some more details about the constructed wetland. It can provide adequate handling of wastewater, and also it can minimize health risk caused by pathogens, and it avoids contamination of the environment by the untreated wastewater. Also, the constructed wetland can cause high risk of infection if contact with the liquid filter influent or the settled sludge in the pre-treatment facility. There will be a low risk of mosquito breeding. Also, settled sludge must be disposed safely as well as correctly. Also, correct handling of treated water can be used for irrigation. Now let's check the applicability of the constructed wetland. It can act as a secondary or tertiary treatment process for black, brown, and gray water. Black water is mainly the water from the flush toilet, and brown and gray water is mainly from the kitchen sinks and other household household water, like the water from the washing machines and all. Adequate strategy if land is no limiting factor. Constructed wetlands are natural systems and do not require electrical energy or chemicals. It's best suited for warm climates, but can be designed to tolerate even freezing periods. Constructed wetlands can also be combined with many other techniques such as aquaculture, irrigation, and several treatment options. Now let's check the advantages and disadvantages of constructed wetlands. First is the advantage. The first one is simple operation and maintenance due to high process stability, and no chemicals are required in this process, and it is very easy to construct as well as operate, and it can be built and repaired with locally available materials, and it is using the natural process only, and it is very efficient to remove suspended and dissolved organic matter, nutrients and pathogens, and also it will address the sustainable goals. The main drawbacks include it is the requirement of permanent land, and it requires expert design as well as supervision, and pre-treatment is needed for preventing the clogging. Now let's check about the swings. It's actually a collaborative project funded by the European Union FP7 program and the Department of Science and Technology of the Government of India. And the main objective of this project is to offer low cost and sustainable technology for the wastewater treatment and reuse in rural areas of India. And here we can see a few partners of swings. There are several European partners from Spain, Denmark, Slovenia, Germany, and France. And the main Indian partners include AMU, UPJN, Kalyani, ANN, IGNTU, UPP, CBE, and RV. So these are the partners of Swings. And as I said before, the main objective of the Swings is to develop low-cost and sustainable technologies for municipal wastewater treatment and reuse, while minimizing the energy demand as a treatment option for rural and energy-scarce towns in India. So here are the location of major Swings sites in India. You can see here the Aligarh Muslim University, the Indira Gandhi National Tribal University in Madhya Pradesh, and Kalyani University in West Bengal. These are the major locations of Swings sites. And this, you can see a picture of pilot site of this AMU site, where the vertical flow bed and the horizontal flow beds are included. The UASB, the primary treatment is included. The sludge drying beds are there. The solar-driven disinfection units are also seen. So this is the pilot site in AMU India. And here you can see the different technologies adopted in different sites of Swings. So mainly the primary treatment adopted is upflow anaerobic sludge blanket, that is the UASB anaerobic digester. And the secondary treatment includes these constructive wetlands, which are the French type constructive wetland, vertical type, and the horizontal type. And the last step, which is the disinfection. And the major technologies used for the disinfection are pre-filtration and solar UV disinfection, solar anodic oxidation, disinfection pond, and bank filtration. And let's check the treatment chain in different universities. In the Aligarh Muslim University, it is UASB, which is the upflow anaerobic sludge blanket, in combination with the vertical flow type, the horizontal flow constructed wetland type, and then finally the pre-filtration and the solar disinfection. And also French type wetland system is included in AMU. Then comes the main treatment chain in Indira Gandhi National Tribal University. Here, the constructed wetland used is the French type, and following the secondary treatment, the disinfection technology used is solar anodic oxidation. Then in Kalyani University, they are using bank filtration and solar anodic oxidation disinfection for the wastewater treatment. Now let us check the treatment schemes at the AMU pilot plant. As you can see from this figure, this is the first picture is the wastewater or raw sewage collected, and then it is fed to the anaerobic digester, which is the UASB, and the treatment happens, and then it is fed to the vertical flow constructed wetland, and then to the horizontal flow wetland, and finally to the disinfection step, that is the solar driven disinfection system. So a few pictures also you can see the vertical type and the horizontal type constructed wetland. And also from this analysis, we can see that the BOD, COD, TSS, all the contents, the contaminant levels are significantly reduced after the treatment process. This is actually the French type constructed wetland system at AMU site. You can see the picture, the raw sewage is there, the picture of the French type vertical flow, then comes the horizontal flow constructed wetland, and finally the aquaculture pond. And this is the image of a vertical subsurface flow constructed wetlands. And here is the horizontal subsurface flow wetlands. And this is the solar-driven disinfection system in Aligarh Muslim University. Also from this figure, we can see the concentration levels of COD, BOD, TSS, and TKN. Here we can see during the inlet stage, it is having a very higher levels of contamination. And after proper treatments in UASB and vertical flow and horizontal flow, the contaminant level has reduced drastically. So it has definitely proven to be an effective system for the wastewater treatment. Here, from this figure, you can see the concentration level of COD, BOD, and TSS also reduced considerably in bed 1, bed 2, and bed 3. From this figure, you can see the content of total coliforms has decreased considerably in the constructed wetland effluent, and further treatment in the anodic oxidation disinfection, it has reduced to a very minute level. So it has proven to be the best treatment technology for the wastewater treatment. Here we can see the major scientific achievements and research outcomes of the SWINGS project. With this project, already one patent has been applied, and there are 10 publications in internal journals and 11 publications in conferences. Also, one book chapter is there, and 3 PhDs which is already awarded, and 3 PhDs which is in progress, and also there are 7 MTech thesis going currently, and also several junior research fellow and senior research fellows involved. And also there is an establishment, a single lab was also established for this water treatment project. This is actually the animated view of sewage water treatment plant based on wetlands technology for a large housing complex. So far, to summarize, we can note that this constructed wetlands has proven to be the best sustainable and low-cost treatment technology for countries like India. So this is all about my presentation. For any further questions about this constructed wetland, you can also email to Professor Nadine Khalil at nkhalil.cv@amu.ac.in. Thank you so much for your patience and kind attention. Thank you.
Okay, thank you, Halima, for presenting the Professor Nadine's presentation. For any questions, can be directed to his email address given on this slide. Okay, thank you again. Now we'll move to the second part of the session, and it will be moderated by Dr. Muhammad Hassan.
Thank you, Professor Zaidi.
Dr. Hassan, are you there?
Yes, Dr. Zaidi, can you hear me? Hello, can you hear me, Dr. Zaidi?
Yes, yes, we can hear you.
Yes. Thank you, Professor Zaidi, and hello, everyone. I will be glad to continue this morning session. My name is Muhammad Hassan from the Center for Advanced Materials. So our next presentation is with Professor Mina Lad. She is a professor at the physics, and she is also the head physics department and the head of the Department of Applied Sciences at the Symbiosis Institute of Technology, Pune, India. She has more than 25 years of teaching and research experience, and published many articles and book chapters and books as well in internationally renowned journals with many internationally renowned publishers. She is also the recipient of the DUO India Professor Fellowship 2020. Also, Professor Lad is in the editorial of many international journals, and also she heads many of the international initiatives at her institute. Professor Mina, please, the floor is yours. His talk is about the waste management strategies. Professor Mina, welcome to Qatar University, and we are glad to have you with us. Go ahead, please.
Thank you so much. I just share my video. Thank you for such a warm introduction. Let me please share. Is it visible to all?
Yes. Yes, please go ahead.
So good morning, everybody. I don't know, I think it's afternoon in Qatar, and I'm very, very happy that I have wonderful friends in Qatar university, and 3 of my research scholars have recently worked in Center for Advanced Material, a great work which is being going on there in the supervision of Dr. Kishore. So very, very happy to be here. This is my university in Pune, India, in a very picturesque, scenic view you can see. And this is my institute where I work, and where is my research lab, Composite Material Lab, that is Symbiosis Institute of Technology. What I want to going to speak about today is about agro waste. I just want to minimize. Dr. Hassan, how do I minimize this window? I want to minimize this.
Yes.
Yeah, I want to minimize this one.
Do you mean like this?
Let me once please open. Now it's fine. Now it's fine. Yeah. So what am I going to talk about? Since morning we are listening to wonderful lectures, one about how to manage the plastic waste, then about the wastewater treatment. And I'm going to talk about the agro waste today. Some of the very startling things that I want to bring the focus upon is global waste and the news which is coming, and that this is the right time to actually focus on that. I'm here with some of the statistics. Recently, in one report which has been produced by World Bank, they say that global waste to grow by 70% by 2050 unless urgent action is taken. So it is a very, very important issue that we need to focus on. And with this sustainability that we are talking about, United Nations goals, this is one of the major agenda. If you can see here the graphs, then it shows you about the waste, agro waste in 2016, what was the situation, 2030, and what it is going to be in 2050, and the data is millions of tons per year. So you can see country-wise, you can see the area-wise, and if we talk about Asia, it was 468 million ton in 2016. In 2030, it became 602 million tons, and then 2050, it's going to be 714 million tons. So you can see the rate with which this waste, overall waste, is increasing. And in the second chart, if you see that different kinds of waste. So there is food and green waste, which I will put together in agro waste, glass waste, metal, others, paper and cardboard, plastic, rubber and leather, and wood. So you can see that 44% is agro waste, or the food and green waste, and it is high time that we do something about it. Yeah. So what is agro waste that I'm going to talk about? Agro wastes are defined as the residues from the growing and processing of raw agricultural products, such as fruits, vegetables, meat, poultry, dairy products, and crops. Here, we can further classify it as animal waste, which is manure, animal carcasses, food processing waste. Only 20% of maize, this is just an example, that only 20% of maize is canned and 80% goes waste. And what it is done, it is either burnt or dumped. Then crop waste, corn stalks, sugarcane bagasse, drops and culls from fruits and vegetables, hazardous and toxic agricultural waste, which are pesticides, insecticides, and herbicides, etc. Whatever agro industries which are working, huge amount of waste is being generated, which further can be classified as agricultural residues, which further can be classified as field residues, where we include stems, stalks, leaves, seed pods, and waste which are coming out of the processing, that is husks, seeds, roots, bagasse, molasses. And industrial residues after the processing of the food, canned food, we get potato peel, orange peel, cassava peel, groundnut oil, coconut oil cake, soybean oil cake. These are just few examples, but you talk about the crops and the fruits and vegetables which are available to us, and the kind of foods, instant foods which are coming in the market, huge amount of waste is being generated. So what is done out of this waste? First, field filling, which is a very, very common sight. You can see some open field and people dump over there, and that affects the fertility of the soil. Or another easy way is to burn, right? Which causes a lot of smoke and other poisonous gases and contribute in global warming. In India or in California, you must have seen it becomes the news. The jungle fire and the crop fire, it becomes so huge that people can't even breathe, and they declare the holidays. It is that severe. And if you dump it in open, mosquito-generated diseases, environmental pollution, we all know about it. So if you see that how agro waste is utilized as on today, it is landfilling is 52.5%. Major chunk is landfill, which is actually affecting the fertility of the soil. Then combustion with energy recovery 12.8% only, composting only 8.9%. It should be the most important factor, but it is only 8.9% today, and recycling of waste products is 25.8%. So there is a huge opportunity to work on the agro waste. So what is the pyramid that we follow, the process that we follow today? So first, earlier we used to simply dispose of, but today cycle is different, right? So disposal comes last. We try to find out the energy recovery, recycling, reuse, minimize, and then prepare some important materials out of that, which is my area, and I'm going to talk about that. So goal is to lesser consumption of natural resources, thereby reducing the environmental load. And what are the advantages? Conservation of natural resources, landfill space, and energy. We know that temperature is changing, the environment is changing, the fertility of the soil is changing, the amount of rain which is happening at a place is changing, and disposal of this kind of waste is one major factor. So what I do in my lab, I try to recover the nutrients from agro waste, and here we are rethinking about their potential possibilities. So I have considered rice husk. I worked a lot on rice husk, and I tried to extract the silica and nanosilica, and then using that silica, we are trying to fabricate some more products which are very, very useful, which I'm going to show you in my slides subsequently. This project was supported by UGC, which is the apex body of science of university education in India, and that project was funded by UGC. To give you introduction about the condition or the situation in India, 120 million tons of rice is produced in India every year. It gives around 24 million tons of rice husk and 4.4 million tons of rice husk ash. Rice husk is the outer peel of that rice grain. And then once rice is taken out, then the remaining is the husk. And that husk, when it is burnt or disposed of, it is in a huge quantity. That ash is itself 4.4 million tons. I'm talking about only of the country India, but there are several countries where the rice is being produced and the situation is like that. What currently is being used of this rice husk? Cattle feeding, low nutritional value. Being fibrous, it could be fatal for them. As fuel in boilers, they're using partial and uneven combustion of husk leads to smoke emissions, and it leads to environmental pollution. The challenges are disposal of this huge volume of agro waste. We need to save the environment from pollution caused due to uneven combustion. Find useful ways to utilize silica rich rice husk and provide another means of economic growth of farmers, which we are trying to do, and we have done it. So I can't, yeah. So if you talk about the rice husk ash and rice husk, the constituents are silica, which is 90.23%. It also has very important mineral, that is alumina, which is again for industry use, that is 3.54%. Carbon 1.23%, calcium oxide 1.58, magnesium oxide 0.53, and remaining potassium oxide and ferric oxides are also there. So you can see that maximum content in rice husk is 90.23, and silica is in high commercial demand. I'm not able to move this. Yeah. So you can see here, what are the applications of silica where we can use, and then we can extract silica and use it. Solar panels, plastic reinforcement, animal food, healthcare, cosmetics. You see the freely flowing shampoo ads. There is silica. Coatings, pulp and paper processing, detergents and soaps, rubber and construction industries, silica aerogel for space applications. And further, I have extracted the nanosilica, which is used in ceramics, chromatography, electronics, coatings, emulsifiers, biological sciences, concrete mix. Silica as also thermal insulators. I have worked on silica, which is metal matrix composites that I have synthesized, reinforced with silica. Metal matrix composites, as you can see, some of the pictures and some of the applications, they offer high specific strengths and stiffness, higher operating temperatures, greater wear resistance, and they are lightweight. They're used in automobile, spacecraft, jet engines, brake parts, and there are several other applications of these metal matrix composites. I'm finding it a little difficult to move. Yeah. So how did I prepare the silica? So you can see, first we prepare the rice husk ash. Then next part is extraction of silica by alkali extraction method. Then comes extraction of nanosilica by reflex method. You can see here, this is how the rice husk looks. Then you can see it was washed properly and we crushed it. Here it is kept in the oven, and then finally it was burnt in the oven up to 600 degrees C and onwards. And then finally we got this silica. So steps are mentioned here. First, we sieve rice husk using mesh size of 300 microns, wash with water to remove impurities like sand, air dry for 24 hours. Then rice husk was heated at temperatures 400, 600, 900 and 1000 degrees C for duration 2 hours and 4 hours in the furnace and cooled by slow cooling or fast cooling methods. Again, we use sieves of mesh size 45, 90, 180 microns. Then rice husk ash of particle size 45, 90, 180 micron is prepared, and then ash produced was 20% of the weight of the rice husk. How to extract silica from rice husk ash by alkaline method? We took 8 grams of rice husk ash, added 3 normality sodium hydroxide solution of 100 ml, boiled for 1 hour, filtered and cooled till room temperature. You can see the equation for that. Under constant stirring, we added 5 normality H2SO4 dropwise in the sodium silicate solution till the pH fell to 2 and silica is precipitated. So if you see the pictures here, this is the process, right? And finally, we got this silica. Nanosilica, out of silica, you take 8 gram of pure silica, add 100 ml of 6 normality hydrochloric acid, magnetically stir it using magnetic stirrer. Solution was continuously refluxed. It refluxed for 4 hours at temperature 80 to 90 degree. Washed the sample with distilled water. Add 80 ml of 3 normality sodium hydroxide. Again stirred and nanosilica precipitate is formed. You can see the nanosilica. It comes like this. The precipitation is of nanosilica. Further, because as I said that there are several applications of silica where you need amorphous silica, you need crystalline silica, you need different types of silica. So you change the process parameters and you get it. You may change the duration of heating, temperature of heating, and then you get different types of silica. I mean the amorphous or crystalline silica. So it was observed the XRD that we had taken of rice husk ash, it shows that the crystallinity of silica from rice husk ash, it depends upon incineration temperature. If you incinerate at say 600 degrees C, it was amorphous, while as you increase the temperature after 600, it turns to crystalline. And at 1000 degrees C, the temperature of the furnace, the rice husk ash obtained was crystalline in behavior. Also, if you see the surface morphology, why this image is not coming, SEM image, but when SEM image was taken, there seems to be some problem. SEM image is not coming, but it also shows the presence of irregular sharp edges with angular and cuboidal shaped particles with size varying from 5 micrometer to 10 micrometer of rice husk ash. It has a highly porous structure with homogeneous particle distribution, and this property we used in making the silica gel that we are silica air gel, which we are making it is in the process. We are using this property of porosity of this silica of rice husk ash. The presence of some longitudinal angle coarse particles can be observed in this enlargement. I'm sorry that why the figure is not coming out. It is there. The presence of micron size particles is observed together with some other larger particles, and the angles are also observed in these images. Yeah, you can see here SEM images. Here they are. Fine. We also did TEM of silica, And the analysis, TEM analysis of silica particles shows micrographs or extracted silica. They show particle morphology, as in the pictures you can see. The minimum and maximum particle size of silica was found to range from 25 nanometer to 70 nanometer. TEM images of silica saw spherical silica particles intensively agglomerated. So based on how the silica ash is there, what are the process parameters, we can derive silica and nanosilica and then make use of it or apply in making different kinds of maybe applications. UV spectrometer, UV visible spectroscopy of silica that shows that silica particles exhibit optical phenomenon due to presence of different defects resulting from incomplete formation of silica tetrahedral network on the silica surface, such as oxygen and silicon vacancies. To study the effect of particle size on electronic absorption behavior, this spectroscopy of silica sample has been taken after dispersing in water, and UV visible light transmittance spectra of different sizes of silica particles showed a single maximum at 300 nanometer, as you can see in this graph also. This region corresponds to energy range 5.59 to 5.43 electron volt. The above absorption range may be due to the presence of surface paramagnetic E centers, such as paramagnetic positively charged oxygen vacancies. So that can be further analyzed. Also, we did energy dispersive spectrum. You can see that EDS analysis determines surface composition of ash powders when rice husk is burnt in a controlled temperature during thermal decomposition of organic matter, leaving a highly porous and nanostructured particles of silica. The pore size, amorphous crystalline character can be changed by varying process parameters. This texture is a consequence of husk morphology. The rice husk ash presents complex structures. Canal, pores, and striations can be observed. These are typical forms from the plant ash source. The chemical composition is evident here. You can see there it contains potassium, carbon, nitrogen, oxygen, chloride, silica. First application, I have just mentioned some of the applications where I have used this synthesized silica. Its first application, synthesis of metal matrix composite reinforced with silica extracted from rice husk ash. How we started? Rice husk as we prepared. Then from there, rice husk ash preparation, rice husk ash as reinforcement, and we have taken aluminum as base metal. Technique was used, 80% weight of aluminum, 15% weight of silica, and 5% weight of magnesium. Magnesium is taken for wetting. Otherwise, aluminum and silica will not wet, will not gel together. That's why this magnesium was taken as the wetting agent. Then preparation of metal matrix composites, we got it. I'll show you the picture diagram. You can see here, this was the apparatus that we set in our laboratory. This is the furnace. Inside there is a crucible, and this is how we prepared. The second, that was aluminum metal matrix composite. We also prepared copper and titanium metal matrix composites with increased strength using powder metallurgy. So first, the process, I'm not taking into detail. The powder was taken, it was processed, and the properties were studied. Here, the powder, we checked the size and shape, did the characterization, microstructure studies were done. Then we studied about compaction, sintering, hot pressing method we used to synthesize, and we studied the properties, hardness, density, strength, and other functional properties so that it can be used wherever, with whatever application that we select. The X-ray analysis of aluminum metal matrix composite reinforced with silica is on your screen. You can see that. It shows the image of aluminum silica composite, shows a broad hump between 35 degrees to 45 degrees, which is associated with the amorphous character of metal matrix. Aluminum matrix has large domain of crystalline phase, but when it is reinforced with silica, semi-crystallinity of composite shows up. The XRD image also shows reinforced silica material with tetragonal symmetry. Small peaks in the XRD were observed due to metallic impurities in silica. EDX of aluminum metal matrix composite to find out the composition. As you can see that these are the elements which are present there in this weight percentage. So silica is having the maximum content. SEM of silica composite, as you can see here, micrograph aluminum silica composite with different magnifications. The results show a non-uniform distribution of silica. The magnesium particles were approximately 1.4 micrometer of size. It shows irregularity in shape, unevenly distribution of particles. The regular silica particles are much more variable in size. We couldn't find, and we are working on getting the silica particles of uniform size. And this was the final product that we made, which was having more strength, and it is being used also. Copper and titanium metal matrix composite reinforced with silica. This is the process. Pre-treatment of silica particulates, mixing of powders, blending, compaction, cold uniaxial pressing, sintering of the green samples, and then heat treatment. This is the SEM analysis to check the surface morphology. You can see that XRD analysis is also done for the materials so that we can use it for different applications. Second application that we did was synthesis of geopolymer cement reinforced with silica and graphene, and we could see that we could enhance the strength of construction material. You know that a lot of carbon emission which is happening, 12% is because of the cement production. So we tried to replace partial replacement of cement by the silica which is extracted from green roots. So this was the process followed. 300 gram PPC, that means the cement plus fly ash plus 3% of silica was taken as the base material, and 0.7 gram water stabilized industrial grade graphene nanomaterial was dispersed in it. Consistency check was done, and then finally we measured the compressive strength by keeping the days of curation for 7, 14 and 28 days. You can see here water stabilization of graphene, then ready slump we had, then we have done it in our civil engineering lab, curation of fabricated composite, and this is the final product. As you can see that we could prepare the cement beams were reinforced with silica. I'm sorry, there seems to be some problem. Yeah, so these are my students who are working in the lab. They are doing the procedure as such. Everything was done in the lab itself. And here are the bricks which are formed and which are being used in making a small veranda there in the college. These are the bricks. All these compressive strength measurement tests were done in the laboratory, and you can see that I'll show you the final picture, that when it was curated for 7 days, then the strength increased. As you can see that when we prepared different cubes and the strength in each case increased for different weight percentage that we prepared for 7 days again, 14 days, and we could see that there was a growth in 28 days also. So it depends. Compressive strength depended upon the number of days that we actually curated the cement, synthesized the fabricated cement bricks. Now my lab is working on use of this extracted silica, green silica, in different ways. We are in the process of preparing silica adhesive for joining the tiles in spacecraft and launch vehicles. Then another in our lab, which we are trying to work on Si3N4 silicon nitride, cryogenic ball bearings, silica SiC nozzles, silica reinforced polymer composites for making structural parts of spacecraft, use of silicon carbide coating to prevent the carbon substrate from oxidizing in space shuttle, silica-based materials for thermal protection system, silica aerogel to collect stardust, silicon carbide whisker reinforced, aluminum for making panels and tubes. So these are some very, very limited applications that we are working on, but there are several more where we can work. The most interesting is silica aerogel. This silica aerogel is a synthetic porous ultralight derived from a gel in which the liquid component for the gel has been replaced with a gas. The aerogel has extremely low density and low thermal conductivity. Applications, if you see, it can be used as a sensor. Electrical resistance changes with humidity in case of silica aerogel. Also, aerogel is material with low dielectric constant for IC applications. Aerogel as catalyst, the high surface area of aerogel leads to many applications, such as chemical absorber for cleaning up spills and to trap the stardust. So these are all several applications started with the silica, which we extracted from green root from rice husk ash. These are the properties of silica, and based on these properties, several other applications can be thought. So with that, I just gave you a brief introduction about one of the applications of agro waste, silica, but in the process, we are working on several other applications so that we can minimize the disposal of agro waste. Thank you so much.
Thank you, Dr. Mina. A very nice presentation, a very interesting application for the agro waste. So we have a couple of minutes for one or two questions. Anybody has any question, please? Okay. Dr. Muhammad, do you have any?
Yes, I have a question.
Please.
Yeah, go ahead, please.
I have a question about the preparation of silica by calcination of rice husk. My comment is concerning the yield, because, for example, when we make under inert atmosphere under nitrogen, we pyrolyze the agro waste. We have to obtain biochar, for example, we reach something like 20-25% yield. So I suppose that with ashing, maybe what is the yield? Because the yield must be something about maybe 1 or 5% of the agro waste.
20% ash is extracted from rice husk. 20%, right? But out of that, silica we could take only 3%. Silica was less. But here the thing is that one, we are finding some suitable solution, right? We are not simply dumping it somewhere, but finding some suitable solution of disposal of waste. And then from green root, the silica which we are extracting is not only used in different applications, but mainly for food processing. We are having the silica which is extracted is non-toxic. So that is the yield is very small, no doubt about it. But even that small quantity can be utilized in commercial purposes. That's the objective. Yeah.
Okay, and I have the other question is regarding the treatment of silica, the product you have, because you have a lot of KOH and hydrochloric acid. Is there any way to avoid that, or to change the protocol to avoid using very harsh conditions to obtain the final product?
We have used this NaOH and HCl, but H2SO4. But I think that we didn't try other chemicals, but we just tried with these things, and we could get very good 90% pure silica we could get. But I think there must be some other ways we should try and look into it. Our focus is to use silica of different properties and use for different applications. So right now we are working on preparing, synthesizing highly porous with least density silica aerogel. But you are right, we may have to explore various other processes also. Yeah.
Thank you.
Yeah. All right. For the sake of the time, thank you, Professor Mina, for being with us today, and we look forward for more collaborations between the CAM and yourself. Thank you again. Thank you so much.
Thank you. Thank you so much.
Thank you.
Thank you for inviting me. Thanks.
You are welcome. So our next presenter is Dr. Arvind Kumar Bhakta. Dr. Arvind Kumar Bhakta, he received his MSc from Master of Science from St. Joseph College in Bangalore, India, and his PhD from University of Namur in Belgium in 2020. His thesis was work was on carbon nanotubes modification with diazonium salts and metal oxide nanostructures for water treatment. He is also a recipient of Wolny Bruxelles, international grant to conduct research in brewer spent grain biochar for waste water treatment application at the University Paris Cité. Very interesting application, of course, and very interesting usage of the brewer waste. So, Dr. Arvind, please go ahead.
Thank you so much for this, for the introduction. It's my pleasure to be here, and thank you so much for the opportunity to giving me to talk here. So good afternoon, good morning, and good afternoon, everyone, depending on where you are based on. So I'm going to talk about the carbon allotropes for wastewater treatment application. So sorry, I'm using my mobile to give the presentation. So maybe sometimes you have this.
Everything looks okay, Dr. Arvind.
Okay.
Yes.
Okay.
Yeah.
Okay, so basically, as you know that the carbon element is very interesting because it has a 4 valence electron, and that could participates in making a bond either sp, sp2 or sp3 hybridize, and that makes it to it has a potential to be exist in different allotropic forms, and that's what you have a different allotropes of carbons, and you can see you have nanotubes, graphene, graphene, carbon fiber, diamond, and so on. And wait. So one of the carbon allotropes is nanotubes. What is nanotube? So basically, you all are aware of the pencil, and the pencil tip is made up of graphite. And if you see, the graphite has a layered structure, and when you exfoliate it, basically the one layer of graphite, which we call it graphene, and if you rolled up, it's called carbon nanotubes. It can be single wall, or it can be double walled carbon nanotubes when you have one carbon nanotubes inside another in a concentric fashion, or if you have more than 2, then you call it multi-wall carbon nanotubes. It has a very interesting properties because like for example, it has extremely high elastic modules, it is thermally stable, it has an electric current capacity more than copper actually. And it has a high spectral ratio. So this makes it a potential candidate for plenty of applications. This is just to say about as we are talking about nano. So just to want to say what is nano, just to give a comparison. So what is nano? Nano is nothing but a 1/1,000,000th of something. So if you see the right side, if you can really compare how we are dealing with the size of the earth and the basketball and this nanoparticle. So with this, you will get a clear idea how much is the nanoscale. This is the paper reported by Dr. Ari Smalley, where he has talked about the top 10 problem in the world for next 50 years. And if you see, the top 3 are energy, water, and food. So it's really a good way to also think about some water purification and water recycling. So for the first part of my work, the objective was to advance the method of CNT purification, because then only you can exploit the real properties of CNTs, functionalization, and then nanocomposite preparation. And afterwards, understanding the effect of surface concentration of functional groups. And then here I will also talk about the diogenic chemistry, and finally the application. So basically, the carbon nanotubes, actually, when it is crude form, it contains some impurity, and basically in the form of alumina, which was acting as a support. So this can be removed by refluxing it with sodium hydroxide. And you can see after on the left side down, you have the alumina, which is a big chunk, and on the right side down, you can see after treating with sodium hydroxide, it is completely removed, because when alumina react with sodium hydroxide, it forms a sodium aluminate, which is a salt, and it can be easily washed by water. So here are the, but you know that as such carbon nanotubes is not so reactive and it's not almost a non-dispersible in many solvents. So it's better to functionalize it and to improve the furthest properties. And one way is to use the diazonium salt. Here I have used 2 types of diazonium salt. I mean, of course, I have used many, but I'm talking about only 2. On the left side, you have a 5-amino 1,2,3-benzene tricarboxylic acid, which was mixed with water, carbon nanotube, sodium nitrite, and perchloric acid, and it was gone through iodization, and then finally it was filtered and washed and filtered, and then we have this functionalized carbon nanotubes. On the right side, you can see the how the groups are attached on the carbon nanotubes. You have a carbon-carbon bond and C-N-C bond. This is clearly confirmed by the presence of a high amount of oxygen and also the presence of nitrogen in the table, which is done by X-base analysis. So once I have the functionalized carbon nanotubes, actually I treat with salts. For example, let's say iron acetate salts solution, and here the carboxylic group present on the carbon nanotubes, it acts as an anchoring agent to capture the ions through electrostatic interaction, and after heat treatment, it forms a nanoparticles decorated on carbon nanotubes. This is just a scheme. So for example, here you can see on the left side, you have the TEM image. So one A and B are representing the A is the impregnated sample and B is after heat treatment, where you have a nice formation of iron nanoparticles, and this is using tricarboxylic group. On the right side, you have the monocarboxylic group, and the table clearly shows that when you have a tricarboxylic group, which has high amount of iron content compared to the monocarboxylic one, because here you have a tricarboxylic group which has more anchoring capacity than the monocarboxylic one. Also, there was it was found that it is more crystalline and particle size is 1 to 8 nanometer, but with the monocarboxylic particle size are 1 to 5. It's because here maybe when you have tricarboxylic, you have a high amount of loading, so that causes a slight aggregation, but you can see aggregation of like just 1 to 8 and you have like 1 to 5, so there's not much difference. And then our method was very efficient, which was extended to other nanoparticles also. So it was not just for iron, but like barium oxide, lanthanum oxide. On the right side, you have the megamite. Let's come to the application. So as you know that you have like lots of dyes coming from the textile industry, and it is really polluting the environment. And these dyes are very highly toxic because it can be mutagenic, it can destroy the aquatic life and so on. So there's a really alarming need to develop methodology to purify the water, and one such is through adsorption, because it's simple, non-destructive, but also we have a mineralization, which has another advantage. So in adsorption, you are absorbing and you can recover the dye, and then you have the mineralization where you are completely degrading the dyes, which I will talk later. One of the model pollutant was methylene blue, which is very widely used as a food preservative, hair dye in agriculture, and so on. And that is the fact that it comes into the wastewater. The methylene blue have a really toxic effect, something like you can see lots of disease mentioned due to the high exposure of methylene blue, like nausea, cyanosis, jaundice, and so on. So as I have shown you already, the megamite nanoparticles decorated carbon nanotubes, we tried the test where we were like treated with this 20 ppm methylene blue solution using 3 mg of adsorbent, and you can see after treatment, the water is completely purified. And here, these particles are very magnetic in nature, so you can see with the magnet we can easily manipulate their movement. And also to say that we have done the experiment, we can see the histogram where you have just iron oxide nano powder. The the commercial one where the adsorption was not that good, but when we have just carbon nanotubes, it's still not that good. But when you have a physical mixture also, which is not good, but when you have like a the attachment, the attachment of carbon nanotubes with mega nanoparticle, it has the highest adsorption capacity. So just to summarize for this part of the work, like there was a novel method was created for the scientist purification using sodium hydroxide treatment, and the method was simple and very efficient. And of course, we are able to prepare in a very large scale. This clearly shows the advantage of diazonium chemistry over acid treatment, because when you treat with diazonium salt, we don't really destroy the carbon nanotubes, but when you do with acid, you can really break the carbon nanotubes depending on the time and also the acid used. And finally, it was applied for anti-absorption. Another part is regarding biochar. Biochar is what is biochar? Actually, biochar is like we have this plants and animals waste material, and when we pyrolyze it in an atmosphere, we forms this carbon. It's called biochar. It is a very interesting properties, like it has a high surface area, it has water holding capacity, porosity, and which has made it to apply for plenty of applications. So objective of our work was to study the effect of biomass grinding on resulting biochar, development of new methodology for synthesis of biochar, and also how we can really tune the surface morphology. So this is just, I'm showing you a scheme, what we have done. So we have this, we have obtained the brewers, spent grain from a local brewing industry, and which was pyrolyzed to make a biochar, and this biochar resembles like Chinese leaf tea eggs. So how we have tuned the different morphology from the, it's very interesting because here there's only one brewer's spent grain, like the biomass is the same, it's not the different biomass. And then we have gone through different procedure, like we have just pyrolyzed the as such a brewer's spent grain, washed and dried, and then it was ground in coffee mill, and then it was also mortar and pestle was used to grind the brewer's spent grain. In the other side, the wet biomass was it was blended in a blender, and it was made a pellet, and the pellet was further ground using coffee mill. And you can see we have the same biomass, but with we have created a different morphology using the same biomass, using different grinding procedure, and we can clearly see that this is really reflected in the same image, where you can see you have different some depending on the method used. Some are more soft, some has like a ball or egg-like structure, some are less porous, some are more porous. So you can clearly say that when you have used the grinding method, it was more important to show, like when we use different grinding method, it has a really, when you have this effect on your biomass, actually that effect is really seen in your biochar also. And this is the EDX mapping analysis of the egg-like structure. And this is just to show that this egg-like structure have some particles, which was not like some kind of impurity, but actually they are the carbon materials, and with some phosphorus, and of course you have some metals which are coming from the biomass itself. The TGA was done to understand the stability of the material, and you can see the TGA shows more or less the same stability for all the samples. But when you do the DTG derivative, it really shows a really huge there is a difference reflected in the DTG, and they said that the coffee mill ground biochar have the high stability compared to all of the biochars. And one of the best example of a grinding method induced graphitization is shown in this, when you can see the Raman, where D/G ratio is more than G/G ratio. If you see on the mortar and pestle, that BMP is lower than 1, but in others it's higher than 1. So this really is an example of a pressure-induced graphitization of biochar. So here we can conclude for this part that there's a definite effect of biomass grinding on the resulting biochar, and mortar and pestle grinding have really shown a very different effect. I mean, in terms of all methods have shown different effects in terms of surface morphology, but only the mortar and pestle grinding have shown the biochar graphitization. And of course, we were able to successfully create get a novel Chinese tea egg leaf like biochar, which is very interesting because of its porosity. The last part is about decorating this biochar with silver and copper nanoparticles. So basically, we have used the biomass, which was impregnated with we're using wet impregnation, silver and copper salt, and then it was pyrolyzed, and finally we had biochar impregnated with silver and copper nanoparticles. Actually, this was a literature survey which shown that there's not even a single work using methyl orange degradation with biochar and silver copper nanoparticles. So that was our motivation to discover this. And so XPS analysis have clearly confirmed the presence of silver and copper nanoparticles on the biochar. So this is a clear advantage of biochar impregnation with clear indication of impregnating biochar with silver and copper nanoparticles. And here you can see the figure A is just a biochar, and then figure B is biochar with silver, and figure C is biochar with copper, and figure D is biochar with silver and copper. So you can see the really clear clear distribution of nanoparticles, which is very homogeneous, and particle sizes somewhere around 40 to 50 nanometers. And it is crystalline in nature, which is confirmed by XRD. This is the dye mineralization experiment, where we have used methyl orange as a dye pollutant. And here, after treating the 20 ppm dye solution with this catalyst with under H2O2, in 6 hours, it was completely able to totally mineralize the entire sample of methylene blue. And also we tried on the right side, you can see on the down that you have a mixture of dye that is methylene blue. You have a methyl orange and methylene blue, and even there was a almost demineralization, but here there was a bit of methyl orange was still there, and methylene blue was almost mineralized. So in this, they say that in a mixture, this material have a high affinity towards methylene blue than methyl orange. So I conclude that silver copper nanoparticle was really efficient to degrade methyl orange and also methylene blue, and then it can be also extended to other dyes. And method is simple and reproducible, and of course it has shown a selectivity towards MB compared to methyl orange. Of course, other dyes can also be tested to see if what are the other selectivities. And this could be a good example to degrade dyes from the textile industry. Our future plan from the group is to make this biochar also in the field of like textiles, like using making fiber using electrospinning, and also to use this biochar as an ink for 3D printing application. So we are looking forward for this also application in the future to further advance the biochar field. I acknowledge my funding, Wallonia Bruxelles International, my lab, all my colleague, my special thanks to my supervisor, Professor Mohammad Shehmi, for his always constant support and guidance, and very friendly and helpful, very friendly behavior and helpful support. And I'm really glad because I had a really I can say that I'm doing my postdoc in Paris because of him, because he really did lots of effort to bring me here and also get the funding. So thank you so much, Professor Shehmi, and all of my colleague Yusuf and Mangchi for their work, and Professor Suad Amar, and each and everyone who has contributed to work who has contributed in my field and who has motivated me. And thank you to the audience for their patience to listen my lecture.
Thank you, everyone. Thank you, Dr. Arvind. Glad to have you with us today. So there is a question from the audience. What is the impact of the particle size on the degradation of methyl orange?
Okay.
Jamilor and Sauri.
Actually, till now we have not studied the effect of particle size on the methyl orange degradation, because here our more comparison was like comparing when it is just like a silver and copper, and when we have this together mixture on the biochar. But it's a really good point. But okay, usually we expect that when small sizes are there, the degradation efficiency should increase because of the large surface area, but still we don't know at what particle size it could degrade to what extent.
Okay. So any question from the audience? Dr. Muhammad, do you want to ask something? No question from your side? Okay, Dr. Arvind, I was wondering actually about the mechanism of interaction between the nanoparticles and the biochar surface.
Yes, sir.
What do you think? I mean the metals and the biochar surface. How is the interaction happening in your opinion?
I think it's a good question. Is it like okay?
You had a very good distribution actually in terms of the pictures that SEM pictures that you showed. Very good distribution for the
thank you.
metal, different metals in the surface of the biochar.
Thank you, Professor. Actually, I don't have much idea which kind of really the bonding involved, but I will really find out what's happening, which kind of bonds are there, or the interaction.
Okay. Thank you, Dr. Arvind. Any more questions from the audience? Okay, I guess thank you again, Dr. Arvind. And
thank you so much. Thank you so much.
You are most welcome. And we will move to our last speaker, Dr. Xiaoyang Liu from Hamad bin Khalifa University and Qatar Environment and Energy, KERI Research Institute. Sorry, we used to call it KERI, so this way. Dr. Xiaoyang Liu is a senior scientist at the Water Center at KERI, Hamad bin Khalifa University. His expertise involves the development and optimization of advanced processes and materials for water treatment. He has H index of 38, and his publication gained a lot of citation worldwide. He is currently leading the development of oil water separation technologies at Kerry in alignment with the nation, with Qatar and Kerry is national vision for water security. He also serves as an editorial board member for scientific reports and some other journals. Dr. Leo, we are glad to have you with us today. So please go ahead. The floor is
for
yours.
the next introduction, Muhammad.
You are most welcome. Yeah.
So can you see my shared screen for the slide?
Yes. Yes.
Okay, great, great. So, okay, I will give a brief introduction for myself.
So please make it a full screen. So
full screen. Okay, okay. So full screen here. Is full screen now?
Yes, perfect.
Okay.
Go ahead.
Okay. So my name is Zhaoyang Liu. I'm a senior scientist in Qatar Environment and Energy Research Institute, KIWI Water Center. So my research background is wastewater recycling and reuse. Today, I would like to present the research project named Oil Spill Contaminates Removal by Novel Anti-Fouling Membranes. So let me start with the research background introduction. The reason why we carry out this research project. As we all know, Qatar and the Gulf region is the international hub for the oil gas exploration, production, and transportation. This active oil gas related activity pose a persistent and severe threat on the seawater contamination. So the water supply status in Qatar includes as shown as this. The first one is over 90% of fresh water in Qatar depends on the seawater desalination. This is the main source for oil supply for water supply in Qatar. And Qatar National Strategic Water Storage with a mega water reservoir is only a matter of a few days in the event of any disaster occurrence. And the operation of a desalination plant is vulnerable to the oil contamination in seawater. How to, okay. So this diagram shows the feed and the transport path for the oil spill occur on the marine environment. So the strong wind and the tide and the wave on the seawater actually complicated the oil spill cleanup work and the situation. The strong wind and the tide on the sea will break down the floating oil slick into different form of oil, as shown in the table 1. There are 3 different form of oil, including the free oil, or called dispersed oil, with the oil size larger than 20 micrometers. And the second one is emulsified oil, with the oil droplet size between 1 and 20 micrometers, and the soluble oil with the size less than 1 micron. So among the 3 different form of oil, the dispersed, the emulsified oil has a high chance vertically transferred to the underwater seabed. The seabed is the place where the desalination plant, the seawater intake portal located. So the emulsified oil would be sucked into the seawater intake portal and transported through the pipeline into the on-land seawater desalination plant inside, which can cause the problem for the operation of seawater desalination plant. So this slide shows some cases of oil spill accident happened in Middle East and caused a major desalination shutdown. As shown in the table 2, United Arab Emirates in 1997, and Saudi Arabia in 1991, and Kuwait in recently the year 2017. And these major oil spill accident caused each country's desalination plant shut down for a few days. and affect the national water, freshwater supply capacity. So the oil spill accident or incident in Middle East is a real, severe problem. So, for the oil spill responsive measures, we can break down into two different categories. The first one is offshore responsive measures. From the photo, we can see the first one is polluting boom. The boom will physically contain the floating oil from further spreading on the sea. And after containing the oil, the mechanical skimmer will skim off all the floated oil from the seawater surface. The second one is the chemical dispersant. People can use the ship, the boat, or the airplane to apply the chemical dispersant on the surface oil flake. The chemical dispersant will make the floating oil visually disappear, but physically, the oil still exists or suspended in the water body. Actually, this technique cannot remove any oil from the seawater. So there's some drawback for the current existing, the offshore responsive measure, including for the booming and the skimming. This technique only capable to remove the floating oil, but not for the emulsified oil, and for the chemical dispersant, which can cause a secondary environmental pollution because people added the additional chemicals into the seawater environment. So the second category is onshore responsive measures. As we know, there are two major desalination technologies adopted in Qatar and the Gulf regions, which includes thermal desalination. The typical example is a multi-stage flash (MSF) thermal desalination process. The second one is membrane-based filtration. The typical example is reverse osmosis membrane desalination technology. The figure the green color diagram shows the typical pretreatment process train adopted in the Qatar RO membrane desalination plant. As we can see, the diagram shows the process consists of multiple treatment units, including coagulation, flocculation, media filtration. But the problem is none of this adopted technology is designed for the oil removal. So if there's any oil spill accident occur, the oil contamination would cause severe failure of the RO plant by fouling the RO membranes, make our membrane element dysfunction. And also the oil contamination could be transported to the final water products through the thermal evaporation process in the thermal desalination plant. Until now, there is no effective onshore measures adopted in the desalination plant for removing oil spill. So this slide shows a typical process adopted in the oil gas industry used for the oil water separation process. So the process train consists of the primary separation, which based on the gravity separation. The second one is the secondary separation, which includes the dissolved air or gas flotation. The third one is the tertiary separation, normally include the walnut shell filtration or carbon-based filtration. But there's some limitation for the current existing oil water separation technology. For example, for the gravity separation, it is not efficient for removing the emulsified oil from the water. For the air flotation, it has to add the chemical dosage to enhance the emulsified oil removal efficiency. So also inevitably generate a large quantity of solid sludge needed to be safely disposed. And the media, just like a walnut filtration, the drawback it has a low tolerance for the oil loading in the feed water, which the oil content has to be lower than 100 ppm. So therefore, it is essential to develop effective onshore oil removing technology to prevent the desalination plant shutdown. So, so among all the previous study for the different oil removing technology, including the air flotation, hydrocyclone, gravity separation, membrane filtration, membrane technology stand out from all this technology due to its special advantage for membrane filtration, including the less chemical required for the membrane operation process and the small footprint for the membrane treatment plant. This advantage is very critical if we want to install the treatment technology or the unit on the offshore oil drilling platform because limited space availability on the platform, offshore platform. So membrane filtration also effective in the oil removal, oil emulsion removal based on the previous published literature. And it also has a high tolerance for oil loading in the feed water, which can be up to the 1000 ppm, and also has a high effluent quality for environment discharge. Based on the US EPA regulation, the oil content in the discharged wastewater, the concentration for oil has to be lower than 20 ppm. But still, there are some issues for the current available commercial membrane, including the first one, the low water permission flux, as shown in the figure 1, the SEM image. The commercial membrane body is made of the segregated pore structure, which requires the external pressure to push the water pass through the membrane body, which inevitably result in the low water permission flux. The second one is the membrane fouling issue, because most of the commercial membrane is made of the synthetic polymer, for example, the PVDF polymer, which in nature is hydrophobic and oleophilic, so which is easy to be fouled by the oil contaminant during the operations. So under this background, so our research team in Kiri came up with a new research strategy for developing oil water separation membranes. This new idea was inspired by one of our previous research outcome for the forward osmosis membrane fabrication. The FO membrane is made of nanofiber-based structure, so which has a very excellent advantage, that is the super high water permission flux, because the three-dimensional interconnected pore structures which made of the nanofibers as shown in the SEM image. So inspired by this research outcome, so our team expect our new idea, the inorganic nanofiber-based membrane, can achieve the following result. The first one, the high water permission flux, because the interconnected pore structure, if it made of the nanofibers, and high oil separation efficiency, because the tight the pore size in the new membrane, and the low fouling propensity, because the material is made of inorganic material, ceramic material, rather than the polymeric materials. So our teams developed two different kind of nanofiber-based membrane. The type 1 membrane called inorganic nanofiber, polymeric microfiber, asymmetric membranes, based on the SEM, the photos and the SEM image in the figure 7. The new membrane consists of two layers, which is top layer and the bottom layer. The top layer is made of the inorganic titanate nanofiber with the fiber length greater than 30 micrometers. And the bottom layer is made of the, actually it's used, directly the commercial cellulose microfiber filters as mechanical substrate, provided mechanical strength for the membrane body. So we conduct the surface wettability study on this new membrane, as shown in the image in the figure 8. So the water droplet on the surface of the new membrane rapidly sink into the membrane body, which suggests, the super hydrophilic property for this new membrane. And the B shows the results for the underwater oil contact angle measurement, as shown the B. We use different oil, including the sunflower oil, diesel, petroleum ether, hexane, as the contact angle result shows all the oil contact angle from different oil, or shows the super hydrophobic property with oil contact angle greater than 150 degrees, which indicate a very sound oil repelling potential to prevent the oil falling issues. So we further conduct the performance test with this new membrane for the oil water separation, as shown in the figure 10. All the oil content in the treated effluent, the oil concentration in the effluent is lower than the concentration regulated by the US EPA, the discharge limit, which is 42 ppm. So which suggests our membrane is very effective and efficient to make the water quality, the treated water quality is good enough for environment discharge. So the photo 11 shows the before and after the treatment with our new membrane. We can see before the membrane filtration, there is some small emulsified oil droplet suspended on the solution. But after membrane filtration, the solution become clear, and there is no visible oil droplet suspended in the effluent. So we also conduct the anti-fouling and the reusability test. So we carry out 10 cycles of reuse for the membrane with the oil water separation test. So in between each reuse cycle, we use our lab hot tap water to rinse the membrane body to remove the oil residue inside the membrane body. So the hot water temperature is around 50 degrees Celsius. So as shown in the figure 12, after 10 cycles of the reuse test, in terms of the water flux and the water content in the permit all remain constant, which indicate its excellent reusability for our new membranes. So for the second tab 2 membrane we developed, it called the wendable or inorganic symmetric membrane. The reason we developed the type 2 membrane because the type 1 membrane, although it has excellent oil remove efficiency and high water permission, flux, and low membrane fouling tendency. But there's a weakness. I like to be honest for this type 1 membrane. It is weak mechanical strength because it made of the cellulose substrate. After long-term soaking in the water, the mechanical strength will become very weak. So under this, background, we further developed type 2 membrane, which made of we use the commercial carbon fiber cloth as substrate, as shown in the photos. So and further grow the inorganic zinc oxide nanorod on the individual carbon nanofibers. Because the carbon nanofibers size is around micron size. The ground nanorod is in the nano size. So we also conducted the surface wettability study. The data not shown here because the time limitation for the presentation slot. The results also show the type 2 membrane also have the super hydrophilic and at the same time super hydrophobic oil repelling property, which indicated the good water flux permission potential and also the high anti oil fouling potential. So this slide shows a performance test with this type 2 membrane for the oil water separation test. As shown in the figure 14, we use different oil to test the membranes, including the diesel, gasoline, sunflower oil, toluene, petroleum, ethane, hexane, etc. So we can see, the type 2 membrane has high water fluctuations, permission fluctuation, also has a high oil ejection rate, almost can achieve over 99% of oil removed from the wastewater. So we also conduct the oil water separation test under the saline condition. We dose the salt, sodium chloride in the wastewater solution with the salinity around 5,000 ppm to simulate the brackish water condition. We can see, the performance of the membrane in terms of water flux and oil rejection rate almost didn't get noticeable affected. The performance still remain the same as the conducting the fresh water. So for the all the technical details, how to fabricate the membrane and the conditions to test the membrane, you can find out in our series publications as shown in this publication list in the slides. Okay, the conclusion for our studies, the new type of inorganic nanofiber-based membrane has an advantage, including the high water permission flux, because the interconnected three-dimensional pore structure made of the nanofibers. So the efficient removal of emulsified oil because the tight pore size in between the individual nanofibers, and the low oil fouling propensity because the material is made of inorganic or called ceramic materials, compared with the commercial ones, majority made of the polymeric materials, which is easy to fold by the oil. Thank you for your attention. That's all for my presentation. I'm happy to answer any question from the audience.
Thank you. Thank you, Dr. Liu. We are really glad to have you with us today. Any question from the audience for Dr. Liu?
Can I ask a question?
Yes, Professor Muhammad, go ahead.
Okay, thank you, Dr. Leo, for your talk. I have a question about the fabrication of the membranes with the top layer. How do you proceed? You make two electrospinning procedures.
So you mean
I can't remember which number of the
so you
slide.
mean this membrane?
You have shown one with, I think there is a green color.
Green color. Oh, this one. Oh, okay.
Yes, this one, this slide.
Okay. So let me clarify it. The two layer made of the top layer and the bottom layer. The bottom layer we directly use the commercial, the lab cellulose filter as a substrate. On the top layer, we firstly we synthesize the inorganic titanate nanofibers in our lab. Use a method called hydrothermal. Oh no, yeah, the hydrothermal method. So I use the autoclave. This one, to synthesize the nanofibers solution. Then we use dead end filtration setup. First, we lay, the commercial cellulose microfibers on the setup, the filtration setup, and pour the nanofiber contained solution on top of the cellulose membrane. Under the filtration, the membrane, the nanofibers layer will deposit on the surface of the cellulose substrate. That's the process how we make the two-layer membrane. It's like a physically deposited on the substrate, for the top layer.
Okay, thank you. Thank you very much.
Thank you, Dr. Mohammed. Dr. Leo, I have a question regarding this one. You mentioned about the mechanical strength and the loss of the mechanical strength of this membrane, basically. So what do you think happening there? Is it mainly because of the titania? Do you think that it might be good to have some kind of substrate mixed with the titania in a form of a composite, basically? You get my point? Instead of spinning just titanate nanofiber, you might mix it with some host matrix like polyethylene glycol or polyethylene oxide, and then do the electrospinning on the top of the cellulose, the commercial cellulose acetate, I believe, that you use. Yeah.
Yeah. Yes. Oh, of course. That's a good idea. They also can deposit the nanofiber top layer on the. But for my personal experience, the electrospinning method normally use to spin the polymer solution. It's not the inorganic solution. So normally it's polymer membrane can be made by the electrospinning method. It's not the inorganic membrane. Yeah, this is my understanding. Yeah.
Yeah, so I'm suggesting that you mix the titanate nanofiber that you produce by the hydrothermal with another polymer, like typically PVA is a very good one for the electrospinning, and then you make the electrospinning in the top of the commercial membrane.
Oh yes,
this might help with the mechanical property issue.
Yes, you're right. You are right. You are right. Yeah, I agree with you. Yeah, this could be another research direction maybe for the
Yeah.
future. Yeah.
Yeah, we could work together on this. If you
Of course.
Sure.
Of course,
Yeah.
I love. It's my pleasure. Yeah.
Yeah, thank you.
Thank you very much. Thank you.
Yeah, thank you. But very interesting performance actually. Especially the flux is very high, honestly, in your case, and the fact that you're able to clean it with just water. This is very interesting too. Yeah, you don't use any chemicals. It's very interesting. Yeah. Thank you so much. Any other question from the audience? It seems that we don't have any more question, and I guess this will conclude our session for this morning. So please note that we'll still have a video presentation. Ms. Noor will handle after me for this part. And also there is most importantly, there's another session tomorrow morning. So please be with us in this session. And thank you to all for all the nice presentations, as well as thank you to the audience for being with us today. Thank you.
Thank you, Dr. Muhammad Hassan, and thanks for Professor Said Zaidi. I would like to thank all the audience. We have poster session now. We will present video for posters was made by researchers and students. You can have a break now, enjoy the posters, and we will come back at 3 p.m. Qatar time. So please be aware that we will continue our evening session at 3 p.m. Thank you so much. Hi, good evening, everyone. I would like to welcome you all in our evening session for the day 1, where we will consider Goal 3, good health and well-being, and Goal 6, clean water and sanitation. The moderator of this session will be Dr. Shane from Qatar University, Center of Advanced Material, and Dr. Khalid Bani Milham, Qatar University Center of Advanced Material. Dr. Shane, the floor is yours.
Thank you, Ms. Noor. Good afternoon, all speakers for afternoon section. We have a nice talk in the early morning. Continuously, we hosted some distinguished lectures with 8 topics, where we have 2 keynote speakers and 6 invited talks. We want to start with first speaker, Jack Lawrence Morales, but he is not attending yet, so we have some modified schedule by switching Ahmed Abdel Wahab, Professor Ahmed Abdel Wahab. So I want to introduce Dr. Ahmed Abdel Wahab for the first keynote speakers. Professor Ahmed Abdel Wahab is a professor of chemical engineering at Texas A&M University, Qatar, Doha, Qatar, and a professor, a joint appointment of civil environmental engineering and Texas A&M University, College Station, main campus, USA. Professor Abdel Wahab's research primarily focusing on electrochemical, photochemical, and physical process associated with environmental and energy conversion applications. This work includes electrochemical water splitting, engineered osmosis for desalination, for osmotic energy extraction, and advanced oxidation and reduction process for treatment of water and wastewater. Professor Abdel Wahab has published more than 150 peer-reviewed articles in leading research journals and 10 book chapters and more than 120 conference publications and presentations. He is the editor board member of the Journal of Water Process Engineering and associate editor of Emergent Material Journal. He is the co-founder and technical director of the Qatar Sustainable Water Energy Utilization Initiative, and Professor Abdel Wahab has received several awards for his scholarly activities and contributions. We want to welcome to Dr. Abdel Wahab for his first keynote speech in the afternoon section. Dr. Abdel Wahab, are you ready?
Yes, I am.
Yes. Can you share your screen first? Yeah.
Yes, I will do that. Can you see the screen now?
Yes, you can make, yeah. Perfect. Thank you.
Great. Thank you. Let me just minimize this video. Yes. Thank you very much, Dr. Han, for the kind introduction and for inviting me to be part of this conference. And so today I will talk about energy recovery from hypersaline water sources using engineered osmosis. So it's mainly about pressure retarded osmosis, and I would like to mention first that this project was a collaborative effort between Texas A&M University at Qatar and the Global Water Sustainability Center at ConocoPhillips, led by Dr. Samer Adham, and also the University of Technology, Sydney. And this project was funded jointly between Qatar National Research Fund and the Global Water Sustainability Center. So is it my voice is clear? Everything is fine? If I can go ahead?
Yes, yes.
Okay, great.
Yeah, I can see your pointer. So you use the pointer now, or?
Let me just change.
Yeah. I can see. We can see. Yeah.
Okay, so laser pointer. Yeah. Okay.
Yeah.
Great.
Perfect. We can see laser pointer now.
Sure. Yeah.
Yeah,
So
thank you,
basically here I will give a kind of a more of a high-level overview because there have been actually a good amount of work that has been done in this project, and it's very difficult to go into details in this short time. But the main idea here is to give you an idea about, like the work in general, and also especially for those who are interested to work in pressure retarded osmosis. And so you might want to also have a good idea about the big picture and how, when you scale up things, how things can be different from the lab scale operation. Because in this project, we did both the experimental work in the lab, and also we have done design and optimization of the process if it is to be scaled up, and how to account for the different parameters when you scale up the process. And that's the main thing that I will be talking about today. So we all know that basically the crude oil and natural gas extraction, usually when you extract it, you also extract a lot of water with it. I think you have heard this many times, that for each barrel of oil, you have 3 to 10 barrels of water. And the produced water in the Gulf region, especially the oil-produced water, is actually hypersaline. So it is characterized, but it's very high salinity. You're talking about something between 80 to 2,000 plus 1,000 milligrams, 200 plus 1,000 milligrams per liter, which is very, very high salinity. And this what produced water is problematic in terms of management. So basically, the available options for managing this produced water is re-injection into the formation reservoirs, or you do the deep well injection into the groundwater aquifers, and that's what many industries kind of do now. And or you discharge it into the sea after treatment to meet regulatory disposal limits, or to reuse in oil and gas operation, or for irrigation after also treatment. So the key point here is, in any of these options, you have to do pre-treatment. So you need to pre-treat the produced water before you handle it. And also, if you want to re-inject it into the formation, you have to worry also about the compatibility issue with basically the formation, because when you inject it, this causes some problems with the well due to the scaling and the other issues with especially when you mix it with seawater. So this actually high salinity of the produced water is in a way source of osmotic energy. So basically you can convert this osmotic energy to mechanical energy and produce renewable power from it. The figure here to the right shows basically different water bodies with different salinities. The highest is the Dead Sea, as we know, and the equivalence of in terms of water height. So how is this in terms of potential energy? If you convert it to potential energy, like you construct a dam or something like that. So this is how much basically energy. So it's a huge amount of energy. And here the y-axis here tells you also in terms of kilowatt hour per meter cube. So this is a substantial amount of energy, but how do we harvest this type of energy, the osmotic energy, from this high salinity water? There are many processes that have been explored, but the most promising ones is basically the pressure retarded osmosis and the reverse electrodialysis, with the pressure retarded osmosis has been studied the most. So what is the main idea of the pressure retarded osmosis? As you can see to the right here, it's a membrane process. It's just very similar to a desalination process. When you have the membrane unit, is basically have a semi-permeable membrane. And in this case here, you have the hypersaline water, which in this case, we call it draw solution. So the high salinity water, we call it draw solution in the process, and the low salinity water is called the feed solution. So here, what you do is you pair your hypersaline water with a low salinity water across semi-permeable membrane. And the main idea, I'm going to go to the next slide here. So this is the osmotic process. So, excuse me. So if you look at the unit here, which is the pressure retarded osmosis, so this is the hypersaline water coming from one side, and then you have low salinity water coming from the other side. And due to the salinity difference, because the low salinity water has a higher chemical potential than the hypersaline water. So what happens is, due to the difference in chemical potential, so pure water basically permeates through these membranes to the draw solution side. And then you apply pressure here in the draw solution side in order to recover power after it's the exit stream here. So we know that the energy is either B delta V or V delta B. So the main idea here is basically you have increased volume in this compartment here and the pressure is high. So you recover this energy as in the form of, like you convert it to mechanical energy using a turbine and then generator if you want to convert it to electrical energy. So the main idea is, as I said, so the pressure tied osmosis is not much different in terms of concept than the forward osmosis and the reverse osmosis. The forward osmosis is a natural process. So the water flow from the freshwater stream, or from the low salinity water to the high salinity water here. And reverse osmosis, so basically apply pressure on this side to reverse the flow. And that's a flux. So when you have forward osmosis here, and then as you apply pressure, then the flux can be reversed to the other direction, and that's the pressure that you apply when you have reverse osmosis. Pressure tied osmosis is here. Basically, if you keep applying pressure, so why do we apply pressure? Because again, as I said, the work is the pressure times the change of volume which coming from the permeate of the membrane here, and this is the flux. So the flux, if you multiply the flux by basically the area, it gives you the mass flow rate into this way here, which is the delta V dot. So you multiply the delta B or the pressure with the delta V, it gives you the power you want. And this is the power density equation, as I mentioned. So it is the flux times the change of pressure. So you want to maximize this power that you get out of the membrane when you depressurize this stream. And if you use this equation and do the derivative of the power with respect to the pressure, so this is the power here. And then you get the maximum power when the pressure equals to half of the osmotic pressure. So that's when that tells you also how much pressure will be an optimum pressure. But this is in an ideal situation when you have ideal membranes, ideal everything, and we know that there is nothing ideal. So this basically this depends on the Gibbs free energy of mixing when you have ideal system. Ideal system means that you have perfectly selective membranes, which means that the membrane allows passage only for the water from the feed side to the draw side, and there is no salt is actually transported, but this is not true. We always have salts that is actually leak. We have reverse salt flux going into the other direction from the draw solution. The other assumption, when you have this, you're assuming also that there are perfect mixing. So which means that the concentration at the surface of the membrane is the same as the concentration of the bulk. But again, this is not the case. And excuse me. So in the membranes, as we'll see in the next slide, the concentration at the surface of the membrane is totally different than the concentration in the bulk. So all of this creates several challenges to applying the pressure retarded osmosis for energy recovery from the hypersaline produced water. One of them, for example, when we have very high salinity water, this means, as I mentioned, the applied pressure is half of the osmotic pressure, and you would like to maximize this applied pressure to be here somewhere. And this usually, when I have very high salinity, you can't get it here because, again, the pressure here is basically above the pressure that the membranes can handle. But you would like to have, to maximize the pressure as much as you can, which means that you need to manufacture membranes with high mechanical strength so you can recover as much energy as you want. Another challenge is the source of the feed water here, because as I mentioned, you have draw solution and also you have a feed solution that you need to use in order to basically recover the energy from this high saline solution. And in many cases, previously people have been using river water, and actually this is how it started the BRO idea, when people try to combine river water and seawater. And but the fresh water is not available in the Gulf region. It's in Qatar and in the other regions here, we don't have much fresh water. Some people also have tried to use treated sewage effluent. And the issue here also is that treated sewage effluent is a valuable product for us. It's also, it's a very valuable resource that has been used for irrigation and for district cooling and other purposes. But the good thing is, because of the very high salinity of the produced water, you can use another saline water, but still keep very good pressure or osmotic pressure difference between the two streams. Examples is the seawater, for example. So we can use the seawater, pair it with the produced water, and you can still get very high osmotic pressure difference. Also, you can use the brackish groundwater, which is not very usable without desalination. Or you can use the brine from either groundwater desalination or seawater desalination will still be. So if you talk about the brine, for example, is about 70 grams per liter. You have the produced water is about 150 to 200 grams per liter. This is still very high difference in terms of osmotic pressure. Another big issue is the membrane fouling and the concentration polarization, because again, we were talking about very complex water systems here. We know that I mentioned before that this water has to be treated no matter what you want to do with it, but still, even after pre-treatment, you still have, like this water is aggressive and it harm the membranes, and you would like to have membranes that are basically tolerant to these types of waters. So here's the slide summarize the major issues and how we basically how they affect the membrane performance and how this can affect also the equation for the flux. So the first thing is what we call the internal concentration polarization, and that's, as many of you know, that this is related mainly to the support layer and the concentration, the accumulation of salts close to the membrane surface, and also the resistance of the support layer here. And this mainly depends on the thickness of the support layers, depends on the toxicity, depends on the porosity of the support layer here, which give you the concentration here higher than the concentration in the bulk. And the other thing is the external concentration polarization, which is mainly related to the diffusion layer here, and this depends on the thickness of the diffusion layer at the raw solution side, and this results in the concentration here at the surface is lower than the concentration here. So in reality, instead of getting this much difference of the osmotic pressure or the concentration that gives you osmotic pressure, you get a smaller difference, which is this one. And that's greatly affects the performance of membranes. The other issue we have is mainly the reverse salt solute flux, which is mainly the leakage of the salts from the draw side to the feed side here. So all of these parameters or all of these factors affect greatly the water permeability and have to be incorporated somehow into the mass transport equation, which is the flux equation here. And Elmelik's group about 10 years ago or so, they developed or they were able to incorporate these by developing this complex equation here, which is basically incorporating all of these parameters and all of these effects into the equation, and mainly to relate what's happening here at the surface of the membranes with the concentration of the bulk, because we know the concentration of the bulk, and then you need to relate these concentrations to what's going on and be able to do accurate prediction of the flux if you would like to design a process and scale it up. And also the same thing for the reverse solute flux here in the other direction. So that's how to basically account for these limitations, and also part of the project in order to address all of these issues in terms of internal concentration, polarization, and fouling. And I forgot to mention here that for this, you would like to minimize. So this parameter S, which is the structure parameter, is the parameter that is in actually account for the internal concentration polarization. The higher the S, the higher the internal concentration polarization. So you want to minimize S, you want to also minimize the B, which is mainly the reverse solute flux here. And with the help of our collaborators from the University of Technology, Sydney, I'm going to go through the membranes that were manufactured and utilized in this project very quickly, because this is not the main topic of the presentation today. The presentation today is mainly about the process design and optimization and the cost analysis for this. So, but I will go quickly through this in the next minute or so. So again, we want to maximize A, minimize B, minimize S. So our colleagues from the University of Technology Sydney, they actually manufacture two types of membranes. One is a flat sheet that is basically all of them based on the thin film composite membrane. So this one here was basically the active layer was incorporated with the melamine-based covalent organic framework, and this enhanced it greatly actually the flux, and also reduced the structural parameter. For example, this is the TFC without any incorporation is 4330. This is 240 here with incorporation, which is a great improvement. And the water flux also was improved. The solute, the reverse solute flux was a little bit basically, or the salt rejection was a little bit lower than this one, but this is also the difference here is not significant. So again, the main goal, as I mentioned before, you would like to maximize the pressure that the membrane can withstand. At the same time, you would like to maximize the water flux as well. And that's what we are seeing here. So basically, the water flux is enhanced with, when you optimize the incorporation process, we are being able also to reach high pressure, which exceeds the 25 bars. And this shows the power densities that you can recover. The optimum power density here reaches 12 watt per meter square, which is actually a great accomplishment. Also, again, as I mentioned, our colleagues, they manufactured also hollow fiber membranes, and we tested them here in our lab. The pressure, it's not as high as the flat sheet, but the flux was high, so we got also very good power density from these, which was actually, again, we have the support layer incorporated with the graphene oxide in order to increase the hydrophilicity and also enhance the membrane porosity and selectivity as well. So we tested, as I mentioned, we tested these membranes, we tested the performance of them, we tested also commercial membranes towards, kind of finding the operating and optimizing the operating parameters, and develop also design parameters for scaling up that we can use them in our design model. And we use, these are the units that was actually installed in ThermoQ, and this is the unit also at the Global Water Sustainability in ConocoPhillips. And also we used the osmometer here in order to measure the osmotic pressure that we also used to optimize the parameters for the equation of state, for the osmotic pressure equation. That's the main thing that I want to talk about here, which is the process design and optimization, because there have been a lot of work going on in the lab. So there have been great research efforts in order to design and develop membranes for BRO, in order also to test these membranes for BRO at the lab scale. But when you do things at the lab scale, doesn't necessarily mean that you get the same when you scale up things. I'll tell you just a couple of the things that basically are much different here. So for example, when you have an equation like that, this is very complex equation, and you would like to design the membrane or the BRO process and for scaling up, then this becomes very nonlinear. So what people try to do in order to be able to calculate the flux or estimate the flux is use a very simple thermodynamic equation, which is the Van Hoff equation. And sometimes you just assume an ideal solution, which is basically does not give you an accurate prediction of the osmotic pressure. Another thing another big difference between the lab scale and the full scale. In the lab scale, we use small area membranes, and this doesn't actually make much difference in terms of dilution effects. But when you look at the large scale, if you look at the full scale planet, we know that when the draw solution going from this direction here from in to out, and the feed solution going from in to out here, there is dilution of the dilute or the draw solution, and there is an increase in concentration of the feed solution. But how to account for this difference? Because the driving force becomes different from one point to another here, and this has to be accounted for, because the flux depends on the osmotic pressure difference between the two sides, and the osmotic pressure change along the membrane lengths. This doesn't make much difference in the lab scale, but when you try to scale this up, it makes a big difference. So accounting for this is not an easy process, especially when you use a nonlinear model like that. So what we did is first we addressed the thermodynamic issue. We would like to use an accurate thermodynamic model in order to be able to accurately predict the osmotic pressure difference. And we have tested equations of state that have been developed in-house by Dr. Marcelo Castells and his team, and one of them is the Q electrolysis, and the other one we call the ESAFT equation of state. And this equation of state was mainly done for electrolyte solutions, so it's very suitable to be used here. So we tested these different equation of state against the Van Hoff equation of state and also the ideal solution model. You can see here. So basically the dots here are the experimental data, and in all of these, so these are different salts, that's sodium chloride, potassium chloride, and so on. And as you can see, so this the ESAFT model and the Q electrolytes model that was in-house developed, and this is the Van Hoff equation, and this is the ideal solution. You can see that our models fits very well the experimental data for all the salts that are of concern in produced water and also in the seawater. Right. It's also interesting to notice here that the Van Hoff equation is basically over predicts when you have low salinity and under predicts when you have high salinity here. And this will be also be shown when we predict the performance of the membranes later on. Also, to account for the dilution effects across the lengths of the membranes, we discretize the membrane unit, as you can see it like that, and so to a number of units. So each of these units act as a membrane by itself, and to decide how many slices you need, we did also sensitivity analysis to see, you know, like when do we reach the net difference of the energy, that is basically the energy produced that is less than 0.1%. And that's, for example, an example of 5 slides here that were enough in order to do that, right? So, and then we had to basically use the finite difference method, and as you can see here, you know, the input from one stream is the exit from the other, and so on. So this has been done in a sophisticated way. Other thing that we had to worry about is, you know, like as I mentioned, when you use flat sheet and you increase the pressure, the problem with that is this affects the structure parameter because it's create a compaction. So high pressure makes the membranes compacted, and when you compact the membranes, this also compacts the support layer, and then the structure parameter is affected. In many studies before, they just assume constant structure parameter, but we accounted for the increase of the structure parameter as you increase the pressure, and we incorporated this in our simulation model. The first thing we have done is, after we developed the simulator for, this is only for the membrane area for now. So after we developed the model, the mass transport model, combine it with the thermodynamic model for the streams in and out of the membranes, we validated these results against previously experimental data and other models at the lab scale that has been done by others. So this calibration and validation has done using the lab scale data that have been reported by others in the literature. As you can see, it's actually very good agreement between our model and the experimental data that people have found, which give us good confidence in terms of, you know, like scaling up later on. Then we compared the prediction of our model with basically at the full scale now, when we do the discretizing, when we account for the dilution effects. And as you can see it in here, like this is a difference, for example, between the Van Hoff equation and the Q electrolysis equation. As you can see, when we have seawater, river water, that's a low salinity streams, you get the Van Hoff, again, over predicts. When you have the produced water, seawater streams, which is of our interest, you get the Van Hoff equation under predicts the performance. And this is actually obvious here because this is, again, this what is shown here as well. Okay. Then we, after we developed the model, we tested it, we basically compared, and then we used it to predict now. So this is actually the full scale for give you a comparison between the co-current flow and the counter-current flow. And it's interesting here when you see the difference between the co-current and the counter-current. So the co-current actually is very, give you a high driving force, which is, again, the driving force is mainly the delta pi minus delta B. So it gives you a high driving force in the beginning, but as you actually increase the membrane area, then the counter-current will be more effective and give you better driving force here. And this is logic. This is similar to what you have usually in heat exchangers. it's the same concept, because when you have counter current, the driving force maximized all over the membrane area. Because as you dilute the draw solution here, the feed solution is also very dilute here at the entrance. So that was very nice to see. And then we, excuse me, then we went to do the optimization of the full-scale planet. Now we're not talking only about membranes. So the previous work and the previous results that I presented was mainly about the membrane here. So with how, to predict things at the membrane unit level. But now we're talking about a full-scale planet, which has turbines that generates the power, and it has the pumps that needs to increase the pressure here for the draw solution. It has the pressure exchanger, because what happens is basically you have the draw solution going through the membrane, the volume increased by the permeation of the feed solution here, and then you take half of this, usually it's half, you take it and use it to increase the pressure of the draw solution coming, so you can save some of the power that you need for the boosting pump here, and then the half or the remaining will be used to generate power here. So in here, we accounted for all of these units and towards the scaling up and predicting the cost of the full scale planet. So basically, the optimized parameter was the area of the membrane, the draw and feed rate, the operating pressure, and the objective function is the power density and the specific energy, in order to maximize the power density in some cases, and in some cases to maximize the specific energy. And I will tell you the difference in a minute. And then the parameter range for the area from 30 to 100 meters square, operating pressure from 2 to 50 bars, and then the phi is 0.2 to 8. Phi is mainly the ratio, it's between the streams. So it's a feed stream divided by the feed plus the draw stream. That's how the terminology is. And then we used ideal systems by 100% efficiencies. And then we used also efficiencies of the turbine and the pressure exchangers to be 85% for the pumps and turbines, based on what was reported in the literature, and 95% for the pressure exchanger. And then we assumed costs for the pre-treatment of both the produced water and seawater, based also on available data that we have. Okay, Dr. Shane, how much time I left?
You are supposed to have 20 minutes more.
Oh, okay. So we're doing great.
Yeah.
So I don't need 20 minutes, but
take it easy.
Okay.
Okay.
Okay. Yeah. So here these are the equipment models we have. We accounted for all streams in terms of input and output, in terms of mass and energy as well. So enthalpies, entropies, and so on. So this is just the regular energy balance equation. This is the entropy balance equation that we have done for each stream. And what we have done in the beginning, in order to initiate the simulation, you need to have input, you need to guess some input parameters in the beginning, and then basically optimize or fix them later on. So what we have done, we assumed basically adiabatic system and isentropic system, so that basically for the pumps and turbines, so the difference in entropy is 0, and this helps us to guess an initial temperature, and then we use this initial temperature to get the enthalpies for each streams, and then calculate the work, and then after that we accounted for the assumption for the isentropic assumption by reducing the assumption for isentropic, and let basically the simulator and the equation of state and the energy balance to account for the parameters accurately. And then again, the pump efficiency and the turbine efficiency have been also used in order to calculate the actual work when you don't assume ideal systems. The pressure exchangers was a little bit more sophisticated, because here we have basically pressurization and depressurization, and you have also substantial or considerable entropy generation in the process. And we also, again, we assumed an efficiency of the pressure exchanger from one side, and then the heat that is produced was calculated based on the difference in efficiency on the other side, and then the entropy generation was calculated accordingly, and properties of streams were estimated. And after all of this, then we run the model to predict the energetic properties here. So here you see the specific energy versus power density. And this is an interesting, to see, because as you can see here that the power density is, again, it's the power produced per meter square of the membrane area. A specific energy, it is the energy produced per meter cube of feed and draw together. And as you can see, but if you want to increase the power density, you decrease the specific energy. And this is in a way operating versus capital to some extent. So with the power density here, as you increase the power density, the problem with that is that you basically increase the area, and then what happens is that you get more dilution effects into the equation here. And this affects the specific energy, because you reduce, when you increase the power density, you increase the pumping cost, you increase the flow rates into the process. And when you increase the flow rates, then you increase the pumping cost to the system. When you increase the pumping cost, what happens is you basically add more energy to the system than you get, and that results in, again, decreasing the specific energy by increasing the power density here. So the good thing about the simulator is that we are able to optimize things. So we actually used it to find what would be the optimum then. So if you decrease the power density when you increase the specific energy, and vice versa, what would be an optimum situation if you would like to, for example, to get the power density around, like what basically was reported in the literature as an acceptable power density for cost-effective BRO, and what would be the optimum area that gives you this. And as you can see in here, so the purple here is mainly the specific energy, the blue is the power density, and you can see in this area, around this area here, that's a suitable area that you can actually operate at here. Then we extended this because in reality, if you want to scale up, you don't use flat sheet. Most of the time you use a spiral wand, and that's what is being used in RO and now in FO. And you should be also to account for the difference. And if you would like to use a spiral wand, then you should be able to predict the performance of a spiral kind of wand membrane. And that's what we did that. And one of our students, Salimata, she actually did this by modeling the challenge here. When you model the spiral wand is just a flat sheet that is folded, as you can see in here. But for the BRO is mainly, and for the FO it's similar, you have what we call is the glue line here. Glue line because the feed comes in here, so it comes in this direction and then it goes around like that, so it then comes out from this direction. So the whole membrane area or the flow, the feed flow can flow through the whole membrane area, and then the draw go from that side perpendicular to the direction of the feed flow. And how to discretize the membranes to account for this, and what would gonna be the effect of the glue line. And because as you can see here, some of the elements here that are rectangulars, but some of them are triangle, and even the triangle, some of them are basically ends and some of them are outs. So, but we did that. We were able to discretize the same way, and with different lengths of the glue lines. So first we did 25% in terms of the membrane length, 50%, 75%, and we also evaluated the effect of the glue line lengths on the performance of the membranes. So, and this we also were able to calibrate also the model. As you can see, this some experimental data. We couldn't find much experimental data for BRO using spiral wand, because there is not commercial level now, or commercial planets that are actually operating on spiral wound kind of BRO. But we were able to find some data from, I think, from a pilot planet that actually has been constructed recently. And we calibrated with our model, so this gives us good, basically, agreement with the experimental data here. What is interesting is, if you look at here, so these are the predictions of the model. So this one here is mainly for co-current, and this one for counter current when you do flat sheet, right? So for the first osmosis, there's no co-current and flat current, and counter current. But for the flat sheet, there is. So these are the previous data from the counter current and co-current, and you can see that the spiral is somewhere in between, because again, the spiral has the effects of both the co-current and the counter current. As you see, the flow is perpendicular, the draw is perpendicular to the feed flow rate. Here also, you see that we predicted the pattern of the flow field across the membrane. So this was done for the draw side, and here basically was done for the feed inlet. So the feed, you can see the feed here is getting more concentrated. So this is high concentration, low concentration, and also you can see how the draw is diluted as it goes through this kind of path here, right? We also tested the effect of the length of the glue line here. So it's like this is 50% glue line, this is 75% glue line, and we found that actually the minimum glue line is the 25. We didn't test it before 25, but we found that 25 gives the best performance out of all of them. Then we come to the techno-economic analysis. After we are confident that we can scale this up, we can predict things at the full scale with reasonable confidence. Then we incorporated into the model or into the simulator the cost then. And we accounted for the cost as the levelized cost of electricity. And as you can see in here, and this is a cost item that is used for different renewable energy terms to produce electricity. And as you can see here, so there in our process, we have costs and we have revenues. So basically the costs coming from the capital and operating, coming from the pumps and turbines, coming from the pressure exchangers, coming from the membranes, from the materials, and from the pre-treatment, chemicals for pre-treatment, for the membrane replacement, for the labor and maintenance. And then the parameters that affect the revenue or affect the energy produced are the volumetric flow rates, the draw and the feed, the membrane also area affects, the hydraulic pressure, the applied pressure, the stream salinities also affect both. This gives you also an idea about how the pressure, the applied pressure can affect the net power production and affect the LCOE, or the levelized cost of electricity here. You can see that the optimum power density, or the highest power density, it's not at the same pressure at the lowest cost of the electricity here. And that's actually interesting, because you expect when you maximize the power density, you minimize also the cost of electricity. But this is not the case. Power density, it gives you an indication of what you can achieve at the membrane level. And that's why I said before, it's very different when you do things at the lab level and try to scale them up. So the power density give you around the membrane unit, but when you consider, still considering the energetic cost, when you consider the materials and stuff like that. And by the way, we used costs what they have been there. Again, as I mentioned, there is no large scale plans available for BRO, but the equipment are very much similar to the RO. So we used actual data from full scale planets in RO units in terms of the, like the modules, and in terms of the pumping and all of these, the capital, the labor, and all of these kind of costs, and incorporated them into the model here. So we have seen that the least or the lowest cost of electricity when you have a pressure of 25 bars. So no matter how you would like to, basically, you can increase the pressure too much. But again, this does not mean that you will reduce the cost. That's the message that I would like to say here. So here also, if we did a comparison with other energy costs. So these are different types of renewable energy: the hydro, the offshore, the onshore wind, the biomass, the solar PV, and geothermal, and so on, using the reported data from the ARENA 2019. And as you can see it in here, that basically, so this is the BRO results with 100% efficiency of pumps and turbines, which is, again, this usually doesn't happen. You always have efficiency issues. But again, it comes here. It comes after the hydro, the solar PV, and comes after that the geothermal and offshore wind. When we account for so this is also with ideal membranes, by the way. Which again, this is not very logical. When we account for the current membranes, accounting for the structural parameters that for the available membranes, but still use 100% efficiency of the pumps and turbines, we get it to here, which is after all of these, and only the CSBS is CSB, which is a concentrated solar power, is after that. When we accounted for the pump efficiency was 85%, the turbine efficiency was 90%, it actually did not compete with any of the other renewable energy processes. Saying that doesn't mean that the BRO is not a viable process, but again, it still needs more work and more research effort in order to enhance the performance of the membranes. And also, basically, if I look here, for example, at the ARENA results in 2010, and when the solar energy was more expensive and other renewable energy costs was more before more technology advancement in these technologies, we can actually be here. We can be up if you compare at that time, which means that, like technologies start at high cost, but then with more advancement, the cost can be significantly reduced. The challenge here with the BRO is the continuous, if you want to use it for power generation, with the continuous decrease of electricity coming from solar, it's difficult to compete. So the BRO will be difficult to compete because the electricity coming from solar energy is becoming very cheap now. And it's difficult for something like BRO to compete if you want to use it for power generation. However, there are other niche applications for the pressure tide osmosis that can be very useful, which is mainly one example that here that actually was evaluated by our colleagues at Global Water Sustainability, ConocoPhillips, is basically when you integrate this with enhanced oil recovery, because in this case, you don't produce power. You don't need to produce power. When you don't need to produce power, then you avoid some of the efficiencies of some of the equipments like turbines and stuff like that. So one here is to integrate it with the enhanced oil recovery, because you need high pressure when you inject basically the water for enhanced oil recovery. That's one advantage. So you get increase the pressure, but at the same time also you do, usually when you do enhanced oil recovery, you have the produced water, you mix it with seawater. But then there is a compatibility issue here when you mix produced water with seawater. Here we are not mixing with seawater, but you are actually filtering the seawater through the membrane. So what is transported here is basically pure water. So you increase the volume of the injected water stream without affecting the quality of the water much. So you avoid the compatibility issue here. So our colleagues, they found that by BRO reduces the water flooding pumping, can reduce the water flooding pumping energy by about 38%. So finally, I would like to conclude by saying that a planet scale simulator was actually developed and accurately account for the mass transfer and thermodynamic properties. We actually developed parameters for the bench scale experiments, and we have seen that these parameters, they cannot be used directly to predict the performance of the full scale. And then you have to use sophisticated models and in order to be able to account for the full scale in terms of dilution effects, in terms also of the osmotic pressure difference between the two sides of the membrane. We also have seen that increasing operating pressure can affect membrane's characteristics, like we have seen in the structure parameter basically was affected by increasing the pressure. We found also that counter current flow pattern results in higher driving force in membranes, and also the cost evaluation indicated that the BRO is currently not cost competitive with other renewable energy sources for power production if you use it for power production. However, it can be cost effectively applied for other applications such as in oil and gas operations, such as water flooding in oil and gas operations, for example. Finally, I would like to acknowledge and thank Qatar National Research Fund for supporting this project, and also the Global Sustainability Center for being collaborators and also co-funders for the project as well. It has been actually very nice working with them, and the work has been very productive as actually I've shown you in the previous slides. So this is the project team from different, I'm not going to go through the names, but basically from Texas A&M University, from Global Water Sustainability Center, from University of Technology, Cindy, led by Dr. Sean from there. So that's all I have. This is just a photo of the team who were involved in the project. And by this, I will end my presentation. I would like to thank you all very much for your attention. And thanks again, Dr. Shane, for giving me this opportunity to talk to the audience today. Thank you.
Thank you so much, Dr. Wah. It's very nice, instructive presentation regarding the utilization the produced water to generate the power. We want to have time to have a question from audience. Is there any question from audience? Okay, waiting for some question from audience. I have some question about your presentation. When you look at your modeling data and experimental condition to be applied the pressure in draw solution side, you're going to apply 2 to 50 bar. So also even in the techno economy analysis, the overall LCOE increased exponentially more than 50 bar. So
right.
Yes, to minimize external concentric polarization in PRO membrane consisting of two structures. Yeah. So
yeah,
I don't understand well. So based on my knowledge to see your presentation, it's kind of the two structure layer. Yeah. So how can you sustainably resist the support that kind of apply the pressure more than 50 bar? So is there any?
Yeah, that's a very good point. No, you can't. That's again, that's to say. I mean, as I mentioned before, like membranes cannot withstand this high pressure. The data showed like you can withstand high pressure up to 20 bars or so. When we did the simulation, we are saying, what if? When you try to scale up, even if you are able to reach to this pressure, like you're not getting economically, you know what I'm saying? It's basically, it's more of what if scenario than the actual situation. As I mentioned, the actual situation, you usually 20-25 bars. That's what the BRO, that's what you can operate. And that's what we did experimentally. That's what we tested experimentally. When you come to the cost, we and when we did the simulation also, we ranged the pressure up to 50 bar maximum, if you remember that. But when you do the calculation of the cost, we assumed many things to just say, well, even if you do that, you get cost competitive. And even we assumed 100% efficiency of the pumps and turbines. We assumed 100% efficiency of the membrane. So we assume that the structure parameter is at the minimum. We assume everything at the minimum. And we still, with all of these, we still didn't get the PRO to be competitive with other technologies. Do you know what I'm trying to say? Yeah, yeah.
Yes.
Yeah. So
And
it is hypothetical. It's mainly hypothetical, not real pressure that we are talking about. Yeah.
Yes. I have a question, one more.
Sure, yeah, go ahead.
Last slide is very impressive, directly, throw in and out in the subsurface of the facility for, the oil extraction, where you don't use anymore the pressure exchanger to increase the oil, benefit. But major, as you know, major issue, to treat, some residual oil droplet in the produced
Yes.
water. So, but here, so what do you have any plan we keep the environment, the subsurface environment, but is direct pressure, using the direct pressure, they're gonna be moved to the subsurface environment. A very good idea. But how about the treatment of residual oil droplet? But it will be dilute, but that has also keep the oil
Right.
droplet. Yeah.
Yeah, I mean that's true. You always have the pre-treatment issue that you need to account for, and this was actually when they again this model was developed, or this actually was developed by our colleagues in global, this in specific application, and they accounted for the treatment of the produced water and the seawater. So the treatment was accounted for, and actually there was, but I didn't present this today, there was actually experimental work that also accounted for removal of impurities from actual produced water. So we got produced water from an oil field that is run by ConocoPhillips colleagues, and we did basically treatment processes using coagulation and flotation, and we evaluated different treatment processes. So you need to treat the water for the things that basically harm the membranes before you re-inject.
Anyway, it's very impressive and very good idea that directly use the dilute the total solution of the produced water to inject the subsurface environment. Thank you very much, Dr. Wap. Yes, it's very interesting time. And if you have, if any audience have a question about Dr. presentation, you can leave the message while listening to the following the speaker. Maybe I believe that Dr. will leave some comment on your question in our platform message.
Sure, it will be my pleasure to answer any questions later.
Yes.
Thank you all. Thanks for your attention. Thanks, Dr. Han, again for the opportunity.
Yes. Thanks again.
Thank you.
Professor Shane, we cannot hear you.
Yes, sorry. Thank you. Sorry about that. Jung-Bin Kim is a postdoctoral researcher at Korea University. He graduated with both a bachelor degree and PhD degree from Korea University in 2016 and 2021, respectively. His research focused on the development of energy efficient seawater reverse osmosis desalination process. He has published 11 journal articles in the field of chemical engineering and one book chapter regarding the reverse osmosis membrane processes. Based on his active research, he has received 10 awards related to desalination and membrane processes. Moreover, he holds 14 domestic and international patents. One of the patents was transferred to a company amount more than $50,000 US. Furthermore, in 2019 to 2022, he is a committee member of the International Desalination Association, IDA, Young Leaders Program in the Asia Pacific region. From 2022, he also became a member of the International
Water Association, Young Water Professional, Korean chapter. Also, he recently appointed Young, the board member in Desalination Journal. Dr. Jung Bin Kim, are you ready?
Yes, I'm ready, and thank you
Yeah.
very much for a great introduction. And I hope like you enjoy this webinar, and I also very amazed with the previous presentation. So I need to do well this time. So I'm Jung Bin Kim, a postdoctoral researcher at Korea University. And in this presentation, I'll present future energy efficient SWRO desalination process for sustainable water production. Because this topic is related with SDG goals 3 and 6. This green one is related with SDG 3, and the blue one is regarding the SDG 6. So this presentation, I will present the trends in SWRO desalination application in Arabian Gulf, and then the single-pass SWRO for energy efficient desalination, and two-stage SWRO for sustainable desalination, and the summary. So as you well know, the SWRO application has been dramatically increasing after 2000, and there was a significant energy reduction by the application of ERD. However, in the region of Arabian Gulf, thermal desalination was dominant because of the extreme seawater conditions and then cogeneration with power plant. But with the advancement in ERD, its SWRO application has been increased even in the Arabian Gulf region. So this is the profile of the SWRO desalination plant in the Arabian Gulf. But compared to other regions, these plants consume higher energy because of the high TDS feed condition, which leading to high pressure operation. And also they require energy intensive pretreatment processes. And also because of the high feed TDS, they need to produce clear water by using second pass RO. Because of this one, this region consume high energy consumption compared to other region. So this is the supporting document, as you can see. So in the Gulf of the Oman, its TDS is about less than 40,000 milligram per liter. However, after the Strait of the Hormuz, its TDS is going up to 42,000 milligram per liter. So like Northern Emirates, they were fed with TDS of 42,000 milligram per liter. And then the end of the Arabian Gulf is about 45,000 milligram per liter because of some inflow from the river. And the inland part of the Arabian Gulf, actually the TDS is pretty high, and it's reported to about 46,000 milligram per liter. And in summer season or some shallow area, it reached to 48,000 or higher than 50 milligram per liter. So this is very high salinity, and it's not really the favorable for SWRO application. At the same time, compared to Red Sea, Arabian Gulf has some oily material and some argon contents, so they utilize DAF for protecting their RO system. So its energy consumption is inevitably higher than other regions. And there are many ways to reduce the energy consumption, but because of the factors in RO system is higher than other factors, it is important to focus on the RO system to lower the energy consumption of SWRO desalination plant. So after we analyze several practical energy consumption, we conclude that it is more important to focus on the process optimization and development for the RO system to reduce the energy consumption. And by the theoretical analysis, we found that this was impactful, and then we need to focus on RO system development. So for this presentation, I will present like this. So first of all, I will explain our application of high performance SWRO membrane, and also we will share some experiences to optimize and development RO system for the current system. And then as the word require, we are focusing on some future practice for SWRO desalination, which is increasing the high recovery. So we are optimizing and developing two-stage RO system to increase the recovery, to reduce the amount of the brine discharge. And also we suggest some like needs for advanced SWRO and PRO membrane for the brine management system. So this presentation will cover all RO system development or like other effort done by the Korea University research. So the first one is single pass SWRO for energy efficient desalination. And in this section, we will provide some application of high performance SWRO membrane. Because like, as you know, Arabian Gulf region are using SWRO desalination much, but still because of the high TDS, SWRO application is still limited. Therefore, Korean government want to develop like SWRO technology to win the market in the Arabian Gulf region. So we developed new SWRO membrane and energy saving algae response pretreatment and also low energy future technology for replacing second pass RO. So we established a pilot plant and demonstrated that it will consume less than 3.3 when we compare it to large scale desalination plant. So this is the pilot plant that we constructed in Abu Dhabi, and Korea University coordinate all these projects, and Daewoo Construction, which is the largest construction company in Korea, they constructed, and the K-Water, Korea water utility operate this pilot plant. And we have some different pretreatment system and then UF system, and then the new SWRO membrane developed by Korean membrane company LG, and there is a BW, RO, and CDI system as well. So the plant was constructed in Abu Dhabi, and we apply the advanced SWRO membrane in the world. So because this SWRO membrane has high salt rejection and high flow rate, we can produce high quality water even though the TDS is high. And we can operate the system with lower pressure considering its high TDS condition. So this is the basic approach that we apply this membrane, and the operation results also show very promising. So the feed salinity in the Arabian Gulf region was higher than 50,000 milligram per liter during the summer season, but its pressure was less than 70 bar. So it was maintaining for like after 3 months. So it was quite promising. And the permeate quality was about like 300 milligram per liter, even though the TDS is pretty high. So which cannot be achieved by the other commercial SWRO membrane. So as you can see, the development of SWRO membrane will lower the energy consumption of SWRO system and also reduce the size of the BWRO system. Therefore, it will leading to the reduction of whole SWRO system. So this is one of the research that we done by Korea University as well. And then with the research perspective, we developed and optimized several SWRO configuration as well. So this is the commercial SWRO configuration, which it can be single pass or second pass RO. And there is some design approach, which is ISD, which combine different types of membrane to get the benefit of SWRO operation. And there is some like three-center design, which increase the pump efficiency to lower the energy consumption of RO system. However, we consider changing the membrane location could be more like practical compared to making new RO system again. So firstly, we optimize the RO system by membrane location. So ISD, as I talked about, this is the design that utilize different types of membrane. So in general, high rejection membrane is located in the front, and then high fluxes membrane is located at the rear part. By doing so, they reduce some like membrane fouling propensity in the front, and they increase the water productivity in the rear part of the RO vessels. However, this kind of ISD design should be optimized based on the product water quality that require, because using different types of membrane will produce water quality with different like expectation. So based on that, we found that to produce the high quality water, we need to use the high rejection membrane. But to reduce the energy consumption of our system, high flux membrane is not always prepared, because when we utilize a high flux membrane only, our system will be fouled easily. Therefore, the energy consumption after several months will be eventually higher. Therefore, it is very important to mix the membrane composition together, considering its fouling rate and considering its product quality after several months of operation. So we developed such kind of like optimization technology based on the permeate TDS, and depending on the region of the fouling rate, this kind of program will suggest the best membrane composition in ISD. So this research show that for producing high quality water, we need to use the high reaction membrane, but to lower the energy consumption of our system, we need to optimize. We need to use the optimized membrane composition in the end. So that's one of the research. And next, we are focusing on the development of our own process. So in RO vessel, the front element produces high quality water, but the rear element produces high salinity water compared to the front element. Therefore, sometimes split pressure technology is utilized in the two-pass system, where second pass RO is only treat the rear part of the SWRO permeate. By doing so, they can efficiently operate the two-pass system, but two-pass system consume higher energy because of the BWR operation. So we are trying to develop only SWRO operation that produce high quality of the water. So we developed these devices, and technology transfer is done, and we also apply this technology in the US. And this kind of like configuration can be applied like this kind of unit and train design. This design can be effective because this design doesn't utilize the BWRO system. However, with the single pass RO design, we can produce high quality water compared to single pass RO. So for example, in an island, they have very limited land and not enough space for maintenance for SWRO and BWRO together. But by installing only one SWRO membrane, they can produce higher quality water without using BWRO. So this kind of configuration will be more effective when the SWRO membrane is developed, so that when SWRO membrane is producing high quality water compared to the previous like membrane, then this kind of like single pass process can produce more higher quality of water, so that we can save the extra energy for the BWRO system. So for this research, we also suggest some high purity water production, but low energy, low cost single pass system compared to two-pass RO systems. So we see that some company also utilize our idea and also applied in the industry before. So until this part, we say that single pass SWR operation, this is quite important because our membrane is developing time to time. So this kind of research is meaningful when we consider some efficient RO operation. However, recent studies, they require high recovery operation to reduce the volume of the brine discharge. So we also focus on two-stage SWR desalination for sustainable desalination. Actually, in practice, two-stage SWRO is applied to produce high amount of water. So those plants adopting two-stage SWRO, its recovery up to 60%. However, in the theory, like in many studies, they claim that two-stage RO is energy efficient. So there is a disparity between the practice and theory. So in this study, we analyze whether two-stage RO is more energy efficient, and we also investigate what is the proper recovery to operate the two-stage system. So this is the approach that we consider as two-stage RO. And we found that in the recovery less than 45%, single stage is more effective for the water production. However, when the recovery is increased over like 50%, two-stage design is more effective for the water production in terms of energy consumption. And also its design ratio will be considered depending on its like ERD type. So in this study, we found that to increase the recovery, rather than changing the membrane, it is more important to develop two-stage SWRO and optimize the system depending on ERD type. We further study two-stage RO system for the extreme seawater. Because this system is more effective in high recovery, we also think that this system will be more effective in the high feed salinity condition. It will gonna be operated in high recovery, high pressure. So rather than the single stage, two-stage design can increase its recovery even in the high TDS condition. And in high TDS condition, because of the high pressure, water flux of the front membrane is higher compared to other cases. However, because two-stage RO design is applied, the water flux can be distributed in the first and second stage so that the system can be operated more stably. And we also further consider ISD application in two-stage RO design. Okay. Yes, there is some noise. Yes, anyway, we consider it as ISD application as well. And then this kind of mixed design of the ISD and two-stage design can be effective in high recovery operation. And for further application of high recovery and high quality of the quality production, we consider this kind of split pressure concept in two-stage SWRO design as well. So by doing so, we can secure recovery and also stability in RO system operation. And also we optimize the SDC design because of the split pressure design, and we also improve the water quality. So for the future, the world require high recovery, but high quality water production. So we believe this kind of configuration can be adopted in the future SWRO desalination plants. So this is the summary of our research. However, right now, the two-stage SWRO can be limited because of like the limitation of pressure of current SWRO membrane. So there should be some advancement of SWRO and PRO membrane to further increase the recovery of desalination system. So we review membrane development of brine management. So that there are two types of membrane concentrator. One is like RO type membrane concentrator, and the other one is like PRO types of membrane concentrator. And for the brine, for the like CLD or MLD, the membrane of RO membrane should be resistant up to 230 bar, so that the membrane system can effectively reduce the volume of the brine. And for the like kind of like OA RO, such kind of PRO RO types of membrane is actually has high S parameter. So if the S parameter is lower, this kind of system will be operated with higher and lower operating pressure, which can be more effective for like brine management. So this is the summary of my presentation. There was a long story and long topics, so I will summarize each topics as well. So in our study, we focus on some application of high performance SWRO membrane. And through this study, we found that because of the development of SWRO membrane, we need to optimize the current SWRO membrane system as well. And we need to develop some SWRO process to reduce or no use of the BWRO system for reducing further SCC. And at the same time, we need to develop and optimize the two-stage SWRO system to increase the recovery to reduce the discharge of the brine. And at the same time, there should be some development of SWRO and PRO membrane to implement this system without any difficulty in the future. So by doing so, I think we can secure energy efficiency and sustainability in SWRO desalination process. So this is the end of my presentation. And because I'm working in Korea University right now, but I'll be available from next year. So I hope there must be some like future collaboration or like future career development between like Qatar and Korea University as well. And thank you very much for your great attention.
Very nice talk. Thank you very much, Dr. Jeonbin Kim. So we are open the audience, the questions. Is there any question? Please, your raise your hand emoticon. No question. Yeah, Mohammed, Dr. Mohammed, you can ask.
He don't have a microphone. Just you can read the question.
Okay, just hang on, please.
Yeah. Ask, please.
We cannot see your question, so would you mind speaking
So the
about your question?
The question is, challenges are in the design or in the material composition of SWRO.
Yes, right. So can you repeat your question again? The challenges?
In the design or in the material composition of SWRO.
Oh, so for this one, I think both should be considered because SWRO membrane, as we talked about, should be developed further to resistant to high pressure, and also the SWRO membrane has higher salt rejection to produce good quality of the water, because especially the higher market is the Arabian Gulf region, but their like VTDS is getting increased. So there should be some proper rejection membrane for the SWRO. But at the same time, there should be some process development as well. And for the reduction of the brine, there should be also development in SWRO membrane and also PRO membrane, so that we can reduce the amount of the brine and further treat it with some thermal method to reduce the volume of the brine. So based on your question, I think both materials and process should be developed together.
Yes, thank you very much. One more question. You successfully demonstrate with a brief description of the Abu Dhabi the plant installment.
Yes.
Yeah, I believe. Yeah.
Oh,
so
yes.
Your team successfully operate.
Yes.
We highlight more, intensively. I have a question about the outer membrane. This, UAE environment is very harsh, like Qatar. So
Yes.
what kind of the LG Chem applied with which technology, maybe it related to secret? So two way, polymer based or nanotechnology based or by mimetic, the active layer fabrication. Could you tell a little bit?
Yes, thank you very much for a great question. And frankly speaking, I'm not on behalf of the LG Chem, but on behalf of Korean Research Research Group Association. But as long as I know, they adopt some nanotechnology, so that they have a previous model, which is like the yellow one before, but they adopt more like nanotechnology, so they can increase the salt rejection, but flow rate both together it's very difficult to achieve both goals, but they achieve it with these two goals. So that's the membrane they develop, and not only tested in the Middle East country, that's done by us, but also they tested in different types of water, like some in the Spain, and some Asia. So they demonstrated their technology within their expected level. So this kind of high rejection membrane is quite important in Arabian Gulf region, because in the summertime their SWR permeate TDS will be very is poor actually, but with this one we can secure good water quality. So I think this kind of membrane should be developed more, and when the TDS of the physical salinity is higher than right now, we need to develop proper membrane, which is proper for the Arabian Gulf region. Yes, that's what I can say from my side. Yes.
Yes, yeah. Thank you very much for your detailed explanation about my questions. It's not hard time for you, so Korea is now almost 10:30. Thanks again. Yeah. Yes. We gonna move the next speaker, Dr. Dong-Young Kim. So Dr. Dong-Young Kim, he is here. So we modified a little bit our schedule because some presenter is not showing here. So this speaker is gonna be going to the Dr. Dong-Young Kim.
Hello.
Yeah, Dr. Kim is here. Okay. I want to introduce you the bio, but during the introducing, so you can share your presentation materials. Dr. Dong-Young Kim is welcome, and Dr. Dong-Young Kim is Assistant Professor of Chemical Engineering at Qatar University. Before coming to Qatar, he was Assistant Professor at King Fahd Petroleum and Minerals in Saudi Arabia. His research has been focused on membrane filtration and the module design for bioenergy and high-value added product production. He's expanding the scope of work to the systematic understanding of fouling phenomena observed in various membrane process for water and wastewater treatment and biorefinery. Welcome, Dr. Dong-Young Kim again, and it's your time.
Well, thank you for a nice introduction, Dr. Han, and hello everyone. I'd like to talk about application of membrane filtration for microalgae-derived biofuels and chemicals today, and I'm very honored to have my presentation here. So I believe majority of you participating in this event would quite familiar with what renewable energy is, so let's skip that away. But I'd like to start with the discussions, what microalgae is. So basically, microalgae are unicellular microorganisms found in freshwater and marine systems, producing 70% of the oxygen on this planet. Compared to the other types of biomass from previous generations, they grow faster, accumulate higher lipid contents, and doubling time is much shorter. Basically, doing everything similar to the terrestrial plants, with one exception: they live in water. This is a schematic diagram of microalgae-based biofuels and bioproducts production process, starting with cultivation either using open ponds or photobioreactor. These days, combining flue gas from the plants and wastewater with microalgae culture systems are actively investigated to further reduce carbon emissions and pollution control in the effluents. Before the biomass is further processed into fuels and chemicals, here is one thing we have to do: removing water from biomass. Naturally grown algal suspension has the dilute concentration of 0.5 to 1 gram per liter at the beginning. This high water content is one of the major bottlenecks which hinders the commercialization of the microalgae-based products, and there are various unit operations that can be adapted here, usually since usually the harvesting is composed of two steps, primary and secondary. During the primary harvesting, dilute algal suspension is concentrated by 20 to 30 times, and then in the secondary harvesting process, it is further concentrated to be slurry or cake. The final concentration ranges between 100 to 300 gram per liter. And my research is focused on a primary harvesting, and I use the membrane filtration. Among those different membrane module types, I chose hollow fiber membrane for treating high volume of water, since we need to use a module in a very compact size, still provides a high membrane area for high volumetric flow rate. And the hollow fiber membrane module has the highest membrane surface area in the compact system, but it easily suffers from the intensive fouling and low flux, and thus the frequent backwashing process is required. This may escalate the operating cost and requires frequent membrane exchanges compared to the other type of modules. Speaking of algae fouling, around 70 to 90% of them are cakes, deposited particles in a form of gel on the surface of the membrane. Especially in the hollow fiber membrane module, due to its slow linear flow velocity, fouling occurs much severely. Majority of the cases, the flow is laminar, that is not providing enough shear stress to sweep out the foulants during the filtration. The strategy for mitigating fouling is simple: to induce turbulent flow near the membrane surface. But the problem still remains. How? This is a typical cross-flow filtration hollow fiber membrane module that is operated as out-in direction, which means feed flows out, permeate is collected inside. And in the conventional type has the small inlet and outlet ports, allowing only very low volumetric flow rate of the feed. And we modified its design to allow higher volumetric flow rate in HCFV module. So we enlarged the ports for inlet and outlet both, allowing 7 times higher feed flow rate. That means we have to use higher capacity pump. And also we installed the orifice to produce instability of the flow and more desirably hydrodynamic cavitation along with the HCFV module. Both of them allow 7 times higher volumetric feed flow rate. And our major focus, we focused on a turbulent jet module, which is presented at the last figure. Still allows same feed flow rate as the conventional module, but it converts the type of flow into multiple smaller jets. So those conventional type HCFV and HCFV with orifice, we call it HC. Those are control group, and the turbulent jet, which diverts the flow into the radial direction as TJ, and that's our experimental setup, and do some cross-flow filtration experiments. These are the lab scale module that has been employed in our experiments. And the results was kind of interesting, that the conventional module, during almost an hour of an operation, the permeate flux was below 40 as time goes by. Meanwhile, HCFV with orifice maintained its flux almost nearby 150 liter per LMH. That's the permeate flux. And HCFV simply escalated the feed flow rate, maintained its permeate flux in between 110 to 120 at 40 to 50 minutes of filtration time. Surprisingly, the turbulent jet module almost matches up to HCFV module without escalating or changing the pump capacity. So simply diverting the feed direction into the radial escalated the performance of the filtration module quite significantly. This is a fouling analysis. As I said, the majority of the cake fouling was gone. We wanted to see the in-depth investigation. We want to do some in-depth investigation and do some CFD simulation and plot the contour plot of the velocity. So this is basically a velocity profile in a cross-sectional view. As you can see, the conventional type has very low overall flow velocity, and meanwhile, HCFV has a high core velocity. And HCFV with orifice, you can see the core region is fluctuating. It's unstable. And meanwhile, TJ, the majority of the parts are bluish colored. That means it's more or less the same as conventional type. But in a center column, where the jets are generated, you see the high flow velocity regions. And those jets can be divided into 3 segments: turbulent free jet region, impinging point, and the wall jets. The wall jets covers the membrane with a high velocity, and on the right hand, on the figure right hand side, you see the core region. The turbulent free jet is developed, and and then it impinges on a membrane surface, and the wall jet is created covering the membrane surface. So we plotted the velocity profile, conventional type, regardless of the position, the fluid velocity was less than 0.1 centimeter per second, literally 10 centimeters per second. In the meanwhile, HCFV and HCFV with orifice, you see very high velocity, like more than 10 times. But you have to still remember that the average feed flow rate, feed recirculating ratio has been escalated as well. And meanwhile, TJ, the turbulent jet module, has 10 peaks where each of them are impinging points. And in between those peaks, you see still they are maintaining high velocities, high fluid velocity. We also conducted some boundary layer analysis to see how we narrow down the boundary layers for each filtration modules. Because boundary layer, no matter how fast velocity you have, there is always a boundary layer, and as smaller boundary layer you have, the more defouling capacity you can expect from the filtration module. So we plotted the velocity profile in the vicinity of the membrane surface, the conventional type on the left top corner. You can expect a typical boundary layer shape. And meanwhile, HCFV and HC module, they have reduced boundary layer thickness. And TJ module, they are even thinner boundary layer thickness than HCFV and HC. So in a CFD simulation of shear stress plots, you see even without escalating the pump recirculating ratio, TJ has even distribution of shear stresses colored in green and occasionally red, periodically red, throughout the membrane surfaces. So the average shear stress was 0.44 for conventional type, and the others, HCFV was 2.64, with orifice 4.84, TJ 1.64. You may ask, well, higher shear stress would be beneficial for defouling, for fouling reduction, fouling mitigation inside of the module. But well, there are potential discussions about the energy requirements. Yeah, definitely higher shear stress is better, but once it's saturated, once it's over the limiting shear stress, in other way around, if it provides more than enough shear stress to defoul the foulants, then it's going to be a waste of energy to provide higher velocity. It requires a lot of pumping energy. So if we consider that part into our consideration, well, when the conventional type requires specific energy requirement of 13, then HCFV and HCFV with orifice is 0.5, 1.5, and almost 3 times higher than the conventional type. Meanwhile, TJ, turbulent jet module, reduced the specific energy requirement by 40%. And that was just a proof of concept design at the beginning. We developed this idea through the force balance model. We calculated out the net angular momentum or moment. It's basically a force balance, and depending on the position of the foulant, we decided how much area is going to be defouled under the given conditions. And the second approach was to do more detailed CFD simulation to see and to minimize the dead zones in the corners of the module. Throughout those two design approach, we implemented this modified turbulent jet module in the actual harvesting process. We cultivated more than 60 liters or around 100 liters of microalgae suspension outdoor in a photobioreactor and try to do some real actual harvesting until it reaches to its limitation. The limitation means in case of control, they are not squeezing the permeate anymore, so we have to stop. In the meanwhile, the turbulent jet module, we reached to a minimum recirculating volume, feed volume, so we had to stop. If we proceed more, the module would not be able to, the module would not recirculating the volume, the feed volume anymore. And this is the results. With a periodic backwashing cycles, 30 minutes of filtration and 30 seconds of backwashing period, the control exhibited average flux of 19 LMH, reaching up to 33 gram per liter. In the meanwhile, turbulent jet module exhibited 55 LMH of average permeate flux throughout its operation, reaching up to over 80 gram per liter. And the harvesting time was just 1/3 of the control. So if we combine those two figures, the flux has been increased 3 times. The concentration increased 2.4 times. Harvesting filtration time has been reduced by just 1/3 of the control. And this implies a lot of possibility that we break the limit of the final concentration, and also the backwashing period, number of backwashing period has been reduced by 30%. And the first one can be connected to the process simplification, and the other one is connected to the membrane maintenance, because frequent backwashing may deteriorate the membrane integrity. So this is a schematic diagram of a downstream process, starting with the cultivation to a catalytic conversion for the final product. And as you can see in a light blue rectangle, harvesting is usually composed of 2 processes, membrane filtration and autoflocculation for primary harvesting, and dynamic filtration and centrifugation for secondary concentrating steps or dewatering steps. And 50 gram per liter is a kind of breakthrough concentration for the following cell disruption process. By employing the TJ module, the newly developed module, we can break the limit of 30 gram per liter, and reaching over 50 gram per liter, that means we can neglect or we can omit the secondary harvesting step. So does improving the economic feasibility of the overall biorefinery process, and also contributing to lower the biomass and biofuel prices. So this has been a brief idea. I omitted a lot of stuff to squeeze everything in a time limit. And and thank you for listening my presentation. Your questions and comments are more than welcome.
Yes,
Thank you very much, Dr. Kim. Yeah, it's very nice talk for the collection of the algae from water. We are open the question and answer from audience. Is there any question? Yes, Dr. Mohammed. You have a question? Let me see. Okay, I can read the message. I have a short question. Yeah, so you are using the hollow fiber membranes to recover the algae from water. So how about the applying the flash sheet, dead end flash sheet? Because if we select this, we can apply actually the spacer to allow to get the turbulence, maybe less energy consumption. So I want to hear about your opinion about that.
You mean the spiral wound or plate and frame module?
Yeah, like a spiral wound or the plate frame, whatever, the flash sheet application. So they're allowed to use the spacer to give, turbulence flow.
Yeah, that's a good question. Actually, plate and frame has more flexibility, degree of freedom, I'd say, to implement various techniques to mitigate fouling during its operation. But the problem is the plate and frame module is too small in the actual harvesting process. So if you run the facility at least in a pilot scale, you are not going to be able to secure the membrane area as much as hollow fiber with the same volume. If you are using plate and frame module, it should be really, really large. In case of spiral wound, yes, it's highly durable, and also there are a lot of spacer designs for spiral wound module performance, but the gaps is quite small in microalgae, especially if microalgae is cultivated out in the outdoor open ponds. It has a lot of impurities, and there is more possibility of inducing severe irrecoverable fouling in the spiral wound module. So that's why majority of the cases we are relying on hollow fiber modules.
Yes. Yeah, thank you very much. So is there any question?
Victor?
Yes.
Hi, Dr. Kim, thank you for it is okay, Doctor. Dr. Kim, thank you for a nice presentation, actually. I have one question related to membrane technology in harvesting algae, actually. Did you compare your results with other technologies, for example, electrocoagulation to get algae?
Oh, okay. Thank you for your question. ECF, we call it electroflocculation coagulation, EFC, ECF. Yeah, of course there are, and their final concentration was like 40 to 50 gram per liter in 40 to 50 gram per liter in a scaled up module. So, and at the same time, it's one of an energy efficient option that you can think of. But the problem is when you are injecting, when you are putting some electricity, when you're putting the electrode in the medium, they also produce a hydrogen peroxide, and that may deteriorate the integrity of microalgae biomass. So you have to be very careful when you are adjusting the operating conditions and also the configurations in scaling up the system. So in terms of the electricity consumption in a small scale module, ECF exhibits better energy efficiency, but if we scale up in a higher volume, membrane hollow fiber-based membrane module exhibits better energy efficiency, and also we have to consider the integrity conditions of the biomass at the same time. So it all depends on what is your final target product at the end. I don't know if if my answer satisfies you.
Yeah, it's okay. Okay, thank you.
Pleasure.
Yeah, thank you very much, Dr. Kim again. So for the next following speakers, I want to pass my mic to my colleague,
Yeah, our
moderator, Dr. Khalid.
next speaker is not available now, so we will be showing some posters until the time for Dr. Muhammad Tawalba to join us, which is 5:55.
Okay,
So
thank
we
you.
will have poster session now, and we will see you at 5:55 with Dr. Muhammad Tawalba session.
Yes, almost we have 1 hour. Okay.
Yes. You can drink coffee, have a rest.
Okay. Thank you.
Uniformly distributed equal at lower temperature as well as higher temperature. Structure. There are several layers like international conference on chemicals and materials for emergent technologies, other university for giving me the opportunity to present my work. Then I would like to thank
Hello, everyone. Are you hearing me?
Yes, Dr.
We can start the next part of our evening session.
Dr. Matt is available?
Dr. Matt is available.
Hello.
Hello, Dr. Matt.
Hi. Can you hear me?
Yeah.
Oh, okay. Yeah. I have to leave around 8 o'clock, so I'll try and go through my talk quickly.
Okay, we can start with Dr. Matt.
Okay. So
Okay.
I will share my slides then, and we'll go from there.
Okay, let me introduce Dr. Matt for the audience. Dr. Matt is a professor in the School of Environment and Sustainability in Royal Roads University in Canada. His research is focused on contaminants in the urban environment, metal speciation, and bioaccessibility, soil toxicity testing, and air quality monitoring. Working primarily with the potentially toxic metals and resistant organic pollutants, and more recently, microplastics. He has conducted research and assists with the human health risk assessment for various sites in Canada, China, and Ghana. He also provided scientific advice on environmental remediation of contaminated sites in the Canadian Arctic and the Yukon, and participated in US EPA around open studies on arsenic and lead bioaccessibility. Dr. Dad is a member of Bioaccessibility Research Canada, board member of the Vancouver Island chapter of the Air and Waste Management Association, and has participated in Northern Contaminants Program. Dr. Matt, the floor is yours. Please go ahead.
Thank you for the introduction, and thank you for inviting me to share some of the work we've been doing on contaminants in the urban environment. And so today I'll talk to you about one of the aspects of the program. We'll be looking at how, in terms of human health, and especially with the Sustainable Development Goal 3, how soil plays a role in human health. Because we grow food in soils, and if there are contaminants in the soil, it can be picked up and be introduced into humans. So today, the objective of this talk will be telling you some of the work we've been looking at metals in parks and playgrounds across Canada. And now we've also been looking at metals in backyard gardens and community gardens. And our objective is to create a virtual soil map of metal distribution around the country. And I'll show you a couple of the maps that we have created. And also look at the human health risk associated with exposure to those metals. So just a quick background, some of the potential sources of contaminants which can go into the urban environment based on what we have noticed will be natural sources from weathering of rocks and natural materials. Transportation plays a big role in introducing some contaminants such as volatile organic contaminants, polycyclic aromatic hydrocarbons, metals, and there are various industrial sources. And incineration also plays a role from metals such as cadmium, mercury, and various pesticides. So in the old days, pesticides such as lead arsenic was used in orchards, and I'll be talking a bit about that. And then, of course, people use manure, compost, and biosolids. And research has shown that some of these soil amendments can introduce contaminants into the soils. And then if a site is on a contaminated site, brownfield, it can also introduce some of the metals. Some of the metals of potential toxic metals we've been looking at include arsenic, cadmium, chromium, copper, mercury, nickel, lead, and zinc. And there's not enough time to go into why we selected these metals. But if we take arsenic, for example, chronic exposure to arsenic has been shown to be carcinogenic. And so there are places around the world where people are exposed to arsenic through drinking water and soil, and incidence of cancer is very high. So we look at these potential toxic metals. And I put this chart out to show some of the potential sources of exposure, talking about human health. And so if you have a contaminant in the soil, in contaminated soil, it can be picked up by worms and soil organisms, and then it can be transferred into plants. It can be transferred into animals, into fish, into water, and it can also go into the atmosphere. But for this talk, I'll be restricting myself to contaminant in soil only. So once the contaminant gets into the food chain, it can get to the receptor. And for the human health, we're looking at inhalation, ingestion, and dermal contact. And for this talk, I'll be talking mostly about soil ingestion. So in terms of soil ingestion, how do we determine the risk associated with soil ingestion? We do that by looking at the estimated daily intake of the contaminant from soil. And so the EDI is the estimated daily intake. And so the first thing you do is determine the concentration of a contaminant in the soil, and then use the ingestion rate, exposure frequency, exposure duration, contamination factor, and then the relative bioavailability. Most of these parameters, which I explain here, based on some assumptions. So Health Canada, for example, has various assumptions as to the ingestion rate, exposure frequency. So we use these assumptions. But two of the things that we can determine is the contaminant concentration and the bioavailability. So in terms of the bioavailability, I just thought I should throw this out here. Bioavailability is the amount of the contaminant that is absorbed into the body following skin contact, ingestion, or inhalation. So if a human receptor is exposed to the contaminant through ingestion, only a portion of that will be biologically available. And in order to determine that, I'll go to my next slide. To determine bioavailability, you can do in vivo assays. So you take your contaminated soil and then you introduce it into the animal. Usually we use rats, pigs, or rabbits, and then determine the percentage which goes into circulation. But it's in terms of ethics, cost, and so on, we are looking at using in vitro assays. And in vitro assays involve using simulated gastric fluid. So what you do is you simulate the gastric fluid, introduce your contaminant into the soil, and determine how much of the contaminant is absorbed into the solution. And the amount of the contaminant which is absorbed into your simulated fluid is your bioaccessible fraction. And going back to my previous slide, bioaccessibility is the fraction of the contaminant that is soluble in the simulated gastric tract and is therefore available for absorption. So what you can do is you can use this as a surrogate for bioavailability. And we have developed regression equations which relate the in vivo to the in vitro, and these are typical examples. So in terms of the work that we do in the urban parks, the first thing we do is we've collected samples from various cities across Canada, and this is a map showing all the cities that we've looked at. And so what we do is we take surface samples from the parks, from areas which are accessible to people who are using the park, like from picnic areas, from bare soils, and then we look at the surrounding land use, and we look at the site history and the geography. And then on the basis of that, so this is a typical example for some of the cities. We've got samples all around the city from different land uses, and then from different site history and so on and so forth. So example, Halifax, Fredericton, Toronto, Ottawa. So these are cities in Eastern Canada. So we bring the samples into the lab, and the students dry the samples, sieve, and then they determine metals by X-ray fluorescence and ICP-MS. And then they also look at soil pH and organic matter content. And then we look at the bioavailability using the in vitro extraction. And some typical results we've obtained. So these are some of the mean concentrations. And then in red here, I show, on the bottom here, I show the CCME, which is the Canadian Council of Ministers of Environment guidelines for soil quality for residential and park land use. And if you take a look at the data, arsenic, chromium, copper, nickel, lead, and zinc. There are locations in some parks which have levels which exceed the soil quality guidelines. And the other thing we've done is we compared the concentrations in the urban areas to background areas. And generally, we noticed that the concentrations in the urban areas tend to be higher than in the background areas. And if you look at the locations of the parks which have higher levels of contaminants, they're usually located in either high traffic corridors or industrial areas, especially areas with scrap yards, and then former industrial sites. And then we also found some areas which have been contaminated from lead from paints and then use of wood preservatives. So this is a typical map of distribution for Toronto, which is one of the biggest cities in Canada. And if you look at the lead levels, there is one park where the lead levels highly exceed the soil quality guideline of 140 milligram per kilogram. And this is located in an industrial area where there's lots of metal fabrication. So this site had zinc, lead, and other metals exceeding the guideline. There's another area out in the harbor area, which also had metals exceeding the guidelines. And this area was a former industrial land. And so we can relate the concentration which exceeds the guideline to the historical land use or current land use based on industries. And the next slide, I show data from Victoria. This is where I live. And if you look at the distribution for lead in particular, the downtown core has various locations where the levels of lead are highly elevated. And these are located in, again, industrial sections of the area. So parks located in industrial areas tend to have higher levels of the metals. And then this slide shows the distribution of the different metals in different cities in Canada. One thing I want to point out is that in arsenic, in particular in the Halifax, tend to be very high. And this is based on the geology of the area. So we've looked at samples around across the country, and Halifax in particular, the levels exceed the CCME guideline based on the geology. And then lead in Toronto, the biggest city in Canada with lots of industries and traffic, seems to be the highest, and so on and so forth. And just for lack of time, this shows in terms of the human health risk based on soil ingestion in the urban parks. So what we've done is we've calculated health risk based on the samples from all the different sites that we have. And this is a summary of some of the different sites across the country. And if you look at this chart in particular, there's one site here which exceeded, there are 6 sites where the risk exceeds 1. And these sites, if you look at the site history, this one in particular, the first one here has arsenic as the main driver of the risk. And this site was located in an area which was historical gold mine. And so it's related to the waste rock, which was contaminated the soil. And this, the highest risk was found for a site in Toronto. And this is the site which is located in the industrial area. And this is the other high site was from a former industrial land which was cleaned up, but it looks like the cleanup was not completed. And so in terms of, those are some of the parks. And the other one I briefly wanted to share is results from garden survey. So the way we approach the gardens, we've so far only done work for 3 cities in Canada: Victoria, Calgary, and Kelowna. And the way we approach the garden work is we place ads in social media, asking for people to volunteer for the students to come to their house to take samples from their gardens. And then because it involves talking to people, we do an ethical review, and then the students go to the homes and then they interview the homeowners to know a bit about the site history and how they maintain their gardens, whether they use soil amendments and so on. And then the samples are brought to the lab to do the metal analysis, do the bioavailability analysis, soil pH, and so on. And then the data is interpreted and then mapping and the results are presented. And so far in Victoria, we've sampled 315 residential properties and taken over 800 samples. And we've also taken some plant samples and looked at food chain uptake for the plant. But I will not be talking about that due to lack of time. And one of the things the students do is they do land use history search. So they search the archives, they look at map offices, fire insurance records, telephone directories to try and figure out a bit of the history of the site. And on the basis of that, we can then apportion the contaminant to the site history or whatever soil amendments were used. So here are some photos showing some of the pictures the students got from the archive. So this one here is a site which was used as an orchard. And one interesting fact was that this samples from this area contain high levels of lead and arsenic, exceeding the guideline. And this was attributed to the use of lead arsenate as a pesticide in orchards in the past. So the students can use some of this historical information to apportion the source of the contaminant. And some of the results. So this is a summary of the data we have so far for some of the soils. And again, if you look, the maximum concentration for most of the contaminants exceeded the CCME soil quality guidelines. And what the students do then is for all the sites where the samples exceed the guideline, they go and look at the site history and try to figure out the source of the contaminants. And on the basis of what we found out, elevated concentrations of arsenic, copper, lead, and zinc exceeding the guidelines are present in some of the gardens. And these are related to places like old orchards, and then use of manures and fertilizers. So we've tested some of the manures and fertilizers, and some of them have contaminants with them. And some also use biosolids, which are contaminated. And then metal emission works. So gardens closer to the industrial areas tend to have higher levels. And there were a couple of sites where we did a history and found out the site was used as an automotive repair workshop previously. And so that led to the release of metals from used oil, paint, wear, and so on. And then one of the other key thing we noted was there are some houses where there were elevated levels of lead in the gardens. And these were related to the use of leaded paint. And so what we've done is we've taken samples of paint from the structures and analyzed them with the XRF, and they tend to have high levels of lead. So there's been leaching of lead from the paint which was used in the house into the gardens. And so the next thing we've done is this is a map of Victoria. We have soil quality maps for the different contaminants, which are published online and freely available. So anybody who lives in Victoria can go to this website, Victoria Soil Quality Map, and they can tell the concentrations of different metals, arsenic, lead, cadmium, and so on in your neighborhood. And so what we recommend is if you have a home in one of these areas and you want to plant a garden, the first thing you do is you go and check the soil quality map. And if your area is in a location where the levels of some of these metals are high, we recommend that you take a soil samples and send it to our lab, and we analyze it for free for you to have an idea of the levels of metal. So these soil quality maps are freely available on the web. We have, this is the soil quality map for lead. And if you notice some of any sample which is in red or pink in this case exceeds the guideline. And most of these areas are in the central part of the city near industrial areas or either from leaded paint. And so the next thing we've done is, and this is zinc, I'll skip that. The next thing we've done is we're working in conjunction with the Victoria Compost Education Center. And what we've done is we've developed soil contamination fact sheets, which are available to the community. So what we recommend is if your soil, if you live in an area with elevated levels of these metals, we recommend you have your soil tested. And if your soil comes up as contaminated, then we've published guidelines on some of the best things you can do to grow healthy food. So these fact sheets are available on the line. And we also organize workshops for homeowners, and all these resources are available for free for the community. So they can come to the workshop and learn about best practices on how you can grow food safely and prevent exposure to these contaminated metals if we find in your backyard. And just recently, we've started a bioremediation project where we are looking at phytoremediation. So the students have established various plots in some of these contaminated houses, and then they've been planting 3 types of vegetation to look at the potential uptake and bioremediation using these plants. And so in summary, arsenic, chromium, copper, lead, and zinc are contaminants of potential concern in some of these urban parks and playgrounds. And most of these contaminants are due to anthropogenic activities. And the use of in vitro bioaccessibility helps with the risk assessment. And the take-home message is the risk associated with soil injection is generally very low, except for arsenic and lead in certain parks, playgrounds, and gardens. And in terms of funding, most of this work was funded by the Canadian Foundation for Innovation and Royal Roads University, and a special thanks to students who were involved in the work. And so I think the other thing I haven't mentioned is we looked at soil properties such as pH, loss of organic matter content, and we look at how these impact the metal bioavailability. And then we look at the regression equations, but for lack of time, I'm not going to go into that. And so I think this is all I wanted to share. And thank you for the opportunity to just talk about some of the work we've been doing in the community to make people aware of the potential exposure to these contaminants in terms of the Sustainable Development Goal 3. For good health, we need good soil. And so prevention of exposure to contaminants in soil is very key to some of the projects that we're doing. And I think some references, and I'll stop and see if you have any questions. So I'll stop sharing.
Yeah, thank you, Dr. Matt, for a very nice and informative presentation, actually. I open the door now for the audience. If they have any question, we have time for 2 couples of questions. Anyone have any question? Okay, Dr. Matt, may I ask you a question, please?
Sure.
Do you have any study related the distribution of metals with disease in Canada in the selected locations, for example, the cancer, for example?
No, we haven't looked into the epidemiology. The only work we've done in that area was we did some work. There are light stations across Canada, and what we found was the light stations have high levels of lead in the soil. And we looked at the levels of blood in the people who look at the light stations. And there's a correlation between the levels of lead in the soil and the level of the housekeepers. And based on that, we came up with a recommendation to remove all the topsoils around the light station and then bring in new soils and prevent exposure to lead in particular. But we haven't done that. We haven't looked into the epidemiology.
Okay. Thank you. Okay.
Can I ask a question?
Sure, Dr. Joanne.
Dr. Matt, thank you for your presentation. I'm personally interested to know about what do you think the route of exposure between the public and the soil, the contaminants from the soil? How do they get exposed to the to those contaminants?
So in the playgrounds, we have especially kids playing with toys. And so if you go to some of these playgrounds, we have kids playing soccer or football, in your case, and then they'll be exposed to the dirt. If you get some dirt in your hands and you lick your fingers, you'll be exposed to the dirt. And also for gardeners, if you are gardening, you usually put your hands in the dirt. You try to wash them as much as possible, but sometimes you can get some dirt lodged into your fingernails, and then if you eat, you'll be exposed to it. So the risk that we calculated, we looked at the risk associated to inhalation, dermal contact, and soil ingestion. And soil ingestion seems to be the most major exposure pathway. And we did a calculation on the assumption that a kid will be exposed to 100 milligrams of soil per day based on playing in the playground. And then the adult is 20 milligrams a day. So we use very conservative assumptions for the exposure. So the charts that I showed you, we used some assumptions. And this is based on Health Canada has published some guidelines on assumptions on incidental exposure to somebody playing in a park or playground.
Yeah, it makes sense, but you don't think also aerosolization, like if there's dust or exposure of dust and wind through wind could be another route as well?
Yeah, so there is inhalation of dust, and then there is dermal contact. But when we do the calculation, the amount exposed through inhalation and dermal contact is very low. The risk is very low compared to ingestion. Ingestion is the most prominent exposure pathways. So for the risk assessment, we've been looking more into the ingestion than the inhalation. But yeah, we do have equations for the inhalation. Again, the Health Canada guidelines has equations and then assumptions that you can use.
Interesting. Thank you very much.
You're welcome.
Thank you. Okay, maybe you have one more question from Dr. Muhammad.
Sure, go ahead, please.
Dr. Muhammad, raising your hand.
It's the old one.
You have a question, Dr. Muhammad?
Oh, he said it's the old hand raise. So
Okay, thank you, Dr. Matt, for very nice presentation and for joining us today. We have now need to move to the next speaker. It's supposed to be Dr. Muhammad Tawalve. I think he is not available right now. So we can start with Dr. Joanne.
Thank you.
Thank you very much. Thank you, Doctor. Our next speaker is Dr. Joanne Al-Abdini. Okay.
Do you want me to share my slides or would you do it?
It is okay. Just I would like to present you for the audience. Dr. Joanne Al-Abdini is associate professor in the Department of Land Management and Environment at the Prince Al Hassan bin Talal Faculty for Natural Resources and Environment at the Hashemite University. Dr. Joanne actually Her experience involves teaching branches in environmental science. Here teaching learning. He focus on student-based learning. Dr. Juan, the floor is yours. Please go ahead.
Thank you, Dr. Khalid, for inviting me to this conference. And I'd like to see if my voice is clear. Everybody can hear me very well. And then the slides are there. Yes. So today I will share some of the work that we've been doing with. Actually, this work was done by one of my master's students, and we've done some work on water disinfection by solar energy. As you all know, that this talk is somehow related to SDG number 6, which is clean water and sanitation, which is a global right for everyone. Everyone should have access to clean water and accessible with a good quality. So the United Nations have recognized that it is important to provide good quality water for consumption and also water for sanitation. But it seems that there's a big challenge where 85% of our planet's wetlands and surface water has been lost, has been dried out. It also the figures were also alarming that 1.6 billion people will lack safely managed drinking water, and 2.8 billion people will lack safely managed sanitation, water for sanitation, and 1.9 billion people will lack basic hand hygiene facilities. Therefore, the report was talking about, that was initiated from the United Nations, ensuring availability and sustainable management of water sanitation for all. They pinpointed that meeting drinking water and sanitation and hygiene targets by 2030 will require fourfold increase in the pace of progress. We need to work 4 times harder to provide potable water for drinking and clean water for sanitation. So it's a global issue, but that doesn't leave Jordan away from this picture where we are located in Jordan. This is a picture representing some of the faucets available for drinking in public schools, where we could just lay out certain facts in the country. The available water per capita is at less than 100 cubic meters per year. Rainfall average between 100 and 400 millimeter as well annually. And the water used by sector, majority of the water is consumed by agricultural sector, while also similar kind of 45% in domestic use, and the least percent goes for industry. So this puts a lot more pressure on the country, how to provide water, where it can get it. This report this is an article was published in Nature, and in 2019, where the author Elizabeth Whitman titled it as "A Land Without Water." The Jordan, talked about Jordan and the land without water. How we stop Jordan from running dry. So and she, raises certain factors that contribute to this problem with climate change, the flux of refugees, poor planning, draining water supplies in Jordan. All these factors and probably some more would emphasize the problem of water scarcity and water issues in Jordan. And that also demanded accelerated work towards providing clean water. So what we will be presenting to you today is that with the country characteristics of water scarcity, with limited resources, and of course arid climate, we have a potential with high solar radiation. So that's the question we're then raising here is, can we use solar energy to increase availability of safe drinking water to minimize the risk of waterborne infections? So it's a two-way thing. So what we looked into the quality of water, and of course we did not invent the disinfection by solar energy. This technique has been used for ages from simple tools. But here we try to modify it and see how we can use it as a simple device and how we can optimize the use of solar in the disinfection strategy. So some of the research objectives were into designing the simple unit that can be used in less fortunate areas like refugee camps, stressed, unfortunate places, so they could harness the solar radiation for water disinfection. If I can have access to surface water, can I use this device, for example, to safely use it to sanitize the water and make it then usable? We wanted to investigate some of the parameters that would influence the treatment. So we did some optimization phase with light exposure time, with the amount of water, and perhaps we've also looked into the clay minerals. Clay minerals that we have previously from a previous project have isolated as they have antimicrobial potential. So we wanted to diversify the application of those antimicrobial clay minerals into, can they also have a potential in enhancing the water quality and reduce the microbial load in the water. So we needed to test some water quality like pH, EC, turbidity, and of course the indicator organisms of total coliform, Escherichia coli, and Pseudomonas aeruginosa. These were the main microbial tests that we have done. So to talk a little bit about the research questions, we wanted to see the combination of how much time do I need to expose the water for disinfection according to Jordan weather during the research. I think it was done in October to mid-November, where the autumn time, similar like this time. Is solar system able to achieve the goal to reduce the microbial count in water? And of course, we use different types of water, from the artificial unclean water that we could collect from the faucets in the faculty, in the building. And of course, we've also tested wastewater, and we've tested natural spring water before going to disinfection and filtration. So we tested different types of water, and we wanted to see which conditions were more suitable to achieve our goals, and if clay minerals would either enhance working with the solar energy, would it enhance the capability of clay minerals to reduce the microbial load or not? So we had some research variables ranging from light versus dark, and it was obvious that the dark did not really give much results. So we did not. I'm not going to show you some of the results that were done in the dark because they did not make any reduction in the microbial count, and the contrary, some of the microbes, they multiplied even better. We wanted to investigate light exposure time. Should we put this water for 1 hour, 2 hours, 4 hours? But we wanted to make this system a little bit more quicker. Can we accelerate the time if we use reflectors? So we use reflectors, either mirror reflectors versus no reflectors. We use different models of reflectors, the flat mirror reflector and the concave mirror reflector. We've also tested some quality like turbidity. Does turbidity affect the water quality and the solar disinfection as well? That also comes in hand with the clay mineral. The more clay mineral you add to the water, the more turbid it gets. But does that affect the disinfection or not? And which concentration of clay would be better to use? Therefore, seem to move to the next slide. Okay. So with the methodology here, I'm going to show you a little bit about the simple setup that Isra, my master student, has used in her study. So basically, these are glass bottles. It's a patch culture. We fill them with water that we manipulate, we've used from different systems. And this is the height from the ground, 25 centimeters. And this is without any mirror reflectors. B is with the mirror reflector and flat mirror reflector, and C is with the concave mirror reflector. I'm having issue with my keyboard. I don't know, it's not coming. It's not moving to the next slide. Okay. So we use, of course, glass container because it's transparent, it's available, and it can resist high temperature. We use those as autoclaving so it could withstand the heat. This is the apparatus that we've used, and we wanted to make sure that our system using solar radiation, that disinfection is not related to a major increase in temperature, but it is actually the UV radiation in the solar system that causes the disinfection in the microbial cells. So we've used thermometers to monitor temperature, and there seemed to be the temperature rise no more than 32 degrees Celsius at that time of the exposure, and that kind of gave us indication that the disinfection was caused by UV. These are the 3 different types of water that we use. We use unclean water that we could, simulate in the department. We used wastewater from Zaytuna University, from the treatment plant in that university, and of course we used a natural spring groundwater. It's a groundwater system, but it is kind of contaminated before filtration, before chlorination system. We went there and collected the water, and we did our setup as well. We focused on, as I mentioned, the total coliform, Escherichia coli, and Pseudomonas aeruginosa. These are the indicator organisms, and we used 2 different methods. During the optimization phase, we used what is called a multi-tube fermentation technique, which relies on the ability of those gram-negative bacteria to ferment L'Oreal tryptose broth medium, and if gas is produced, then it is if it is produced, then it indicates a positive test tube. So we followed this procedure to identify and quantify the most probable number of those indicator organisms for total coliform and for E. coli. The E. coli, you need to subject it to fluorescent light, so the fluorescence here is an indication of a positive test tube. While if you have a gas production, this is called a Durham tube. It is an inverted small test tube. When there's a bubble or gas, this Durham tube rises up. So this is a positive tube versus a negative tube. The other technique that we've used to confirm the presence of total coliform, the E. coli, and the Pseudomonas, we use the IDEX for the enzyme substrate method. Also the quanti-tray sealers and the UV lamps with cabinets to ensure that we did this on a systematic level as well. Other physical parameters, we also tested some of the water, the temperature, turbidity, dissolved solids, conductivity, and then the pH of the water. For clay mineral studies, these clay minerals, they've been obtained from a previous study. So we've selected those, the top 1, 2, 3, 4, the top 4 samples. These are from soil fractions. So we went to areas in Jordan, and these are the different locations in Jordan, and we sampled soil, and then we did soil fractionation to obtain the clay fractions. But that was tedious. You need a large amount of soil to obtain a very small fraction because clay is the finest grain in the soil. So my friend, she's a geologist, she recommended why not use clay rocks, and she provided me a bunch of rocks that she had setting in her lab, and I tested that particular rock that we've crushed and then sieved. It was from Mahas, and that also showed antimicrobial potential. So we included that in our study here as well. So what we did with the optimization phase is that we first set the water bottles out in the sun for 5 hours directly without any reflectors. So before we start any solar exposure, we tested the total coliform and E. coli, and these are the numbers that we obtained. After light exposure for 5 hours, we could not detect. It was below detection limit of the multiple tube fermentation technique. And so we would, make sure that solar disinfection actually works. But then we decided to introduce the mirrors, and we focused on total coliform, which we started with like 13, a most probable number per 100 ml of water. We used concave mirror, and after 1.5 hours, the control bottles showed there's some total coliform still left, but with the concave mirror, there's the numbers were below detection limit of the procedure. While after 3 hours, both the control and the concave showed similar results. So it seems that the concave mirrors, they seem to accelerate they reflect the UV light, they reflect the light going back through the sample, and that would enhance the capacity of the disinfection. If we want to compare here, the next step was to see which mirror reflector is best. Is it the flat mirror or the concave mirror? With the technique and with the abilities that we had, and I think we kind of messed it up a little bit because we were not sure if our bottles were at the focal point of the concave mirror, and that's where I think things didn't really show much, the results that we would expect. So the FM stands for flat mirror, while CM stands for concave mirror. For total coliform and E. coli, after 1 hour of solar exposure, these are this is from wastewater, and these started with a really high number of total coliforms, high number of E. coli, and after 1 hour, we managed to get around 74% reduction from flat mirror. With concave mirror, we obtained only 56% reduction. Similar to E. coli, the flat mirror had higher reduction rate in the E. coli, Escherichia coli counts. So with this, it seems that the flat mirror seemed to be more efficient in the way we have set up our experiment. So basically, we kind of to move to the next slide. Okay. So studying the relationship between water and turbidity. The next thing is we wanted to see if does the water turbidity would affect the efficiency of solar disinfection. And it seems that, as the water gets turbid, it does affect the efficiency of disinfection. But there was, due to high turbidity, we could not obtain that with the concave mirror, but with flat mirrors seem to have some sort of efficient water disinfection, but we have to increase the exposure time. So here with the flat mirror treatment with initial turbidity of 13.2 niflometric turbidity units. Where is that? Okay. And the other type of water, we use 37 NTUs turbidity. So this is represents the low turbidity, while the other treatment represents the high turbidity in the water. Again, if we look into the total coliform reduction rate after 1 hour and after 2 hours, the more, the more turbid, less efficient. So if we compare after 1 hour of low turbidity, you get 97% reduction in the total coliform. While in the high turbidity, total coliform only is reduced by 50%. And so after 2 hours, the low turbidity seemed to have very high efficiency in disinfection, but even after 2 hours, the turbid sample seemed to still have 81% reduction. So we could not totally make it safe for drinking, but we may need to increase the exposure time. So that's the issue with turbid water. You need to maximize or increase the exposure to solar radiation. So with the spring water that we used, we did it at a reduction rate for all indicator organisms. It was good at 1.5 hours of solar exposure using the flat mirror. Okay. So if we don't use the flat mirror, you need a maximum of 3 hours to reach the similar values. If you compare solar radiation intensity and the disinfection rate, it seems the flat mirror gave good results. Pseudomonas aeruginosa was able to reach maximum disinfection after 1.5 hours, while total coliform E. coli were reached at maximum 2 hours. So it depends on the the more you leave it, the indicators, you need to also make sure that this is a safe drinking water. So you maximize the exposure time to make sure that all types of indicator organisms are being disinfected and being killed. So it also relates to the variation in the solar radiation. So intensity of solar radiation, it is also a variable per day, between seasons, between the time of the day. It also varies. So this is something that should be taken into account when it comes to using solar radiation. So here with wastewater, okay, also with similar results, we obtained it in wastewater results after 1.5 hours and after 2 hours. Low turbidity indicates high efficiency of disinfection, but when the initial turbidity increases, you get less efficient turbidity, less efficient disinfection, and so you need to increase the exposure time. So the results here with the different types of clay minerals that we have used, we kind of figured out which concentrations, because you really don't want to increase that, amount of clay in the water. So it would make it more turbid and it would decrease the efficiency. So the concentration that we have set during the optimization phase was about 0.1% of each type for about exposure time of solar exposure was 45 minutes to that volume of water that we've used. And the most effective type of clay, and there were variation in different types of clay. They did not all act the same. So it seems that this particular sample of clay, which was from the rocks, seemed to be very efficient in reducing the number of indicator organisms, even with SOBIS. So we will choose it for our most optimized system using the flat mirror as the most effective. This is the samples that we used with clay minerals. This is the layout that we have exposed them up in the sun. So the first batch is, the first bottle is a control bottle. The other ones are clay without any mirror, and the other ones are clay with mirror reflectors. So here we notice that different concentrations of clay, when we applied them between 0.01% ranging to 0.1%, the most efficient was the highest. So the highest concentration of clay gave best result in terms of disinfection. There's, solar exposure used in flat mirror gave best disinfection obtained in this study. So as a conclusion, we could see that the solar disinfection has a potential mean to reduce the microbial load, especially when it comes to water that is been directly taken from the wells without going through treatment plants. Some people, because in Jordan we're very arid, we only get water one day during the week, and some people get it for less time. So if I run out of water, then I have to buy water from an unknown source. And for that unknown source, how would I trust the source of cleanliness of water? So if we could develop systems that can be used in the household to enhance the quality of the water, at least during the microbial part, then we would minimize the risk of waterborne diseases. And this system seems to be a good and efficient way to be adopted, but we need also to recognize that if you want maximum results, you need to emphasize or maximize the benefit with the UV radiation through the reflectors. Usually we use aluminum mirrors. And in our study, it seems that the flat mirror is simple and it is flat and it is very easily and gave good results in our study. With the time exposure, we need to acknowledge that there are some variables. The time, the type of water, the turbidity level, solar radiation intensity, also the angle, okay? Which treatment set was used, so which concentration of clay minerals. These are all factors that affect the optimization of the setup. So if we want to look into future let's say recommendations, we need to think about making this using concave mineral, or maybe we could just we need to redo these experiments and putting those bottles within the focal point of the concave mirror. We need to see if other possible reflectors could become better in our reflectivity. If we use foil, if we use steel, if we use aluminum mirrors, would that also affect the study objectives? Investigate different concentrations of clay minerals, maybe look into other natural elements, other types of clay within the rocks. Do they have a nano system? Can we do artificial nanoparticles, titanium oxides, aluminum oxides? We could just see if we could modify and tweak the system from patch culture to a continuous flow system. If we're able to continuously have that system of solar radiation, then we could make sure that the people are getting a good water quality in terms of the microbial system that we have just shown. So there's a big potential for more improvements, more ideas to hop in, and I think now I'm at the end of my slides, and thank you very much for your good listening.
Okay, thank you, Dr. Juan, for a very comprehensive presentation, very informative presentation about disinfection by solar energy. Actually, we have maybe time for one question from the audience. Anyone? Okay. Okay, Dr. Juan, I have a question from my side, actually.
Yeah.
It seems that the disinfection process by solar energy is very cheap, but I am wondering if you actually compared your results with conventional disinfection processes, because you worked as a batch test experiment.
Yes.
But I am not sure if you use continuous operation, there will be some limitations for using this technology. what do you think the feasibility of this technology in comparison with other available techniques?
Most of the treatments for, for water, drinking water, relies on filtration and chlorination. And we don't want to eliminate the efficiency of these water treatment systems. We want them to be still used. We want to monitor them. But I'm just, thinking about, areas where, clean water is needed, and it's needed at a cheap system, or maybe at refugee camps or systems where households cannot, have access to the water pipelines. But your question is really interesting, because this is what we are focusing on. Now we're trying to collaborate with some engineering faculty to see if we can design maybe tubes that are evacuated tubes that could, also help us collect, and, as the water goes through those tubes, it will be exposed to the solar radiation at a residence time enough to do the action. But the issue is in, separating the clay minerals from the water later on. Should we do immobilization of clay minerals on the glass surface? But that would also minimize the solar penetration into the water. So there are some limitations, and I'm not saying that we should get rid of the conventional means of treating the drinking water, filtration and chlorination. It is needed, but I am just suggesting that there could be other means also of harnessing the solar radiation. If we're able to, also the challenge is in the storing. If I store the water, do I guarantee that these microbes, they are not growing back again? So we need to make sure that the microbes, they are, eliminated before we store it for later use. That's another issue that we're thinking about.
Well, it seems like it be very visible for a small quantity of water or wastewater.
For now, yes, for now it is small. Even, the thing is with gray water reuse, which is a challenge also, and it is brought into a larger application in Jordan. Sometimes to reuse gray water for agricultural practices is limited, it is guided through guidelines. So if the standards, usually with gray water standards, some systems, they fail to meet the standards, especially with the microbial load. So if we could optimize such a system that can use gray water and reduce the microbial load enough to be able then to use it for agricultural practice, I think this could be another application for our system. It's cheap, and it is used not only for domestic, but it can also be used for different types of water types.
Okay, thank you, Dr. Joan, for joining us for our presentation.
You're welcome.
Moving now to the next speaker, Dr. Muhammad Tawalbe. Dr. Muhammad.
Assalamu alaikum. Can you hear me?
Yeah, yes. I will introduce you, Dr. Muhammad, for the audience. Dr. Muhammad Tawalbe is Associate Professor in the Department of Sustainable and Renewable Energy Engineering at the University of Sharjah. He joined the department in 2015. Received his PhD degree from in chemical engineering from the University of Ottawa in Canada in 2014. And he completed his master and bachelor degrees in chemical engineering as well from Jordan University of Science and Technology in 1997 and 1992 respectively. Dr. Tawalbe is a member of the Energy Storage and Management Research Group and Desalination Research Group as well. Dr. Tawalbe also research activity focus on renewable energy and sustainable environment applications, in particular in preparation and characterization of membranes for fuel cells, carbon capture, water desalination, and development of solar power membrane desalination processes. Dr. Tawalbe activities actually collaborates with the researchers from different researchers from different universities. He published around 100 international peer-reviewed publications. He served as a guest editor for many journals, and he served for a reviewer for more than 20 international journals as well. Nawal Bey, mashallah, is the recipient of several awards, including the University of Sharqa Annual Faculty. His topics today is about recent advances in the use of microbial fuel cells for water purification and power generation. So Muhammad, welcome to Qatar University, and the floor is yours.
Thank you very much, Dr. Khalid. So my presentation, as Dr. Khalid mentioned, it's about recent advances in the use of microbial fuel cells for water purification and power generation. And okay, so before we start, this is the campus for Sharjah University or University of Sharjah. It is in the heart of Sharjah Emirati in United Arab Emirates. And there were good news last week because the rank for University of Sharjah now is between 251 to 300 worldwide. And on the citation rank, University of Sharjah is number 68, which is number 1 in United Arab Emirates according to the Times ranking, which was an excellent news. Alhamdulillah Rabbil Alameen. Okay, I don't know how would move the slides. Okay. So the overview for my presentation, I will speak a little bit about microbial fuel cells. Before I go to the microbial fuel cells, I need to speak a little bit about the fuel cells because they are similar. Then different configuration of microbial fuel cells, factors affecting the performance of microbial fuel cells, the scalability studies on microbial fuel cells, and some limitations and challenges for microbial fuel cells. Then I will end up with conclusions. So we know that the use of fossil fuels is causing many environmental problems, mainly global warming, and it also with the war right now in Ukraine, the energy prices going so high, which makes like energy crisis. And so many countries, including United Arab Emirates, Qatar, Saudi Arabia, they are going toward renewables, solar energy, wind energy, hydro energy. Like in Canada, they are focusing on hydro energy, geothermal energy, and many countries, they are looking now for biomass sources, especially wastewater, animal waste, industrial waste, all these wastes, agricultural waste, to use them to produce use them as energy sources, and the same way to clean the environment. Wastewater is charged in large amount and extracted from many sources, industrial, domestic, sewage water, and agricultural sectors. And treating this water is cost and energy intensive. Okay, and with no valuable materials being regenerated, the cost would be very high. So using microbial fuel cell for water treatment and power generation, it will give both advantages. So we get rid from this huge wastewater that discharges to the environment, and the same way we produce power that would help with the energy crisis. Let us discuss the fuel cell before we go to microbial fuel cell. Like in a fuel cell, this is hydrogen fuel cell. The hydrogen will enter at the anode chamber, where it will react to produce protons and electrons. At the anode, there would be a catalyst there, mainly platinum or platinum alloys, and the electrons will go through the electrical circuit to produce the power, and the protons would go through a membrane. This membrane has to be proton exchange membrane to allow the membrane to pass to the other chamber, to the cathode side, which would meet there the oxygen and reduce the oxygen at the cathode chamber. Uh, like this is simple representation. Usually the fuel cell will consist of many layers, sorry. Has intercollectors, bipolar plates to control the flow for the hydrogen and the oxygen. We have gaskets, we have gas diffusion layers. Then we have the layers for the catalyst. At the heart for the fuel cell would be the proton exchange membrane. In the other side, in the microbial fuel cell, usually will have the same, will have the two chambers, will have the anode in one chamber, the cathode in the other chamber. However, in the anode, we have the biofilm that would be at the anode. And instead of having hydrogen, we'll have the substrate, which is a hydrocarbon or organic material. In our case, it would be a wastewater. And it would react at the or oxidize at the anode side, and it will produce the proton, the electrons, and the CO2. The CO2 gas would go with the gas recycle, and the electrons will go through the circuit to produce the power generation, and the protons, similar in the fuel cell, it will go through the proton exchange membrane to the cathode side. In the cathode side, it would meet the oxygen, and it would produce water. When hydrogen is used in fuel cells, usually the only production would be water, which is a cleaner process. When we have hydrocarbons, in that case, CO2 would also produce. Sometime CO will also produce. We have for microbial fuel cells several configurations, and this several configuration, it could be also single chamber and the double chamber. The double chamber is the mostly used configuration, where we have a chamber for the anode and the chamber for the cathode separated by the proton exchange membrane. In a single chamber, usually the membrane won't exist, and we have both the anode and the cathode in the same chamber. Will we have the biofilm covered both of them, and oxygen will come to the cathode side that will meet the proton that will move from the anode toward the cathode. It looks cheaper, but at the end of the day, controlling the operation is not that easy. It's more challenging. For the configuration, we have different type of configuration. So we may have, like as shown in figure A here, what we call H type, where the two chambers would exist as the letter H, or it could be like a cube type. Plate type would be also like a miniature type, or a horizontal tubular bar type, or a vertical tubular type. In all this configuration, we could have the single chamber or the double chamber. The components, as we speak before, we have the anode, the cathode, the proton exchange membrane, then we have the microorganism and the substrate. Okay, the substrate, which is in our case would be the wastewater that would be used to generate the power. Applications: wastewater treatment, electricity generation. It also used the microbial fuel cell in biosensors. It used in water desalination. Okay, and it is used to convert the chemical energy that's in the waste or substrate into electricity using the biological process. And it is very beneficial for the environment, as we mentioned earlier, because we'll get rid of all this waste, and we'll cut the cost for the water treatment. And it is also would be good to provide sustainable power, especially for isolated communities, and it could be also used to desalinate water. The principal work of microbial fuel cell. So at the anode, in order to generate electrons and the protons, we have the microorganism that will use the organic material in wastewater, and will produce the protons and the electrons, and the electrons will go through the external cell toward the cathode, and the protons will go through the internal cell through the proton exchange membrane from the anode to the cathode. They meet at the cathode, and there the protons will meet the oxygen or the air, depending about the source of oxygen, and this will produce H2O, and the waste will like in the cathode side, we'll have only pure water from, or in the anode side, we'll have the wasted water that would have all the waste and the hydrocarbons. As example, if we look for the reactions that would happen at the end and the cathode, and if we have acetate as the substrate, okay, so we'll have the acetate that will react with water at the anode side, and it will produce CO2, protons, and electrons. These electrons would pass through the external circuit to the cathode. The protons would pass through the proton exchange membrane, and they will be at the cathode. At the cathode side, the reaction, the oxygen, will take the electrons plus the 4 protons and will produce H2O in the other side. This is simply the principal work. What is the benefits of microbial fuel cell? Generation of energy from biowaste, omission of gas treatment, bioremediation of toxic compounds that exist in wastewater treatment, and also wastewater treatment. It has several advantages. Allow wastewater process to reduce activated sludge compared to anaerobic digestion process. Insensitive for the operation environment. Doesn't require the treatment of the gas because of the recycling and conversion. And it work with it. It produce much energy, and it work without energy input, and doesn't require aeration, and can be used widely in locations where there is insufficient electrical infrastructure, especially in rural areas. Despite these advantages, we have several advantages like low electricity production. The current density is unstable because it depends about the organic matter in the wastewater. There is highly internal resistance for the electrons and for the protons, and it is costly. This figure shows us the SWOT analysis for microbial fuel cells. As we said, the strength for microbial fuel cell, it is wastewater could be used as substrate, and could be used for acid, alcohol, esters, and chemical synthesis. Low input energy requirement. It could be platform for circular economy. Give us many opportunities, recovery for variable chemicals, utilization of flue gases, waste from industrial, suitable for desanitization treatment, waste to resources recovery techniques, real-time monitoring and control. However, it has many weaknesses, as we said, low energy yield, low net current density. There is a big challenge with the scale up, high initial investment, and poor conversion efficiency. It has also many threats, like it is very complicated, high costs associated with the operation, far away from commercialization. Like people are trying to scale up the process, but it has many challenges. So it's far away from commercialization, and there are many competition from other technology, and the techno-economical feasibility needed for the operation. The factors affecting the performance of microbial fuel cell. To be able to improve the performance, there are many factors that needs to be addressed. The microbial metabolism and cell potential, electron transfer mechanism, substrates, and operating condition, including pH, temperature, salinity, external resistance, and shear stress. And when we discuss like the factors affecting, I will focus my discussion about the catalyst at the cathode side and the membranes used, because this is where we are doing our research to improve the performance of microbial fuel cells. If we look for the factors, like for the performance indicator for microbial fuel cell, usually the voltage, measured voltage, the Coulomb efficiency, current density, and CO2 removal. And for the process parameters, we look for applied potential at the voltage, retention time, microbial fuel cell feeding mode. In the pilot scales, the volume that's needed for the pilot, the membrane or the pilot shape, the materials like used for electrode design, The parameters there is anodic area, volume ratio, anodic projected area, anodic work volume, anodic geometry or material. Also, we have the inner column, which is bio age, and this is like the biofilm aging is the challenge. And then we have the substrate properties and operating condition like the BOD, conductivity, nitrogen, pH, CODs, temperature, type of effluent. Substrates used, it's different. As we said, in our case, we'll use the wastewater, but like in the research, people using different substrates, acetate, arbitol, cellulose particles, corn, stover biomass, farm manure, ethanol, glucose, acetate, landfill, many of them. And this is like the most common one used as electron donors at the anode, and for the cathode side, these like the most used element as expressed. Oxygen is the most used one, but some people they are using bicarbonate, acetate, nitrate or nitrite, permanganate, iron or copper. And for each one of these substrates, the concentration would be different, and accordingly the current density would be different. Now, the catalyst used in microbial fuel cell is platinum or platinum alloy, which is very expensive. And because of that, there are many research to replace this expensive catalyst with catalyst that's cheaper, or using metals that's cheaper than platinum, like nickel, cobalt, copper, or even silver. Were investigated. Some metal oxides such as manganese oxide and titanium oxide were also used. Nitrogen fractionalized carbon nanotubes were also used as catalyst for microbial fuel cell as replacement for platinum. The performance will not be the same, but for the visibility study, when the catalyst is cheaper, even if the performance or the reaction kinetics is lower, then it would be justified by the cost. For the membranes, which is the heart of the microbial fuel cells, Nafion is the most used membrane, and Nafion is also very expensive membrane. It has the highest proton conductivity, and it is stabilized membrane. It has a chemical and mechanical stability very high. However, it is very expensive, and it has an disadvantage. The proton conductivity for Nafion, it decreases dramatically at high temperature. It is not that challenge in microbial fuel cell. For BIM fuel cells, it is a big challenge, because in BIM fuel cells, people tend to go for higher temperature to enhance the kinetics for the reactions. However, in microbial fuel cell, usually people, they don't go for that high temperatures. Usually the highest temperature would be 40 or maybe 50. They don't go for 100. However, the proton conductivity for Nafion decreased by increasing the temperature. So people, they are trying to go for other alternatives using zirconium hydrogen phosphate, polyether sulfone, enzymodiazole, sulfonated polyether ketone, SPEAK, or other composite membranes. They are trying, like, so they got this polymeric membrane, maybe sulfonated that polymeric membrane. Sometimes they are adding some inorganic materials for these membranes to enhance the stability, to enhance the conductivity. The conductivity so far not competing with the Nafion conductivity, but at higher temperatures they were able to compete or exceed the Nafion conductivity, because the Nafion conductivity decreased at higher temperatures. Another challenge for microbial fuel cell is the biofouling, and there should be, like, there's a lot of work in to remove or to decrease the biofouling or mitigate the biofouling, and the most commonly used methods are using smoother surfaces. So when the surface for the membrane is smooth, usually the biofilm doesn't like grow in the membrane. Increasing the hydrophilicity of the membrane, this will enhance the H2 transfer and also will decrease the biofilm formation. Adding negative charge to the membrane, which also decrease the biofilm formation or the biofouling, and sometimes people sterilize or using the sterilizing agents to kill this biofilm at the membrane surface to get rid of this biofouling or mitigate biofouling. Other challenge is scalability. To make this process commercial, you need to scale it up. You need to go for from the lab to pilot plant, then the commercial scale, and it needs to increase the volume for the microbial fuel cells. So like working with the small or lab scale chambers will show like the performance very high, everything is going fine. However, when you go for large volumes, more challenges will appear. This graph shows like how the historical timeline, like starting from 1911 when we have the first microbial fuel cell, then at 2007 where the scale up started with microbial fuel cell. We have 1 meter cube in 2008. Then we go for a pure culture for microbial fuel cell the same year. Then we have 20 liter stacking in 2009. Then in 2011 there were like 1,000 liter 1 meter cube with 190 liter per day hydrogen production. Then like it goes like scaling up, trying to increase the size, going for more stages, trying more elements, and improving the anode and the cathode. And this continues until 2013, okay, when the wetland microbial fuel cell was constructed in 2013. Scaling, as I said, we have to work on both the current produced from the microbial fuel cell, the same way we need to go for higher size. So if we plot the current versus size, we can see these trials that we showed before, and we need to go toward the right corner where the size for the microbial fuel cell would be large, more than 1 meter cube or 2 meter cube or higher meter cube, by the same way keeping the current density at highest level. Okay, so we don't want to sacrifice the current density because this will affect the feasibility of microbial fuel cell. With that, I will come to my conclusions. The performance of microbial fuel cell is governed by many factors: design aspect, material selection, the operating condition, the micro environment challenges, and all that need to be optimized to be able to make the microbial fuel cell commercialization for the microbial fuel cell. To overcome the scale-up challenges, we need to appropriately select expensive materials for the electrode, for the membrane, and for the anode, and this would be a key for scale-up. For longevity, maintaining the stable performance of the membrane and controlling the biofouling. Or the biofouling should be controlled, and this could be happen using physiochemical and biological treatment methods, as I showed before. The commercialization of microbial fuel cell for on-site bioremediation require optimizing the operating condition and identifying low-cost electrode or membrane materials. The field trials such as bioelectric toilet, B-power microbial fuel cell, 1,000 liter microbial electric cell, 100 liter microbial desalination cell are positive indicators for the readiness for such technology for practical applications. Economics is one of the most important aspects for scaling up. if we want to go for commercialization, you need to be sure this process is feasible, and the key point for that is using expensive materials. So finding a new catalyst other than platinum, a new membranes other than Nafion, this would be very important. Additional research incentives and funding should be diverted toward scaling up attempts for microbial fuel cell and promoting the work from scalability to practicability. With that, I finish my presentation. Thank you very much for listening, and you are welcome if you have any question.
Thank you, Dr. Muhammad, for very nice and informative presentation. And I will open the door for the audience if you have any question.
Hello.
Yes.
Yes.
Yes. Thank you, Dr. Mohammed. It's a very nice lecture. Actually, I have collaborated, for your information, with Sharjah University with Dr. Ahmed Mohammed, but he returned now to United States. I liked very much your talk, and especially when you talked about the biofouling of the membranes and the catalyst. You mentioned the lower cost catalyst than platinum, but you mentioned silver and copper. Silver and copper are maybe they prevent biofouling. So what is your opinion? Could you have the catalyst which serves also as anti-bacterial, anti-fouling nanomaterial? What is your opinion?
Like the copper, this is one of their disadvantages because they can kill the microorganism at the anode. Okay, usually the fouling would happen at the membrane side.
Yes.
For sure, if the copper would be at that side, it will kill the. But the advantage for the copper and silver that they may kill the microorganism that's there to operate the microbial fuel cell. But people, they are trying to use them to check their performance, and for sure they will have some disadvantages, but also they have very high disadvantage because they are very conductive for electricity, and this would enhance the electron transfer in the microbial, which is one of the challenges.
Okay, so what is needed is less conductivity, is catalysis, but without a lot of electron transfer. Is that what
No. We need the electron transfer, but we don't want materials that kill the bacteria or the microorganism.
Okay. I understand. Okay.
Thank you.
Thank you.
You are welcome.
One more question. Okay, Dr. Muhammad, I have a question. As I understood from your conclusions, there are many limitations actually for microbial fuel cells.
Yes.
So where do you think this technology will be within 10 years from now?
People are working, like there's many advances, like in the catalyst size, in both at the anode and the cathode, and in the membrane. Like we were able in our labs to get very good results for electrodes for the anode side. We tried many catalysts at the cathode side, and they give us very good results. However, the challenge is to go from lab scale to the commercial. Like every time we try to increase the volume for the microbial fuel cell, the control, the stability of the microbial fuel cell is challenging. The same way with the membrane. Like we produce membranes with a controlled size, maybe 5 centimeter by 5 centimeter, 10 centimeter by 10 centimeter. But if you want to operate large volume, you need to have larger membranes that would have the reproducibility. You'd have the conductivity controlled. So there's like two ways for scalability. The volume is one of them. Sometimes maybe the volume would be less, but you go for stacking. But people working to overcome these challenges 10 years, maybe before 10 years, it would be commercial. Like there is like some pilot plant scales and they are working well, but the cost is still high, like not with the cheap materials.
So what do you think the major challenge now to go to further modification?
Materials, electrodes and membranes. This is the major challenges.
Okay. Okay, thank you, Dr. Mohammed.
You are welcome. You are welcome.
Okay, I think we have finished our presentations for today, and I would like to thank all of you for joining us for this presentation. Very nice presentation, and I move the floor to Dr. Kishore, the chairman of the conference. Dr.
Thank
Kishore,
you. Thank you, Dr. Khaled. Thank you, Dr. Shane. And I would like to thank all the moderators and speakers for today. And I would like to thank also all our audience. I want just to remind you all that we will have another day tomorrow, day 2, and we will have, it will start at 9 a.m. and end at 1:30, the first session. The next session will start 3 p.m. and finish 7 p.m. And we will be considering SDG Goal 7, affordable and clean energy, where we will talk about energy storage, battery and solar cells, and clean energy. And at the evening, we will be considering industry, innovation, and infrastructure. So stay tuned for tomorrow, and good night all.
okay, good night for all.
Thank you.
Good night,
Good night.
everybody. Assalamu alaikum.
Assalamu alaikum.